140 modern cybersecurity incident types, designed for experienced engineers, security architects, and senior interviews.
This is not a beginner OWASP list. This is how incidents are actually categorized in real postmortems, SOC reviews, and staff or principal interviews in 2026 and beyond. Think of this as a mental map of how security fails today.
How security systems actually fail.
This video is not a list of vulnerabilities, tools, or certifications. It is a deep walkthrough of how modern security systems fail in the real world, even when they pass audits, follow frameworks, and are signed off by experienced teams. These are the explanations senior and staff-level interviewers are actually listening for.
How to watch this video important.
This video covers more than 140 real-world security incidents. You are not expected to memorize them. Instead, they are grouped into 14 recurring failure patterns. Interviews do not test recall. They test whether you can recognize patterns under pressure and explain why controls failed without being bypassed.
How the video is structured.
We move through 14 categories. Each category represents a specific way security breaks in modern systems. Inside each category, you will see multiple real incidents that follow the same pattern. If you understand the pattern, you can explain any incident in that category, even ones you have never seen before.
The 14 security failure categories covered.
These categories reflect how cybersecurity incidents actually occur in 2026 and beyond. 1. Identity and access control failures. 2. Cloud configuration and control plane failures. 3. Software supply chain attacks. 4. Data exposure and privacy breaches. 5. API and application logic abuse. 6. Ransomware and lateral movement. 7. Insider threats, intentional and accidental. 8. Observability and monitoring failures. 9. Availability and resilience attacks. 10. AI and Gen AI-specific security failures. 11. Governance and process breakdowns. 12. Kubernetes and container runtime failures. 13. Shadow AI and data sovereignty failures. 14. Integrity and logic corruption incidents. Each category is a failure pattern, not a checklist and not a tool comparison.
Category 1. Identity and access control failures.
This category focuses on incidents where systems were compromised without exploits, malware, or 0 days. These failures happen when identities are trusted too broadly, for too long, or in the wrong context. In senior interviews, this category is used to test whether you understand access as a living system, not a static policy.
Category 1. Identity and access control failure patterns.
In this category, we will analyze the following real-world incident patterns. 1. Overprivileged IAM roles used legitimately. 2. Long-lived credentials leaked through logs or CICD. 3. Token replay attacks in OAuth and JWT systems. 4. MFA fatigue and push notification abuse. 5. Service-to-service authentication bypass. 6. Broken cross-account trust relationships. 7. Privilege escalation through misscoped policies. 8. Orphaned access after employee offboarding. 9. Identity sprawl across SaaS and cloud platforms. 10. Legitimate access used for silent data exfiltration. Every incident in this category passed initial security reviews and still resulted in compromise.
Real-world cybersecurity incident number 1. Overprivileged IAM roles used legitimately.
A production service accessed and exfiltrated sensitive customer data for days without triggering a single security alert. There were no failed logins, no blocked API calls, and no policy violations. Every action was fully authorized, logged, and compliant with existing IAM reviews.
1. The setup. Everything looks secure.
IAM roles were reviewed and approved. Cloud Trail was enabled across all accounts. MFA was enforced for human access, and services used short-lived credentials. The environment passed internal security reviews and external audits without findings.
2. What passed audits? Security incidents that passed every audit.
No wildcard permissions were flagged. Policies followed least privilege guidelines on paper. Access reviews showed valid business justification. And all data access originated from approved service roles operating inside production boundaries.
3. The breach. What failed anyway?
The service legitimately queried large datasets unrelated to its core responsibility, and streamed them to an external destination. Because the access pattern resembled normal operational traffic, detection systems did not flag the activity until downstream business anomalies appeared.
4. Where controls broke, diagnosis.
IAM correctly verified identity but failed to enforce intent. Multiple responsibilities were bundled into a single role, expanding blast radius. Monitoring focused on authentication failures rather than misuse of valid permissions, allowing the activity to persist unnoticed.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Authentication worked correctly, but authorization lacked containment. 2. The role violated single responsibility by combining unrelated permissions. 3. Valid credentials are assumed to be misused eventually, not protected forever. 4. Blast radius matters more than permission count when incidents occur. 5. Security maturity comes from designing narrow trust boundaries, not stronger logins.
6. The trade-off nobody mentions.
1. Smaller IAM roles increase deployment complexity and coordination overhead. 2. Operational velocity slows when permissions are tightly scoped. 3. Teams must manage more roles, reviews, and change processes. 4. In return, incidents are contained instead of becoming organization-wide failures. Here is the IAM policy showing how task scope permissions reduce blast radius compared to broad service roles. Disclaimer: always test code in a non-production environment. Here is the code limiting the service to read-only operations. This prevents silent escalation into write, export, or destructive actions. This line scopes access to a single dataset, ensuring legitimate misuse cannot pivot into unrelated customer data.
Follow-up 1. Senior level. What if the service occasionally needs broader access during migrations?
Answer: I treat elevated access as a temporary operational event, not a permanent configuration. Access is granted through time-bound role assumption with automated expiration, enhanced logging, and post-migration audits. Broad permissions never live longer than the task that requires them.
Follow-up 2. Staff level. How do you prevent teams from slowly expanding role permissions over time?
Answer: I enforce permission drift detection and role ownership accountability. Any permission change requires a business justification tied to a single responsibility, and unused permissions are automatically flagged and removed during scheduled access reviews.
Follow-up, curveball. What if leadership resists because this slows delivery?
Answer: I frame blast radius reduction as insurance. Slower delivery is a visible cost, but uncontrolled incidents create invisible risk that becomes painfully obvious during breaches. Leadership support follows once containment is positioned as business resilience, not security overhead.
8. Pro insider tip.
Most IAM breaches do not involve attackers breaking controls. They involve systems doing exactly what they are allowed to do. In interviews, replacing the phrase least privilege with blast radius reduction instantly signals real-world security experience.
Real-world cybersecurity incident number 2. Long-lived credentials that were never supposed to exist.
A production breach was traced back to an access key that had been active for over 18 months. The key was not stolen through malware or phishing. It was committed to a private repository during an emergency fix, copied into multiple scripts, and quietly propagated across environments.
1. The setup. Everything looks secure.
The organization enforced MFA for all human users, used IAM roles for production workloads, and had periodic credential rotation policies documented. CICD pipelines were locked down and passed security reviews.
2. What passed audits? Security incidents that passed every audit.
Audits verified MFA compliance, confirmed no hard-coded secrets in main branches, and validated that production services used IAM roles. The leaked key lived outside the audited paths, embedded in auxiliary scripts and legacy automation.
3. The breach. What failed anyway?
An attacker gained access to the long-lived access key through a compromised developer machine backup. Because the key was valid, unrestricted by session duration, and widely trusted, it enabled sustained access without triggering authentication alerts.
4. Where controls broke, diagnosis.
Security controls focused on identity hygiene for humans and services, but failed to account for credential persistence outside those systems. The real failure was allowing static credentials to exist at all, bypassing the protections built around short-lived identity.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Static credentials are liabilities, not conveniences. 2. Short-lived credentials limit blast radius by default, even when leaked. 3. IAM roles enforce time, context, and revocation automatically. 4. Any access key that cannot expire is a security debt. 5. Eliminating static credentials is more effective than rotating them.
6. The trade-off nobody mentions.
1. Removing access keys complicates local development and legacy tooling. 2. Teams must rework scripts, automation, and vendor integrations. 3. Debugging becomes harder when credentials expire mid-session. 4. The payoff is immediate revocation and drastically reduced dwell time. Here is the AWS CLI configuration, showing how role-based access replaces long-lived access keys. Disclaimer: always test code in a non-production environment. Here is the code initiating a short-lived session instead of using static credentials. The session automatically expires, limiting how long leaked access can be abused. This binds access to a specific session, improving traceability and allowing rapid revocation without rotating secrets.
Follow-up 1. Senior level. What about third-party tools that require access keys?
Answer: I isolate them behind tightly scoped roles or use vendor integrations that support role assumption. If static keys are unavoidable, they are restricted, monitored aggressively, and treated as temporary exceptions with clear ownership and expiry.
Follow-up 2. Staff level. How do you detect leaked keys that are already in use?
Answer: I combine IAM Access Analyzer, Cloud Trail Anomaly Detection, and usage pattern baselining. Keys used outside expected locations, times, or workflows are flagged even if the API calls themselves are valid.
Follow-up 3. Curveball. What if engineers push back because keys are easier?
Answer: ease of use is not a security argument. I explain that keys trade short-term convenience for long-term incident response pain. Once teams experience instant revocation with role-based access, the resistance fades.
8. Pro insider tip.
The most dangerous AWS access keys are not the ones in public repos. They are the ones quietly copied between scripts, laptops, and backups. In interviews, saying, "We eliminated static credentials entirely," is a strong higher signal.
Real-world cybersecurity incident number 3. Token replay using valid OAuth/JWT sessions.
A partner integration was abused to repeatedly access sensitive APIs using perfectly valid OAuth tokens. No credentials were stolen, no signatures were forged, and no scopes were escalated. The attacker simply replayed already issued tokens until business limits were exceeded.
1. The setup. Everything looks secure.
The system used OAuth 2.0 with short-lived JWT access tokens, HTTPS everywhere, and scope-based authorization. Tokens were signed, validated, and issued by a trusted identity provider. All requests passed authentication and authorization checks.
2. What passed audits? Security incidents that passed every audit.
Auditors verified token expiration times, confirmed signature validation, checked scopes, and reviewed OAuth flows. From a standards perspective, the implementation was compliant and correctly configured.
3. The breach. What failed anyway?
The same access token was reused thousands of times from multiple locations within its valid lifetime. Because the token itself was legitimate and unexpired, every request succeeded, allowing large-scale data extraction and abuse of business workflows.
4. Where controls broke. Diagnosis.
Authentication verified token validity, but the system assumed tokens were single-use in practice. There was no binding between a token and its execution context, no replay detection, and no rate limiting at the token level.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. OAuth validates identity, not intent or usage patterns. 2. A valid token can still be maliciously reused within its lifetime. 3. Security requires binding tokens to context, not just verifying signatures. 4. Replay protection belongs at the application layer, not the identity provider. 5. Rate limits and non-C checks close gap standards do not cover.
6. The trade-off nobody mentions.
1. Replay protection adds statefulness to otherwise stateless APIs. 2. Non-C tracking and token binding increase storage and latency. 3. Strict enforcement can break legitimate retries and client behavior. 4. Teams must balance abuse prevention against system simplicity. Here is a JWT claim pattern showing how non-C and audience binding reduce token replay risk. Disclaimer: always test code in a non-production environment. This binds the token to a specific service, preventing reuse across unintended APIs. This unique token identifier enables replay detection by tracking whether a token has already been used.
Follow-up 1. Senior level. How do you handle legitimate retries without triggering replay blocks?
Answer: I allow idempotent retries by scoping replay checks to sensitive operations and short time windows. For read-heavy endpoints, I rely on rate limiting instead of strict non-C enforcement to avoid breaking client behavior.
Follow-up 2. Staff level. Why not just shorten token expiration times?
Answer: shorter lifetimes reduce exposure but do not eliminate replay within the valid window. Attackers can still cause damage quickly. Replay protection addresses a different threat class than expiration alone.
Follow-up curveball. What if your identity provider does not support non-C claims?
Answer: I implement replay protection at the API gateway or application layer. Security guarantees should not depend entirely on IDP features when business impact is high.
8. Pro insider tip.
OAuth standards assume honest clients. Real systems face adversarial reuse. In interviews, calling out replay risk with invalid token lifetime signals deep understanding beyond protocol compliance.
Real-world cybersecurity incident number 4. Session fixation in single-page applications. SPA.
A customer-facing web application was compromised without any credential theft. Users logged in successfully, MF worked as expected, and no suspicious login attempts were detected. Yet attackers were able to hijack authenticated sessions and perform actions as legitimate users.
1. The setup. Everything looks secure.
The application was a modern SPA using OAuth-based login, HTTPS everywhere, secure cookies, and MF for user authentication. Session identifiers were present, tokens were signed, and front-end security scans showed no obvious vulnerabilities.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed secure cookie flags, validated OAuth flows, verified token expiration, and confirmed MF enforcement. Pen tests focused on login bypass and password compromise, none of which were successful.
3. The breach. What failed anyway?
Attackers pre-generated valid session identifiers and tricked users into authenticating with them via malicious links. Once the user completed login, the attacker reused the same session identifier to gain authenticated access without ever logging in themselves.
4. Where controls broke. Diagnosis.
The application accepted an existing session identifier during authentication and upgraded it to an authenticated session. Authentication validated the user but failed to invalidate or rotate the session identifier, allowing fixation-based hijacking.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Authentication and session management are separate security concerns. 2. A session identifier must never survive a privilege change. 3. SBAs often trust front-end state more than they should. 4. Session rotation on login is mandatory, not optional. 5. Fixation attacks bypass MF because they exploit post-authentication state.
6. The trade-off nobody mentions.
1. Rotating sessions invalidates parallel browser tabs and background requests. 2. Users may experience unexpected logouts after login events. 3. Stateful session regeneration complicates front-end caching logic. 4. The trade-off is minor UX friction versus full account compromise. Here is JavaScript session logic showing how failing to rotate session IDs enables fixation attacks. Disclaimer: always test code in a non-production environment. This explicitly destroys any pre-authentication session identifier, preventing attackers from reusing a fixed session. A brand new session identifier is issued after authentication, ensuring privilege elevation cannot be hijacked.
Follow-up 1, Senior Level. Why doesn't MFA protect against session fixation?
Answer: MF validates identity during authentication, not session ownership afterward. Session fixation abuses post-authentication state. Once a session is authenticated, MF has already done its job and cannot detect reuse of that session.
Follow-up 2, Staff Level. How does this risk increase in SBAs compared to traditional apps?
Answer: SBAs rely heavily on client-side state and long-lived sessions. Token storage in memory or local storage combined with API-driven flows increases the blast radius when session rotation is missed.
Follow-up, Curveball. What if rotating sessions breaks critical user workflows?
Answer: then the workflows are incorrectly coupled to session identity. Security boundaries must not depend on fragile client assumptions. Fixing that coupling is part of the remediation.
8, Pro Insider Tip.
If a session identifier survives login, assume it can be hijacked. In interviews, explicitly saying, "We rotate sessions on every privilege change," signals hands-on application security experience.
Real-world cybersecurity incident number 5, MFA fatigue attacks.
Multiple user accounts were compromised without password theft, malware, or phishing kits. MFA was enabled everywhere and working exactly as designed. Audit logs showed successful MFA approvals from legitimate devices. The breach still happened.
1, the setup, everything looks secure.
The organization enforced MFA for all users, blocked legacy authentication, and required push-based approvals through a trusted identity provider. Login alerts were enabled, and authentication success rates looked normal.
2, what passed audits? Security incidents that passed every audit.
Audits confirmed MFA enforcement, reviewed conditional access policies, and validated that no MFA bypass rules existed. Pen tests focused on credential stuffing and password reuse, all of which failed.
3, the breach, what failed anyway?
Attackers repeatedly triggered MFA push notifications until users approved one out of frustration or confusion. Once approved, attackers gained full access using valid credentials and a legitimate MFA signal.
4, where controls broke, diagnosis.
MFA validated possession of a device, but not user intent. Push-based MFA treated approval as binary truth without context, rate limiting, or challenge verification. The system assumed users would behave securely under repeated prompts.
5, the interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. MFA is not proof of intent, it is proof of device possession. 2. Push fatigue turns humans into an authentication oracle for attackers. 3. Security controls must account for human behavior under stress. 4. MFA approvals require context, throttling, and user verification. 5. Authentication systems fail when they assume perfect user judgment.
6, the trade-off nobody mentions.
1. Stronger MFA prompts slow down legitimate logins. 2. Number matching and challenge questions reduce convenience. 3. Users complain when security interrupts workflow. 4. The alternative is silent account takeover with valid MFA.
Follow-up 1, Senior Level. Why doesn't MFA rate limiting solve this completely?
Answer: rate limiting reduces noise but does not eliminate social pressure. Attackers only need one approval. Without intent verification, even a single successful prompt compromises the account.
Follow-up, Curveball. What if leadership refuses anything beyond push-based MFA?
Answer: then the risk must be explicitly accepted and documented. Security teams should treat push-only MFA as a compensating control, not a strong guarantee, and increase detection and response readiness accordingly.
8, Pro Insider Tip.
MFA fatigue is not a technical failure. It is a human one. In interviews, saying, "We moved from approval-based MFA to intent-based verification," immediately signals real-world security experience.
Real-world cybersecurity incident number 6. Service-to-service authentication bypass.
A backend service accessed sensitive internal APIs without any user context, MFA, or interactive login. No credentials were stolen. No alerts fired. All calls were authenticated and appeared legitimate in logs.
1. The setup, everything looks secure.
The architecture used microservices with service-to-service authentication, short-lived tokens, and IAM roles. Network access was restricted, and internal APIs were never exposed publicly.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed mutual authentication between services, validated TLS certificates, and verified that no hard-coded credentials existed. Access logs showed only approved services making requests.
3. The breach, what failed anyway.
A compromised internal service reused its valid service token to call higher privilege APIs it was never intended to access. Because authentication succeeded, authorization was implicitly trusted.
4. Where controls broke, diagnosis.
Authentication was enforced, but authorization was coarse-grained. Services were trusted as identities instead of being constrained by explicit scopes and intent. Internal traffic was treated as inherently safe.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Service identity alone is not sufficient for authorization. 2. Each service call must be constrained by purpose, not just identity. 3. Internal APIs require the same zero-trust posture as external ones. 4. Fine-grained scopes prevent lateral movement between services. 5. Service-to-service auth failures are authorization failures, not authentication failures. Here is Java service authorization logic showing how missing scope validation allows internal service abuse, despite valid authentication. Disclaimer: always test code in a non-production environment. Here is the code snippet showing how check enforces intent. Authentication proves who the service is. Scope validation proves what it is allowed to do. This code block shows failing closed, prevents silent lateral movement when a service is compromised.
6. The trade-off nobody mentions.
1. Fine-grained authorization increases implementation complexity. 2. Teams must manage scopes and contracts explicitly. 3. Initial development slows down. 4. Blast radius is dramatically reduced during compromise.
Follow-up 1. Senior level. Why isn't mutual TLS enough for service security?
Answer: mutual TLS verifies identity, not intent. Once a service is authenticated, MTLS cannot restrict which APIs it may call. Without authorization checks, compromised services gain excessive power.
Follow-up, curveball. What if teams resist adding scopes due to velocity concerns?
Answer: then the organization is explicitly trading speed for risk. In interviews, the correct answer is to acknowledge the trade-off and show how to phase scopes incrementally on high-risk paths first.
8. Pro insider tip.
Internal service abuse is one of the hardest breaches to detect because everything looks authorized. In interviews, stating that internal traffic must be treated as hostile by default is a strong senior-level signal.
Real-world cybersecurity incident number 7. Broken role assumptions across cloud accounts.
A production breach occurred without compromised credentials or misconfigured permissions in the target account. An attacker pivoted from a lower trust account into a higher privilege production account using a legitimately assumed cross-account role. Every action was authenticated, authorized, and logged.
1. The setup, everything looks secure.
The organization used multi-account cloud architecture with separate accounts for development, staging, and production. Cross-account IAM roles were established to allow controlled access for automation and shared services. Trust relationships were reviewed and approved.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that production resources were not publicly accessible. IAM roles followed naming conventions, and cross-account access required explicit trust policies. No wildcard permissions were detected in permission policies.
3. The breach, what failed anyway.
An attacker compromised a low-privilege service in a non-production account and used its legitimate permissions to assume a cross-account role into production. From there, sensitive data was accessed without triggering alerts because the access path was fully authorized.
4. Where controls broke, diagnosis.
The trust policy assumed that any principal from the source account was safe. Authorization focused on who could assume the role, not why the role was being assumed. Trust boundaries were defined at the account level instead of the workload level.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Cross-account trust is a security boundary, not a convenience feature. 2. Trust policies must constrain intent, not just identity. 3. Accounts are not trust domains, workloads are. 4. Any role that can be assumed broadly will be abused eventually. 5. Authorization failures often hide inside legitimate trust relationships.
6. The trade-off nobody mentions.
1. Tighter trust policies increase configuration complexity. 2. Teams must manage explicit principal lists and conditions. 3. Automation becomes harder to generalize across accounts. 4. The benefit is containment when one account is compromised. Here is IAM trust policy, JSON, showing how broad account-level trust enables cross-account privilege escalation. Disclaimer: always test code in a non-production environment. Here is the code snippet trusting the entire source account. This allows any principal in that account to assume the role once compromised. This code block shows unconditional role assumption without intent checks, enabling lateral movement across accounts using valid authentication.
Follow-up 1. Senior level. How do you restrict trust without breaking automation?
Answer: I scope trust policies to specific roles instead of entire accounts and add conditions such as external IDs or source identity. Automation still works, but the blast radius is constrained to known workloads.
Follow-up, curveball. What if teams insist on account-level trust for speed?
Answer: then the risk must be explicitly accepted. In interviews, the correct response is to acknowledge that account-level trust optimizes velocity at the cost of containment during compromise.
8. Pro insider tip.
Most cross-account breaches are not caused by bad permissions, but by overtrusting entire accounts. In interviews, saying, "Accounts are not trust boundaries, workloads are," signals real-world cloud security experience.
Real-world cybersecurity incident number 8. Privilege escalation via misscoped IAM policies.
A production environment was compromised without stolen credentials, exploits, or misconfigured network access. A low-privilege role gradually escalated its own permissions using actions that were explicitly allowed by IAM policies. Every API call was authenticated, authorized, and compliant.
1. The setup. Everything looks secure.
IAM roles were created for automation tasks with narrowly scoped permissions. Policies were version-controlled, reviewed during onboarding, and attached only to non-human service roles. No administrator access was granted directly.
2. What passed audits? Security incidents that passed every audit.
Audits verified that no roles had administrator access attached, checked for wildcard resources, and confirmed separation between IAM management and application roles. Permission boundaries were documented but not enforced.
3. The breach. What failed anyway?
A service role was able to attach additional IAM policies to itself using allowed IAM actions. Over time, the role accumulated broader permissions, eventually gaining access equivalent to an administrator without ever violating policy rules.
4. Where controls broke. Diagnosis.
IAM evaluated permissions correctly, but allowed identity self-modification. The policy granted write access to IAM without enforcing boundaries, allowing the role to expand its own authority incrementally.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Privilege escalation often happens through allowed management actions. 2. IAM write permissions are more dangerous than data permissions. 3. Roles must never be allowed to modify themselves. 4. Permission boundaries exist to cap blast radius, not to document intent. 5. Escalation paths usually look compliant until it is too late.
6. The trade-off nobody mentions.
1. Permission boundaries add cognitive overhead for developers. 2. IAM changes require tighter review processes. 3. Automation becomes less flexible. 4. The benefit is prevention of silent, incremental privilege escalation. Here is IAM policy JSON showing how allowing IAM attach role policy enables self-service privilege escalation. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing the role to attach new policies to itself. This enables incremental privilege escalation without breaking any rules. This code block shows self-referential permission scope. The role is explicitly allowed to modify its own authorization boundary.
Follow-up 1, senior level. How do you prevent this without blocking automation?
Answer: I enforce permission boundaries and separate IAM management roles from application roles. Automation can request changes, but cannot apply them to itself without external approval.
Follow-up, curveball. What if teams argue this slows delivery?
Answer: then the trade-off must be explicit. In interviews, the correct response is to say that IAM write access is a production safety control, not a convenience feature.
8, pro insider tip.
Most IAM privilege escalations happen using permissions that look harmless in isolation. In interviews, stating that IAM write actions are equivalent to admin access without boundaries signals real-world cloud security experience.
Real-world cybersecurity incident number 9. Orphaned access after employee offboarding.
A former employee retained access to production systems weeks after leaving the organization. No credentials were stolen, no alerts were triggered, and no policies were violated. The access remained valid because offboarding focused on HR workflows, not identity lifecycle enforcement.
1. The setup. Everything looks secure.
The organization used centralized identity management, enforced MFA, and followed documented offboarding procedures. Employee accounts were deactivated in the primary identity provider on the employee's last day.
2. What passed audits? Security incidents that passed every audit.
Audits verified timely HR termination records, IDP account deactivation, and removal from primary access groups. No active human user accounts were detected for former employees.
3. The breach. What failed anyway?
The former employee retained access through an API access key created earlier for automation and testing. Because the key was not tied to the IDP account lifecycle, it remained active and usable after offboarding.
4. Where controls broke. Diagnosis.
Offboarding revoked interactive access but failed to revoke non-human credentials. Identity lifecycle controls assumed all access flowed through the IDP, leaving standalone access keys orphaned and invisible to HR-driven processes.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Offboarding is an identity lifecycle problem, not an HR task. 2. Access that is not centrally governed will not be centrally revoked. 3. Non-human credentials must be owned, inventoried, and expired. 4. Any credential that survives termination is a breach waiting to happen. 5. Identity systems must control all access paths, not just user logins.
6. The trade-off nobody mentions.
1. Centralizing credential ownership increases operational overhead. 2. Legacy scripts and tools must be refactored. 3. Teams lose the convenience of ad hoc access keys. 4. The benefit is guaranteed access revocation on termination. Here is IAM user policy JSON, showing how unmanaged access keys survive employee offboarding. Disclaimer: always test code in a non-production environment. Here is the code snippet granting direct data access through an access key. This permission remains active even after the human identity is deactivated. This code block shows data access not bound to an identity provider session, allowing orphaned credentials to continue functioning silently.
Follow-up 1, senior level. How do you ensure offboarding revokes all access paths?
Answer: I eliminate standalone access keys and require all access to flow through centrally managed identity systems with enforced expiration. If a credential cannot be revoked automatically, it is not allowed.
Follow-up, curveball. What if teams insist they need long-lived keys for automation?
Answer: then those keys must be treated as production identities with ownership, monitoring, and expiration. In interviews, the correct answer is that convenience does not override lifecycle control.
8. Pro insider tip.
Most offboarding breaches are not caused by missed checklists but by invisible credentials. In interviews, saying, offboarding must revoke every credential, not just user accounts, signals real-world security maturity.
Real-world cybersecurity incident number 10. Identity sprawl across SaaS platforms.
Sensitive company data was accessed and exfiltrated by former employees months after their departure. No single system was breached. Instead, access persisted across multiple SaaS platforms that were never centrally governed or reviewed.
1. The setup. Everything looks secure.
The organization used a central identity provider for core systems, enforced MFA, and had documented onboarding and offboarding processes. Major SaaS tools were integrated with SSO, and IT maintained an official application inventory.
2. What passed audits? Security incidents that passed every audit.
Audits focused on SSO-integrated applications, verified IDP deprovisioning workflows, and confirmed MFA enforcement. No active user accounts were found in centrally managed systems after termination.
3. The breach. What failed anyway?
Former employees retained access to smaller SaaS platforms that were never integrated with the identity provider. These tools stored documents, API tokens, and customer data, allowing ongoing access without triggering any centralized alerts.
4. Where controls broke. Diagnosis.
Identity governance assumed SSO coverage equaled identity coverage. Accounts created directly in SaaS tools fell outside lifecycle management, creating blind spots where access persisted indefinitely.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Identity sprawl is an ownership problem, not a tooling problem. 2. SSO adoption does not eliminate unmanaged accounts. 3. Access reviews must include every system holding data. 4. Untracked SaaS applications create silent long-term exposure. 5. Identity governance must follow data, not just users.
6. The trade-off nobody mentions.
1. Centralized SaaS governance slows experimentation. 2. Teams lose autonomy to adopt tools independently. 3. Application inventories require continuous maintenance. 4. The benefit is full visibility into who can access company data.
Follow-up 1. Senior level. Why isn't SSO enough to solve identity sprawl?
Answer: SSO only governs applications that are integrated. Any SaaS tool that allows local accounts bypasses identity lifecycle controls entirely unless explicitly governed.
Follow-up curveball. What if teams adopt SaaS tools without approval?
Answer: then the risk must be addressed at the organizational level. In interviews, the correct response is to say that shadow SaaS is an identity risk, not just a procurement issue.
8. Pro insider tip.
Most identity sprawl incidents are discovered during legal or compliance reviews, not security monitoring. In interviews, saying SSO is not identity governance signals real-world security leadership.
Category 1 wrap-up. Identity and access control failures.
Every incident in this category had one thing in common: identity controls worked exactly as designed. Credentials were valid, MFA succeeded, tokens were trusted, and permissions were approved. The failures came from assuming that identity correctness equals security. In reality, identity is only the starting point, not the safety net.
Why identity failures are so dangerous.
Identity-based breaches rarely trigger alarms because nothing looks wrong. Logs show successful authentication, authorized access, and compliant behavior. That is precisely why these incidents cause the most damage before detection. When identity is overtrusted, misuse becomes invisible.
Transition from identity to cloud control plane failures.
So far, every failure assumed the attacker already had valid access. Next, we shift focus to an even more uncomfortable truth: many breaches do not require abusing identity at all. They happen because the cloud itself was configured incorrectly.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers, like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews, like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 2. Cloud Configuration and Control Plane Incidents.
Cloud security failures are not application bugs and not user mistakes. They are control plane decisions expressed as configuration. When these decisions are wrong, the cloud does exactly what it was told to do at massive scale.
What makes cloud incidents different?
In cloud environments, configuration is code and code is power. A single misconfigured policy, network rule, or logging setting can silently expose entire datasets or eliminate forensic visibility. These incidents rarely involve exploits. They involve defaults, assumptions, and drift.
Category 2. Cloud Configuration and Control Plane Incidents we will cover.
In this category, we will break down the following real-world failure modes. 1. Public object storage exposure across S3, blob, and GCS. 2. Misconfigured security groups and firewall rules. 3. Open cloud metadata services enabling credential theft. 4. Cross-account trust misconfigurations. 5. Logging disabled or overwritten in production. 6. Shadow infrastructure created outside infrastructure as code. 7. Drift between ISC definitions and runtime state. 8. Overly permissive managed cloud policies. 9. Unrestricted egress enabling silent data exfiltration. 10. Region-based compliance and data residency violations. In cloud security, the most dangerous vulnerabilities are the ones that look like normal configuration.
Real-world cybersecurity incident number 11. Public object storage exposure.
Sensitive customer data was accessed publicly without exploiting the application, compromising credentials, or bypassing authentication. The data was exposed because object storage was configured to allow public access. The cloud platform behaved exactly as configured.
1. The setup. Everything looks secure.
The organization used cloud object storage for application assets and data exports. Access was managed through bucket policies and IAM roles. Infrastructure was provisioned through infrastructure as code and passed security reviews.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed encryption at rest, encryption in transit, and no publicly exposed compute resources. IAM roles were reviewed and no excessive permissions were detected. Application authentication controls were functioning correctly.
3. The breach. What failed anyway?
A storage bucket was configured to allow public read access. Anyone with the object URL could download sensitive files. Because no authentication was required, the access bypassed all identity and application-level controls.
4. Where controls broke. Diagnosis.
Security controls focused on identity and application access, but the data layer was exposed directly. Object storage permissions were treated as static configuration instead of a critical security boundary.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Object storage permissions bypass application security entirely. 2. Public access at the data layer non-IFIs identity controls. 3. Encryption does not protect against unauthorized reads. 4. Cloud services do exactly what configuration instructs. 5. Data exposure is often a configuration decision, not an exploit.
6. The trade-off nobody mentions.
1. Restricting public access complicates content delivery workflows. 2. Teams must use signed URLs or access proxies. 3. Operational complexity increases for data sharing. 4. The benefit is elimination of anonymous data exposure. Here is S3 bucket policy JSON, showing how public read access exposes data without authentication. Disclaimer: always test code in a non-production environment. Here is the code snippet granting access to everyone. This removes identity as a control entirely and allows anonymous data access. This code block shows read access granted directly at the storage layer, bypassing application and IAM authorization.
Follow-up 1, senior level. Why didn't IAM prevent this?
Answer: IAM governs authenticated principals. Public bucket policies operate outside IAM evaluation. Once public access is allowed, IAM is no longer part of the decision.
Follow-up, curveball. What if the business requires public access?
Answer: then access must be limited to non-sensitive assets and enforced through signed URLs or access layers. In interviews, the correct answer is to separate public content from protected data entirely.
8, pro insider tip.
Most cloud data breaches are configuration mistakes, not attacks. In interviews, saying object storage permissions bypass application security entirely signals real-world cloud security experience.
Real-world cybersecurity incident number 12. Misconfigured security groups and firewall rules.
Production systems were accessed directly from the internet without exploiting the application or bypassing authentication. The exposure occurred because network firewall rules allowed broad inbound access. Every connection was permitted by configuration.
1. The setup. Everything looks secure.
The environment used virtual private networks, private subnets, and security groups to restrict access. Network rules were defined through infrastructure as code and reviewed during provisioning.
2. What passed audits? Security incidents that passed every audit.
Audits verified that no servers had public IP addresses assigned manually and confirmed that firewall rules were documented. Application authentication and authorization controls were functioning correctly.
3. The breach. What failed anyway?
A security group rule allowed inbound traffic from any IP address on a sensitive service port. Attackers connected directly to the service, bypassing application layer controls entirely.
4. Where controls broke. Diagnosis.
Network controls were treated as supporting infrastructure instead of a primary security boundary. Broad CIDR ranges were allowed for convenience and never revisited as the environment evolved.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Network access is a security control, not a routing decision. 2. Any open inbound rule becomes an attack surface. 3. Application security cannot compensate for exposed network services. 4. Firewall rules must reflect intent, not convenience. 5. Most network breaches are caused by overly broad CIDR ranges.
6. The trade-off nobody mentions.
1. Restrictive network rules slow troubleshooting and debugging. 2. Teams must manage IP allow lists and access paths carefully. 3. Temporary access exceptions require discipline to remove. 4. The benefit is elimination of direct internet exposure. Here is security group rule JSON, showing how open inbound access exposes internal services to the internet. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing inbound access from any IP address. This exposes the service globally without authentication. This code block shows a sensitive service port open directly to the internet, bypassing application and identity controls.
Follow-up 1. Senior level. Why didn't application authentication stop this?
Answer: application authentication only applies when traffic reaches the application layer. Network-level exposure allows attackers to interact with services before authentication logic is invoked.
Follow-up curveball. What if teams need temporary open access?
Answer: then access must be time-bound, documented, and automatically revoked. In interviews, the correct response is to say that permanent open rules are never acceptable.
8. Pro insider tip.
Most firewall breaches are caused by rules added during emergencies and never removed. In interviews, saying temporary network access must expire automatically signals real-world cloud security experience.
Real-world cybersecurity incident number 13. Open Cloud Metadata Service Exploitation.
Cloud credentials were stolen without phishing, malware, or credential leaks. The attacker never accessed the cloud console. Instead, they queried the cloud metadata service from within a compromised workload and obtained valid temporary credentials.
1. The setup. Everything looks secure.
Workloads ran on cloud virtual machines using IAM roles for access. No static credentials were present. Network access was restricted, and instances were provisioned through infrastructure as code.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that no access keys were hard-coded, IAM roles were scoped correctly, and instances did not expose management ports publicly. Identity controls and network policies appeared sound.
3. The breach. What failed anyway?
An application vulnerability allowed attackers to execute requests from within the instance. From there, the attacker accessed the instance metadata service and retrieved temporary IAM credentials associated with the instance role.
4. Where controls broke. Diagnosis.
The metadata service was accessible without session enforcement. Security assumed that network isolation was sufficient protection, but the metadata endpoint was reachable from any process running on the instance.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Instance metadata is a credential issuance service. 2. Any code running on the instance can reach metadata unless restricted. 3. Network isolation does not protect against internal request forgery. 4. Metadata access must require explicit session enforcement. 5. Cloud credentials are only as safe as the metadata controls.
6. The trade-off nobody mentions.
1. Enforcing metadata session tokens adds implementation complexity. 2. Legacy applications may break when metadata access changes. 3. Debugging instance issues becomes more constrained. 4. The benefit is preventing credential theft via internal compromise. Here is EC2 instance metadata configuration, JSON, showing how disabling IMSF2 allows credential theft via internal requests. Disclaimer: always test code in a non-production environment. Here is the code block enabling the metadata service. This allows any process on the instance to reach the credential endpoint. This code snippet shows metadata access without session tokens, enabling attackers to retrieve credentials using simple internal requests.
Follow-up 1. Senior level. Why isn't IAM role scoping enough here?
Answer: IAM controls what credentials can do, not who can retrieve them. If metadata access is unrestricted, any compromised process can obtain those credentials regardless of scope.
Follow-up. Curveball. What if applications rely on unrestricted metadata access?
Answer: then the risk must be acknowledged and mitigated incrementally. In interviews, the correct answer is to say that IMSF2 should be enforced first on high-risk workloads and expanded over time.
8. Pro Insider Tip.
Most cloud credential theft happens without stealing secrets. In interviews, saying the metadata service is a credential endpoint and must be protected as such signals real-world cloud security experience.
Real-world cybersecurity incident number 14. Cross-account trust misconfiguration.
Sensitive production resources were accessed from a separate cloud account without exploiting applications or stealing credentials. The breach occurred because a cross-account trust relationship was overly permissive. All access was authenticated, authorized, and logged.
1. The setup. Everything looks secure.
The organization used multiple cloud accounts to separate environments and business units. Cross-account IAM roles were created to enable shared services and centralized automation. Trust relationships were reviewed during initial setup.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that production accounts did not grant administrator access externally, and that role assumption required explicit trust policies. No wildcard permissions were found in role permission policies.
3. The breach. What failed anyway?
A role in a non-production account was able to assume a higher privilege role in production because the trust policy allowed any principal from the source account. Once assumed, the role provided broad access to production resources.
4. Where controls broke. Diagnosis.
The trust policy defined the source account as a trust boundary instead of individual workloads. Authorization focused on who could assume the role, not whether the assumption aligned with a specific purpose.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Cross-account trust must be as restrictive as permission policies. 2. Accounts are administrative boundaries, not security boundaries. 3. Trust relationships should be scoped to specific roles and purposes. 4. Broad trust enables silent lateral movement across environments. 5. Authorization failures often hide in trust configuration, not permissions.
6. The trade-off nobody mentions.
1. Restrictive trust policies increase configuration complexity. 2. Shared services require explicit role mapping. 3. Automation must handle more granular assumptions. 4. The benefit is containment when one account is compromised. Here is IAM Trust Policy, JSON, showing how account-wide trust enables unintended cross-account access. Disclaimer: always test code in a non-production environment. Here is the code snippet trusting the entire source account. Any role or user in that account can assume this role if compromised. This code block shows unrestricted role assumption without purpose-based conditions, enabling lateral movement using valid authentication.
Follow-up 1. Senior level. How do you restrict trust without breaking shared services?
Answer: I scope trust to specific roles instead of entire accounts and add conditions such as external IDs or source identity. Shared services still function, but trust is constrained to known workloads.
Follow-up curveball. What if teams want account-level trust for simplicity?
Answer: then the risk must be explicitly accepted. In interviews, the correct response is to acknowledge that account-level trust optimizes convenience at the cost of blast radius during compromise.
8. Pro insider tip.
Most cross-account breaches happen through trust policies, not permission policies. In interviews, saying trust boundaries deserve the same scrutiny as permissions signals real-world cloud security experience.
Real-world cybersecurity incident number 15. Logging disabled or overwritten in production.
A security incident was discovered weeks after it began, not because the attacker was stealthy, but because the system produced no usable forensic data. Logs were missing, incomplete, or overwritten. The breach timeline could not be reconstructed.
1. The setup. Everything looks secure.
The environment used centralized logging, role-based access, and infrastructure as code for provisioning. Log groups existed for all critical services, and monitoring dashboards showed healthy system metrics.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that logging was enabled. IAM roles had permissions to write logs, and monitoring alerts were configured. Compliance checks focused on the existence of logs, not their durability or retention.
3. The breach. What failed anyway?
An attacker performed unauthorized actions that went undetected. When investigators attempted to review logs, critical events were missing because log retention was set to a short window and older logs had already been deleted.
4. Where controls broke. Diagnosis.
Logging was treated as an operational feature instead of a security control. Retention policies, optimized for cost, silently erased forensic evidence, eliminating the ability to detect or investigate malicious activity.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Logs are security artifacts, not debugging tools. 2. Retention defines how far back trust can be reconstructed. 3. Short retention creates a blind spot attackers exploit. 4. Cost optimization should never erase security evidence. 5. If logs cannot support investigations, they do not exist.
6. The trade-off nobody mentions.
1. Longer retention increases storage and processing costs. 2. Search and analysis become more expensive over time. 3. Teams must manage archival strategies. 4. The benefit is the ability to investigate and respond effectively. Here is CloudWatch log group configuration, JSON, showing how short retention silently destroys forensic evidence. Disclaimer: always test code in a non-production environment. Here is the code snippet setting log retention to 7 days. Any activity older than this window is permanently deleted. This code block shows that retention applies to a critical production workload, eliminating the ability to investigate incidents discovered later.
Follow-up 1. Senior level. How do you balance log retention with cost?
Answer, I tier retention by risk. High-impact systems retain logs long-term, while low-risk systems use shorter windows. In interviews, the key is to show that retention decisions are threat-driven, not cost-driven.
Follow-up, curveball. What if leadership pushes to reduce logging costs?
Answer, then the risk must be explicitly accepted. In interviews, the correct response is to explain that reduced retention directly limits incident response and forensic capability.
8. Pro insider tip.
Many breaches go undetected not because attackers hide well, but because logs disappear. In interviews, saying log retention defines our investigative window signals real-world security leadership.
Real-world cybersecurity incident, number 16. Shadow infrastructure created outside infrastructure as code.
A production breach originated from infrastructure that did not exist in any repository, review process, or deployment pipeline. The resource was created manually during an emergency and never brought under infrastructure as code. Security tooling had no visibility into its existence.
1. The setup, everything looks secure.
The organization provisioned infrastructure exclusively through infrastructure as code. Terraform repositories were reviewed, changes required approvals, and drift detection tooling was in place for managed resources.
2. What passed audits? Security incidents that passed every audit.
Audits reviewed Terraform repositories, validated approved modules, and confirmed no insecure resources were defined in code. Drift detection reported no deviations from declared state.
3. The breach, what failed anyway?
During an incident response, an engineer created a temporary security group directly in the cloud console to restore service. The rule allowed broad inbound access and was never removed. Attackers later discovered and exploited the exposed service.
4. Where controls broke, diagnosis.
Infrastructure as code only governed what it created. Resources created outside ISC were invisible to reviews, scanning, and drift detection. The control plane trusted manual changes by default.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Infrastructure as code is a governance boundary, not just automation. 2. Anything created outside ISC bypasses security controls. 3. Drift detection cannot detect resources it does not manage. 4. Emergency changes are the highest risk changes. 5. Shadow infrastructure is invisible risk.
6. The trade-off nobody mentions.
1. Blocking manual changes slows emergency response. 2. Engineers lose direct console access. 3. Operational processes must mature. 4. The benefit is elimination of invisible attack surface. Here is Security Group Rule J. Sun, showing how manually created infrastructure bypasses infrastructure as code governance. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing inbound access from anywhere. Because this resource was created outside ISC, no review or approval was enforced. This code block shows a sensitive management port exposed by shadow infrastructure, creating an attack surface invisible to code-based controls.
Follow-up 1. Senior level. How do you prevent shadow infrastructure during emergencies?
Answer: I restrict console write access and require all changes to flow through ISC pipelines, even during incidents. Emergency modules can exist, but they are still versioned, reviewed, and tracked.
Follow-up, curveball. What if leadership demands console access for speed?
Answer: then the risk must be explicitly accepted. In interviews, the correct response is to state that speed gained through ungoverned changes creates long-term security debt.
8. Pro insider tip.
Most cloud breaches start with resources security teams did not know existed. In interviews, saying, if it's not in ISC, it's not governed, signals real-world cloud security leadership.
Real-world cybersecurity incident, number 17. Drift between infrastructure as code and runtime state.
A production environment deviated from its declared security posture without any code changes. The breach did not originate from malicious commits or pipeline compromise. Instead, runtime configuration drift slowly eroded security guarantees, while infrastructure as code reported everything as compliant.
1. The setup, everything looks secure.
All infrastructure was provisioned using infrastructure as code. Terraform state files were versioned, plans were reviewed, and automated checks validated declared security configurations before deployment.
2. What passed audits? Security incidents that passed every audit.
Audits reviewed infrastructure as code repositories and confirmed that security groups, IAM policies, and logging settings were correctly defined. No insecure configuration was found in code.
3. The breach. What failed anyway?
Over time, manual changes were applied directly in the cloud console to resolve operational issues. These changes were never reconciled back into code. The runtime environment gradually became more permissive than the declared state.
4. Where controls broke. Diagnosis.
Infrastructure as code described intent, but enforcement was optional. Drift detection existed but was not enforced as a blocking control. The system trusted declared state over observed reality.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Infrastructure as code defines intent, not enforcement. 2. Runtime state is the true security posture. 3. Any drift represents undocumented risk. 4. Drift detection without remediation is observability theater. 5. Security must reconcile declared and actual state continuously.
6. The trade-off nobody mentions.
1. Strict drift enforcement reduces operational flexibility. 2. Emergency fixes must be reconciled quickly. 3. Automation complexity increases. 4. The benefit is prevention of silent security erosion. Here is Security Group Rule JSON, showing how runtime drift creates exposure not present in infrastructure as code. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing inbound access from anywhere. This rule exists in runtime, but not in infrastructure as code. This code block shows a sensitive management port exposed due to drift, bypassing code review and deployment controls.
Follow-up 1. Senior level. How do you handle necessary emergency changes?
Answer: I allow emergency changes but require immediate reconciliation back into code. In interviews, the key is to show that drift is temporary, visible, and enforced.
Follow-up curveball. What if teams ignore drift alerts?
Answer: then drift detection is ineffective. In interviews, the correct answer is to say that drift must block or auto-remediate to be meaningful.
8. Pro insider tip.
Most cloud environments are less secure in reality than in code. In interviews, saying runtime state is the source of truth for security signals real-world cloud security maturity.
Real-world cybersecurity incident. Number 18. Overly permissive managed cloud policies.
A production workload gained access far beyond its intended responsibility without custom policy changes or administrator grants. The escalation occurred because a broad managed cloud policy was attached for convenience. All actions were valid, authorized, and logged.
1. The setup. Everything looks secure.
The organization relied on cloud provider managed policies to simplify access management. Roles were created for services and attached to managed policies recommended by documentation. Custom policies were minimized to reduce maintenance.
2. What passed audits? Security incidents that passed every audit.
Audits verified that no custom policies granted administrator access and that only approved managed policies were used. IAM reviews focused on policy names and avoided deep inspection of effective permissions.
3. The breach. What failed anyway?
A service role attached to a managed policy was able to access unrelated services and data stores. The policy included permissions that exceeded the service's intended scope, enabling lateral access without violating any explicit rules.
4. Where controls broke. Diagnosis.
Managed policies optimized for broad usability, not least privilege. Security controls trusted policy labels instead of evaluating effective permissions. The blast radius was inherited implicitly.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Managed policies trade precision for convenience. 2. Policy names do not reflect effective permissions. 3. Least privilege requires evaluating permission unions. 4. Broad policies silently expand blast radius. 5. Custom policies are safer for critical workloads.
6. The trade-off nobody mentions.
1. Custom policies require ongoing maintenance. 2. Policy sprawl increases management overhead. 3. Teams lose one-click convenience. 4. The benefit is predictable and constrained access. Here is IAM Managed Policy JSON, showing how broad permissions silently expand service blast radius. Disclaimer: always test code in a non-production environment. Here is the code snippet granting full access to multiple services. This expands permissions far beyond a single workload's responsibility. This code block shows unrestricted resource scope, allowing the role to access all data across the account without constraint.
Follow-up 1. Senior level. When are managed policies acceptable?
Answer: managed policies are acceptable for low-risk or exploratory workloads. For production systems, I derive custom policies from observed access patterns and restrict them to required actions only.
Follow-up curveball. What if teams resist custom policies?
Answer: then the risk must be acknowledged. In interviews, the correct response is to explain that managed policies optimize speed, while custom policies optimize containment.
8. Pro insider tip.
Managed policies are designed for breadth, not safety. In interviews, saying, "I audit effective permissions, not policy names," signals real-world cloud security experience.
Real-world cybersecurity incident. Number 19. Unrestricted egress enabling silent data exfiltration.
Sensitive production data was exfiltrated over standard HTTPS without triggering network alerts or firewall violations. No inbound rules were misconfigured. The breach succeeded because outbound network traffic was unrestricted and implicitly trusted.
1. The setup. Everything looks secure.
The environment used private subnets, restrictive inbound firewall rules, and application-level authentication. Network security focused on blocking external access to internal services.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that no inbound ports were open unnecessarily, and that perimeter firewalls blocked unauthorized access. Outbound traffic was not evaluated because it was assumed to be safe.
3. The breach. What failed anyway?
After compromising an internal workload, attackers exfiltrated data by sending it to an external endpoint over HTTPS. Because outbound traffic was unrestricted, the activity blended into normal application behavior.
4. Where controls broke. Diagnosis.
Network security assumed that threats only enter environments, not leave them. Egress traffic was not constrained, inspected, or monitored, allowing data to exit without resistance.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Inbound controls do not prevent data exfiltration. 2. Outbound traffic is the primary data loss path. 3. Unrestricted egress turns every workload into a potential leak. 4. HTTPS hides exfiltration inside legitimate traffic. 5. Egress control is a core security boundary.
6. The trade-off nobody mentions.
1. Restricting egress complicates application dependencies. 2. Teams must maintain allow lists for external services. 3. Troubleshooting outbound connectivity becomes harder. 4. The benefit is containment of data exfiltration. Here is Security Group Egress Rule JSON, showing how unrestricted outbound traffic enables silent data exfiltration. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing outbound traffic to any destination. This permits data to leave the environment without restriction. This code block shows all protocols are allowed for egress, enabling attackers to exfiltrate data over any channel.
Follow-up 1. Senior level. Why isn't TLS inspection enough to stop this?
Answer: TLS inspection can detect content, but it does not limit destinations. Without egress controls, attackers can still exfiltrate data to allowed endpoints.
Follow-up curveball. What if applications require broad internet access?
Answer: then egress must be explicitly documented, monitored, and reviewed. In interviews, the correct answer is to say that unrestricted egress is an accepted risk only when consciously managed.
8. Pro insider tip.
Most data breaches leave through the front door. In interviews, saying egress is where data loss actually happens signals real-world cloud security experience.
Real-world cybersecurity incident. Number 20. region-based compliance, and data residency violations.
Sensitive customer data was processed and stored outside approved geographic regions without any system compromise or policy bypass. The violation occurred because cloud resources were deployed in non-compliant regions by default. All operations were authorized and functioned normally.
1. The setup. Everything looks secure.
The organization used infrastructure as code to provision cloud resources and relied on provider defaults for region selection. Compliance requirements were documented, and teams assumed deployments followed those constraints.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed encryption, access controls, and logging across environments. Resource configurations were reviewed, but region placement was not explicitly validated against compliance requirements.
3. The breach. What failed anyway?
New workloads were automatically deployed in a default region outside approved jurisdictions. Customer data was replicated and processed there, resulting in regulatory violations without any technical security alert.
4. Where controls broke. Diagnosis.
Compliance constraints existed as documentation, not enforcement. Infrastructure as code defined resources but did not encode geographic restrictions, allowing non-compliant deployments to proceed silently.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Compliance requirements must be enforced as code, not policy. 2. Default regions are rarely compliant by accident. 3. Data residency is a control plane decision. 4. Cloud platforms will not enforce jurisdictional intent. 5. Security includes regulatory correctness.
6. The trade-off nobody mentions.
1. Restricting regions limits deployment flexibility. 2. Global architectures require careful data placement. 3. Automation becomes more complex. 4. The benefit is regulatory compliance and reduced legal risk. Here is infrastructure as code provider configuration, JSON, showing how default region selection causes compliance violations. Disclaimer: always test code in a non-production environment. Here is the code snippet defining a default deployment region. Without enforcement, this allows workloads to be created outside approved jurisdictions. This code block shows that region selection is a control plane decision encoded at the provider level, affecting all downstream resources.
Follow-up 1. Senior level. How do you enforce region compliance consistently?
Answer: I enforce region constraints through policy as code and guardrails that block non-compliant deployments. In interviews, the key is to show that compliance rules are executable, not advisory.
Follow-up curveball. What if global availability is required?
Answer: then data classification must drive placement. In interviews, the correct response is to say that not all data belongs everywhere, even if the application does.
8. Pro insider tip.
Many compliance breaches happen silently through defaults. In interviews, saying region is a security control signals real-world cloud governance experience.
Category 2 wrap-up. Cloud configuration and control plane failures.
Every incident in this category demonstrated the same uncomfortable truth. The cloud did exactly what it was configured to do. No exploits were required. No defenses were bypassed. Security failed because configuration decisions quietly became attack surfaces at scale.
Transition from cloud configuration to software supply chain failures.
So far, breaches originated from misconfigured environments we controlled directly. Next, we move into a more dangerous domain: failures caused by code we trusted but did not write. This is where modern security incidents increasingly begin.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs. cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving. Interview questions and answers where almost 80% of the people are failing to answer. System design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 3. Software Supply Chain Incidents.
Software supply chain attacks do not exploit vulnerabilities in your code. They exploit trust. Build systems, dependencies, and automation pipelines become the delivery mechanism. By the time malicious code runs, it is already inside the perimeter.
Why supply chain incidents are so hard to detect?
Supply chain failures rarely trigger security alerts because everything looks legitimate. Builds succeed, tests pass, and artifacts are signed. The compromise happens upstream, long before runtime defenses ever see the code.
Category 3. Software Supply Chain Incidents we will cover.
In this category, we will analyze the following real-world failure modes. 21. Compromised open-source dependencies. 22. Typo-squatting attacks in package registries. 23. Malicious CI/CD pipeline injection. 24. Build artifact poisoning. 25. Dependency confusion attacks. 26. Compromised container-based images. 27. Secrets exposed through build logs. 28. Compromised GitHub actions and CI plugins. 29. Unsigned artifacts deployed to production. 30. Stolen artifact signing keys. In supply chain security, trust is the vulnerability.
Real-world cybersecurity incident number 21. Compromised open-source dependencies.
A production breach originated from a third-party library that was included during a routine dependency upgrade. No internal code was compromised, and no CI/CD systems were breached directly. The malicious code entered through a trusted dependency.
1. The setup. Everything looks secure.
The organization relied on widely used open-source libraries and managed dependencies through an automated CI/CD pipeline. Dependency updates were automated, builds were reproducible, and no warnings were raised during installation.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that no vulnerable versions were flagged by scanners. CI pipelines ran in isolated environments, and no secrets were exposed. Dependency versions were locked and tracked in source control.
3. The breach. What failed anyway?
A popular dependency was updated with malicious code by a compromised maintainer account. The new version was pulled automatically during a routine build and deployed into production without triggering any security alerts.
4. Where controls broke. Diagnosis.
Security controls focused on vulnerabilities, not trust. The pipeline verified version numbers and checksums, but did not verify provenance, maintainer integrity, or behavioral changes introduced by the dependency.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Dependency security is a trust problem, not a vulnerability problem. 2. Automated updates amplify upstream compromise. 3. Version pinning does not protect against malicious releases. 4. Pipelines must validate provenance, not just integrity. 5. Every dependency expands the attack surface.
6. The trade-off nobody mentions.
1. Stricter dependency controls slow development velocity. 2. Manual review of updates increases engineering effort. 3. Build pipelines become more complex. 4. The benefit is preventing malicious code from entering production silently. Here is CI/CD pipeline YAML showing how Unverified dependency installation allows compromised packages into production builds. Disclaimer: always test code in a non-production environment. Here is the code snippet automatically installing dependencies from the public registry. Any compromised package version is trusted and executed during the build. This code block shows dependency installation occurring without provenance verification, allowing malicious upstream code to enter the pipeline silently.
Follow-up 1. Senior level. How do you reduce supply chain risk without blocking development?
Answer: I introduce provenance verification, restrict automated updates for critical dependencies, and require review for major version changes. The goal is to slow trust, not stop development.
Follow-up curveball. What if teams resist added pipeline checks?
Answer: then the risk must be explicitly accepted. In interviews, the correct response is to state that supply chain attacks exploit speed and automation, and security must slow trust intentionally.
8. Pro insider tip.
Most supply chain breaches happen during routine upgrades. In interviews, saying, "We treat dependency updates as untrusted code changes," signals real-world software supply chain experience.
Real-world cybersecurity incident. Number 22. Type squatting in package registries.
A production system executed malicious code during a routine build without any repository compromise or pipeline breach. The incident originated from a misspelled dependency name that resolved to an attacker-controlled package. The build completed successfully and deployed as normal.
1. The setup. Everything looks secure.
The organization used automated CI/CD pipelines to install dependencies from a public package registry. Dependency installation was scripted, builds were reproducible, and no manual steps were involved.
2. What passed audits? Security incidents that passed every audit.
Audits verified that dependency installation occurred in isolated build environments. No secrets were hard-coded, and builds used approved registries. No known vulnerable packages were detected by scanners.
3. The breach. What failed anyway?
A developer introduced a dependency with a subtle typo in its name. The package manager resolved the name to a different, attacker-controlled package. During installation, the malicious package executed code in the build environment.
4. Where controls broke. Diagnosis.
The pipeline trusted package names implicitly and did not validate expected publishers or namespaces. Security controls assumed correctness of dependency names and focused on version risk instead of identity risk.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Package managers resolve names, not intent. 2. A single character typo can redirect trust. 3. Dependency identity matters more than version. 4. Automated builds amplify human mistakes. 5. Supply chain security must validate publishers.
6. The trade-off nobody mentions.
1. Restricting registries reduces dependency flexibility. 2. Publisher allow lists require maintenance. 3. Developer experience becomes stricter. 4. The benefit is prevention of silent malicious installs. Here is CI/CD pipeline YAML showing how a misspelled dependency name resolves to an attacker-controlled package. Disclaimer: always test code in a non-production environment. Here is the code snippet installing a dependency with a subtle typo. The package manager resolves this to a different package controlled by an attacker. This code block shows the install step executing without publisher or namespace validation, allowing malicious packages to run during the build.
Follow-up 1. Senior level. How do you prevent type squatting at scale?
Answer: I restrict builds to approved registries, enforce publisher allow lists, and use dependency proxies. In interviews, the key is to show that name trust must be constrained explicitly.
Follow-up curveball. What if teams rely heavily on open registries?
Answer: then dependency usage must be monitored and reviewed continuously. In interviews, the correct response is to acknowledge the trade-off and show compensating controls around trust validation.
8. Pro insider tip.
Type squatting succeeds because humans type faster than they verify. In interviews, saying, "We treat dependency names as untrusted input," signals real-world supply chain security experience.
Real-world cybersecurity incident. Number 23. Malicious CI/CD pipeline injection.
Production credentials were exfiltrated during a routine build without compromising source code repositories or production systems. The attacker injected a malicious step into the CI/CD pipeline configuration. The build succeeded and deployed as expected.
1. The setup. Everything looks secure.
The organization used a centralized CI/CD platform with protected branches, required code reviews, and restricted production access. Pipelines were defined as code and stored alongside application repositories.
2. What passed audits? Security incidents that passed every audit.
Audits verified branch protections, mandatory reviews for application code, and secret storage in the CI/CD platform. No unauthorized commits were detected in the main branch.
3. The breach. What failed anyway?
An attacker modified the pipeline configuration in a less protected branch that still triggered builds. A malicious step was added to exfiltrate environment variables during execution. Because the pipeline ran with trusted permissions, secrets were exposed.
4. Where controls broke. Diagnosis.
Security controls focused on application code, but treated pipeline code as lower risk. The CI/CD system executed pipeline definitions with high privilege regardless of branch trust level.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Pipeline code is production code with elevated privileges. 2. CI/CD systems execute configuration, not intent. 3. Branch protections must apply to pipelines, not just source code. 4. Any injected step inherits the pipeline's trust. 5. Supply chain attacks often start in automation layers.
6. The trade-off nobody mentions.
1. Restricting pipeline changes slows iteration. 2. Teams must align branch policies across code and pipelines. 3. Debugging CI failures becomes more controlled. 4. The benefit is preventing credential exfiltration during builds. Here is CI/CD pipeline YAML showing how injected build steps execute with trusted secrets. Disclaimer: always test code in a non-production environment. Here is the code snippet exfiltrating environment variables. This step executes with full access to pipeline secrets. This code block shows a seemingly harmless step added to the pipeline. Because it runs inside CI, it inherits trusted credentials.
Follow-up 1. Senior level. How do you protect pipelines without blocking developers?
Answer: I apply the same review and protection rules to pipeline code as application code and restrict secret access by branch and context. Pipelines are treated as privileged infrastructure.
Follow-up curveball. What if teams want dynamic pipeline changes?
Answer: then changes must be scoped and reviewed. In interviews, the correct response is to state that dynamic pipelines increase flexibility but require stronger guardrails.
8. Pro insider tip.
Most CI breaches do not compromise code, they compromise automation. In interviews, saying pipeline code runs with production trust signals real-world supply chain security experience.
Real-world cybersecurity incident number 24. Build artifact poisoning.
Malicious code was deployed to production even though source code repositories and CI pipelines showed no unauthorized changes. The compromise occurred because a previously built artifact was replaced in the artifact repository. The deployment system trusted the artifact implicitly.
1. The setup. Everything looks secure.
The organization used CI/CD pipelines to build artifacts and stored them in a centralized artifact repository. Deployments pulled pre-built artifacts by version and promoted them across environments.
2. What passed audits? Security incidents that passed every audit.
Audits verified that source code repositories were protected, build pipelines were isolated, and deployments referenced approved artifact versions. No unauthorized commits or pipeline changes were detected.
3. The breach. What failed anyway?
An attacker replaced a trusted build artifact in the repository with a malicious version using valid repository credentials. When the artifact was deployed, the poisoned binary was executed in production.
4. Where controls broke. Diagnosis.
The deployment process trusted artifact identity based on name and version only. There was no integrity or immutability enforcement to prevent replacement of existing artifacts.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Artifacts are executables, not files. 2. Artifact repositories are production attack surfaces. 3. Version numbers do not guarantee integrity. 4. Immutability is a security control, not an optimization. 5. Build provenance must be enforced end-to-end.
6. The trade-off nobody mentions.
1. Immutable repositories limit rollback flexibility. 2. Storage usage increases due to non-reusable artifacts. 3. Cleanup and retention policies become critical. 4. The benefit is preventing silent artifact replacement. Here is CI/CD pipeline YAML showing how deployments trust artifacts by name and version, without integrity enforcement. Disclaimer: always test code in a non-production environment. Here is the code snippet deploying an artifact by name and version only. If the artifact is replaced, the pipeline cannot detect the change. This code block shows deployment occurring without checksum or signature verification, allowing poisoned artifacts into production.
Follow-up 1. Senior level. How do you prevent artifact poisoning?
Answer: I enforce immutable artifact repositories and require cryptographic signing and verification during deployment. Artifacts cannot be overwritten once published.
Follow-up curveball. What if teams want to re-upload fixed artifacts?
Answer: then a new version must be created. In interviews, the correct response is to state that overriding artifacts destroys trust and traceability.
8. Pro insider tip.
If artifacts are mutable, production is mutable. In interviews, saying artifact immutability is a security boundary signals real-world supply chain security experience.
Real-world cybersecurity incident number 25. Dependency confusion attacks.
Malicious code was executed during a build without compromising internal repositories or CI/CD systems. The attacker exploited the package resolution order, causing the build system to download a public package instead of the intended internal dependency. The pipeline behaved exactly as configured.
1. The setup. Everything looks secure.
The organization hosted private packages internally and used public registries for open-source dependencies. CI/CD pipelines were configured to resolve dependencies automatically using default package manager behavior.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed access controls on private registries, verified that no credentials were leaked, and reviewed CI/CD configurations. No unauthorized access to internal repositories was detected.
3. The breach. What failed anyway?
An attacker published a malicious package to a public registry using the same name as an internal dependency, but with a higher version number. During the build, the package manager resolved and downloaded the public package instead of the internal one.
4. Where controls broke. Diagnosis.
The build system trusted version precedence over source authenticity. Dependency resolution favored the highest version number without enforcing registry boundaries or namespace ownership.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Package managers resolve versions, not trust. 2. Public registries can impersonate internal packages by name. 3. Version precedence is a supply chain attack vector. 4. Registry boundaries must be enforced explicitly. 5. Internal dependencies should never resolve externally.
6. The trade-off nobody mentions.
1. Strict registry separation reduces flexibility. 2. Build configuration becomes more complex. 3. Teams must manage scoped namespaces carefully. 4. The benefit is eliminating dependency impersonation. Here is CI/CD pipeline YAML showing how default dependency resolution allows public packages to override internal ones. Disclaimer: always test code in a non-production environment. Here is the code snippet installing a dependency by name only. The package manager may resolve this from a public registry if version precedence is higher. This code block shows dependency installation occurring without enforcing registry boundaries, allowing dependency confusion attacks.
Follow-up 1. Senior level. How do you prevent dependency confusion?
Answer: I enforce private registry scoping, require explicit index URLs, and block public resolution for internal package names. In interviews, the key is to show that dependency source must be constrained, not inferred.
Follow-up, curveball. What if teams rely on both public and private packages?
Answer, then package resolution rules must be explicit. In interviews, the correct response is to say that ambiguity in dependency sourcing is an unacceptable risk.
8. Pro Insider Tip.
Dependency confusion exploits defaults, not vulnerabilities. In interviews, saying, "We treat package resolution order as a security boundary," signals real-world supply chain expertise.
Real-world cybersecurity incident number 26. Compromised container base images.
Malicious code was introduced into production containers without modifying application source code or CI/CD pipelines. The compromise originated from a trusted container base image that was later discovered to include backdoored components. All builds and deployments completed successfully.
1. The setup. Everything looks secure.
The organization built application containers using official-looking base images from a public registry. Images were referenced by tag for convenience, and builds were automated through CI/CD pipelines.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that Docker files were reviewed, no secrets were embedded, and images were scanned for known vulnerabilities. The base image was widely used and showed no critical CVEs at the time.
3. The breach. What failed anyway?
The base image maintainer account was compromised, and a new image version was pushed with malicious startup logic. Because the image tag remained the same, builds pulled the poisoned image automatically.
4. Where controls broke. Diagnosis.
Security controls trusted image tags and vulnerability scans. There was no verification of image provenance, immutability, or digest pinning. The pipeline assumed base images were inherently trustworthy.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Container images are software dependencies. 2. Image tags are mutable references, not guarantees. 3. Vulnerability scans do not detect malicious intent. 4. Provenance matters more than popularity. 5. Base images must be pinned and verified.
6. The trade-off nobody mentions.
1. Digest pinning reduces update convenience. 2. Image rotation requires more coordination. 3. Build configurations become stricter. 4. The benefit is preventing silent image replacement. Here is CI/CD pipeline YAML showing how mutable image tags allow compromised base images into builds. Disclaimer: always test code in a non-production environment. Here is the code snippet building an image that implicitly pulls a base image by tag. If the tag is poisoned, the build inherits malicious code. This code block shows image builds occurring without digest pinning or provenance verification, allowing compromised base images into production.
Follow-up 1. Senior level. How do you secure base images without slowing teams?
Answer: I enforce digest pinning, maintain an internal base image registry, and rotate images on a controlled schedule. In interviews, the key is to show that image trust must be explicit.
Follow-up, curveball. What if teams insist on using public images directly?
Answer: then those images must be mirrored, scanned, pinned, and approved internally. In interviews, the correct response is to state that direct trust of public images is an unacceptable supply chain risk.
8. Pro Insider Tip.
Most container compromises enter through base images, not application code. In interviews, saying image tags are not immutable trust anchors signals real-world container security experience.
Real-world cybersecurity incident number 27. Secrets embedded in build logs.
Sensitive credentials were leaked without any repository breach or pipeline compromise. The exposure occurred because secrets were printed to build logs during normal execution. The logs were retained, searchable, and accessible to users who did not have access to the underlying secrets.
1. The setup. Everything looks secure.
The organization used a centralized CI/CD system, with secrets stored securely in the platform's secret manager. Pipelines reference secrets through environment variables and masked values in standard output where possible.
2. What passed audits? security incidents that passed every audit.
Audits verified that secrets were not committed to source control, access to the secret manager was restricted, and CI/CD pipelines used approved secret injection mechanisms.
3. The breach, what failed anyway.
During a build failure, debug output printed full environment variables to logs. The CI/CD platform did not mask dynamically generated secrets. Anyone with access to build logs could retrieve valid production credentials.
4. Where controls broke, diagnosis.
Security controls protected secret storage, but not secret exposure during execution. Logging behavior was treated as benign, and log access was broader than secret access.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Secrets are vulnerable at runtime, not just at rest. 2. Logs are a data exfiltration channel. 3. Masking static secrets is insufficient. 4. Debug output must be treated as sensitive. 5. Log access should never exceed secret access.
6. The trade-off nobody mentions.
1. Restricting logs complicates debugging. 2. Developers lose visibility during failures. 3. Additional tooling is required for secure diagnostics. 4. The benefit is preventing silent credential leakage. Here is CI/CD pipeline YAML showing how debug logging exposes secrets stored securely elsewhere. Disclaimer: always test code in a non-production environment. Here is the code snippet printing all environment variables. This exposes secrets injected at runtime into the build environment. This code block shows a debugging step that bypasses secret masking controls by dumping runtime state directly to logs.
Follow-up 1. Senior level. How do you debug pipelines without exposing secrets?
Answer: I restrict debug output, redact environment variables by default, and provide controlled diagnostic tooling. In interviews, the key is to show that observability must be security aware.
Follow-up curveball. What if teams insist on verbose logs?
Answer: then log access must be tightly restricted and retention minimized. In interviews, the correct response is to say that verbose logs increase breach impact.
8. Pro insider tip.
Many secrets leak through logs, not repositories. In interviews, saying logs are a credential surface signals real-world CI/CD security experience.
Real-world cybersecurity incident number 28. Compromised GitHub actions.
Production credentials were exposed during a trusted CI run without any changes to application code or pipeline logic. The breach occurred because a third-party GitHub action was compromised upstream. The workflow executed exactly as defined.
1. The setup. Everything looks secure.
The organization relied on GitHub actions for CI/CD automation and reused popular third-party actions to speed up workflows. Actions were referenced by version tags and executed with access to repository secrets.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed branch protections, reviewed workflow files, and verified that secrets were stored securely in GitHub. No unauthorized workflow changes were detected.
3. The breach. What failed anyway?
A maintainer of a widely used GitHub action was compromised and pushed malicious logic to the referenced version tag. During the next CI run, the action executed and exfiltrated secrets from the workflow environment.
4. Where controls broke, diagnosis.
The workflow trusted action version tags as immutable and did not pin to specific commit SHAs. Security controls validated workflow files, but not the integrity of referenced actions.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. GitHub actions are executable code from external sources. 2. Version tags are mutable trust anchors. 3. Workflow security depends on action integrity. 4. Pinning actions is a supply chain control. 5. CI secrets inherit the trust of every action executed.
6. The trade-off nobody mentions.
1. Pinning actions reduces update convenience. 2. Action upgrades require manual review. 3. Workflow maintenance overhead increases. 4. The benefit is preventing upstream action compromise. Here is GitHub Actions workflow YAML, showing how unpinned actions execute with access to CI secrets. Disclaimer: Always test code in a non-production environment. Here is the code snippet referencing an action by version tag. If the tag is updated maliciously, the workflow executes the compromised code. This code block shows a trusted workflow step, inheriting full CI context and secrets through an external action.
Follow-up 1, Senior Level. How do you secure GitHub Actions at scale?
Answer: I pin actions to commit SHAs, restrict allowed actions, and limit secret exposure by job. In interviews, the key is to show that action trust must be explicit and verifiable.
Follow-up Curveball. What if teams want automatic action updates?
Answer: then updates must be reviewed and rolled out deliberately. In interviews, the correct response is to state that automatic trust updates create supply chain risk.
8, Pro Insider Tip.
Most CI breaches come from trusted automation, not attackers writing new code. In interviews, saying, "Every GitHub action is a third-party executable," signals real-world CICD security maturity.
Real-world cybersecurity incident number 29. Unsigned artifacts deployed to production.
Malicious code reached production, even though build pipelines and repositories showed no unauthorized changes. The deployment system accepted artifacts without cryptographic signatures. As a result, there was no way to verify whether the artifact originated from a trusted build.
1. The setup. Everything looks secure.
The organization used automated CI/CD pipelines to build and deploy artifacts. Artifact repositories enforced access controls, and deployments referenced approved artifact versions.
2. What passed audits? Security incidents that passed every audit.
Audits verified repository permissions, build isolation, and pipeline approvals. There were no checks for artifact signing or signature verification during deployment.
3. The breach. What failed anyway?
An attacker uploaded a modified artifact to the repository using valid credentials. Because the artifact was not signed, the deployment system could not distinguish it from a legitimate build output.
4. Where controls broke. Diagnosis.
Artifact trust was inferred from location and naming rather than cryptographic proof. The deployment pipeline assumed that repository access equaled artifact integrity.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Unsigned artifacts are untrusted by definition. 2. Repositories store files, not trust guarantees. 3. Deployment systems must verify provenance. 4. Signing enforces a chain of custody. 5. Trust must be cryptographically enforced.
6. The trade-off nobody mentions.
1. Artifact signing adds operational overhead. 2. Key management becomes a critical dependency. 3. Build pipelines grow more complex. 4. The benefit is verifiable artifact provenance. Here is CI/CD pipeline YAML, showing how deployments proceed without verifying artifact signatures. Disclaimer: always test code in a non-production environment. Here is the code snippet deploying an artifact without signature verification. Any modified file with the same name is accepted. This code block shows deployment occurring without cryptographic validation, allowing untrusted artifacts into production.
Follow-up 1. Senior Level. How do you enforce artifact trust?
Answer: I require all artifacts to be signed during build and verified during deployment. In interviews, the key is to show that trust must be enforced at every stage.
Follow-up Curveball. What if signing slows deployments?
Answer: then the trade-off must be explicit. In interviews, the correct response is to say that unsigned deployments optimize speed at the cost of trust.
8. Pro Insider Tip.
If artifacts are not signed, provenance is assumed, not proven. In interviews, saying unsigned artifacts are untrusted artifacts signals real-world supply chain security maturity.
Real-world cybersecurity incident number 30. Stolen artifact signing keys.
Malicious software was deployed to production using perfectly valid artifact signatures. No pipelines were compromised, no policies were bypassed, and no alerts were triggered. The attacker signed malicious artifacts using stolen signing keys that were fully trusted by the deployment system.
1. The setup. Everything looks secure.
The organization enforced artifact signing and signature verification across all environments. Deployment systems rejected unsigned artifacts, and signing keys were treated as high-value assets.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that artifacts were signed, signature verification was enabled, and no unsigned code reached production. Key existence and usage were documented.
3. The breach. What failed anyway?
A signing key was stolen from a compromised build environment backup. Using the stolen key, the attacker signed malicious artifacts that passed all verification checks and were deployed normally.
4. Where controls broke. Diagnosis.
Security controls verified signatures but did not protect signing keys adequately. Key storage, access, rotation, and monitoring were insufficient for the level of trust assigned to the keys.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Signing is only as strong as key protection. 2. A stolen key invalidates all trust guarantees. 3. Keys are production credentials, not configuration. 4. Key compromise is equivalent to pipeline compromise. 5. Trust must be revocable, not permanent.
6. The trade-off nobody mentions.
1. Hardware-backed key storage increases cost. 2. Key rotation adds operational complexity. 3. Build pipelines require tighter controls. 4. The benefit is preventing trusted malicious deployments.
Follow-up 1. Senior level. How do you protect signing keys properly?
Answer: I store keys in hardware-backed key management systems, restrict usage through short-lived access, monitor all signing operations, and rotate keys regularly. In interviews, the key is to treat signing keys as production secrets.
Follow-up curveball. What if revoking a key disrupts production?
Answer: then the system is overcoupled to a single trust anchor. In interviews, the correct response is to say that trust must be designed for revocation, not permanence.
8. Pro insider tip.
Many supply chain breaches succeed even with signing in place. In interviews, saying protecting signing keys matters more than signing itself signals real-world supply chain security leadership.
Category 3 wrap-up. Software supply chain incidents.
Every incident in this category demonstrated the same systemic weakness. Trust was granted upstream and consumed downstream without verification. The failures were not technical bugs, but architectural assumptions that trusted automation, dependencies, and artifacts implicitly.
Transition from supply chain failures to data exposure and privacy breaches.
So far, the damage entered through software we executed. Next, we examine incidents where systems behaved correctly but revealed too much. These failures do not require attackers to break in. They occur when sensitive data is exposed through normal operation.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 4. Data exposure and privacy incidents.
Data exposure incidents are among the most damaging because they are silent. Systems remain available, logs look healthy, and no alarms fire. The breach is often discovered months later through downstream misuse, regulatory inquiries, or external reporting.
Why data exposure is harder than traditional breaches.
Encryption, authentication, and access controls can all function correctly, while sensitive data is still mishandled. Privacy failures usually originate from excessive visibility, overcollection, or careless handling inside trusted systems.
Category 4. Data exposure and privacy incidents we will cover.
In this category, we will analyze the following real-world failure modes. 31. Personally identifiable information leaked via application logs. 32. Debug endpoints exposing sensitive data. 33. Analytics tools collecting unintended private data. 34. Overbroad data replication across environments. 35. Exposed backup snapshots containing sensitive records. 36. Inference attacks on anonymized datasets. 37. Improper data masking in non-production environments. 38. GDPR and regulatory scope violations. 39. Excessive data retention beyond policy. 40. Internal dashboards leaking sensitive business data. Most privacy breaches occur in places engineers stop looking.
Real-world cybersecurity incident number 31. PII leaked via application logs.
Sensitive customer data was exposed without any system compromise or unauthorized access. The application logged full request and response objects for troubleshooting. Those logs were aggregated, retained, and accessible to users who did not have permission to view personal data.
1. The setup. Everything looks secure.
The application enforced authentication, role-based access control, and encryption at rest and in transit. Logging was centralized for observability, and log access was granted to engineering and operations teams.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed encryption, access controls, and that no sensitive fields were exposed through APIs. Logging was reviewed only for availability and performance, not data sensitivity.
3. The breach. What failed anyway.
Application logs captured full request payloads containing names, email addresses, and identification numbers. These logs were indexed and searchable, allowing unauthorized internal access to sensitive data without triggering security alerts.
4. Where controls broke. Diagnosis.
Security controls protected data at rest and in transit, but failed to protect data in motion within the application. Logging was treated as harmless telemetry rather than a data exfiltration surface.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Logs are data stores, not diagnostics. 2. Anything written to logs must be considered exposed. 3. PII should never appear in application logs. 4. Observability must respect data classification. 5. Log access often exceeds data access.
6. The trade-off nobody mentions.
1. Reduced logging makes debugging harder. 2. Engineers lose full request visibility. 3. Additional tooling is needed for safe diagnostics. 4. The benefit is preventing silent privacy violations. Here is Java logging logic showing how logging full request objects silently exposes PII. Disclaimer: always test code in a non-production environment. Here is the code snippet logging the entire request object. If the object contains PII, it is permanently written to logs. This code block shows logging occurring at the application boundary, where sensitive user data is most likely to be present.
Follow-up 1. Senior level. How do you balance observability with privacy?
Answer: I log identifiers, not payloads, and use structured logging with explicit allow lists. In interviews, the key is to show that observability must be privacy-aware by design.
Follow-up. Curveball. What if logs are required for compliance investigations?
Answer: then logs must be redacted, access controlled, and retained minimally. In interviews, the correct response is to state that compliance does not justify unnecessary data exposure.
8. Pro insider tip.
Many data breaches never leave the organization. They leak internally through logs. In interviews, saying logs are a privacy boundary signals real-world data protection experience.
Real-world cybersecurity incident number 32. Debug endpoints exposing sensitive data.
Sensitive internal data was accessed without exploiting authentication, authorization, or infrastructure controls. The exposure occurred through a debug endpoint that was never intended for production use, but remained accessible after deployment.
1. The setup. Everything looks secure.
The application enforced authentication and role-based access for all customer-facing APIs. Debug tooling was added during development to accelerate troubleshooting and was assumed to be unreachable in production.
2. What passed audits. Security incidents that passed every audit.
Audits verified authentication on primary APIs, reviewed role permissions, and confirmed that no administrative credentials were exposed. Debug endpoints were not included in the audit scope.
3. The breach. What failed anyway.
An unauthenticated debug endpoint exposed internal application state, configuration values, and cache data structures. The endpoint returned sensitive information without triggering any access control checks.
4. Where controls broke. Diagnosis.
Security controls were applied selectively to business APIs, but not to operational endpoints. Debug functionality was treated as non-production code, despite running in production environments.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Debug endpoints are production code once deployed. 2. Security boundaries must apply uniformly. 3. Operational visibility should not bypass authorization. 4. Assumed inaccessibility is not a control. 5. Debug tooling must be explicitly disabled or secured.
6. The trade-off nobody mentions.
1. Removing debug endpoints slows troubleshooting. 2. Engineers lose quick visibility into runtime state. 3. Additional tooling is required for safe diagnostics. 4. The benefit is preventing accidental data exposure. Here is Java controller logic showing how an unprotected debug endpoint exposes internal application state. Disclaimer: always test code in a non-production environment. Here is the code snippet exposing a debug endpoint. Without access controls, this endpoint is reachable by anyone who can reach the service. This code block returns internal application state directly, which may include sensitive data and configuration.
Follow-up 1. Senior level. How do you keep debug capability without exposure?
Answer: I restrict debug endpoints behind strong authentication, network isolation, or remove them entirely in production. In interviews, the key is to show that operational tooling must be production hardened.
Follow-up curveball. What if teams rely heavily on debug endpoints?
Answer: then the architecture is compensating for missing observability. In interviews, the correct response is to state that proper monitoring should replace ad hoc debug access.
8. Pro insider tip.
If a debug endpoint exists in production, assume it will be found. In interviews, saying debug code is production code signals real-world application security maturity.
Real-world cybersecurity incident number 33. Analytics tools collecting unintended private data.
Sensitive user data was exfiltrated through an approved analytics platform without any breach of the application or infrastructure. The application intentionally sent events to an analytics service, but those events included far more data than intended, including personal and sensitive attributes.
1. The setup. Everything looks secure.
The application used a popular third-party analytics SDK to track user behavior and improve product decisions. Events were sent over HTTPS, the vendor was approved, and data processing agreements were in place.
2. What passed audits. Security incidents that passed every audit.
Audits verified vendor compliance, encryption in transit, and access controls on the analytics dashboard. The event schema itself was not reviewed for data sensitivity.
3. The breach. What failed anyway.
Front-end code sent entire user objects to the analytics service for convenience. These objects contained email addresses, internal identifiers, and metadata never intended for analytics. The data was stored, processed, and accessible through the analytics platform.
4. Where controls broke. Diagnosis.
Security controls focused on vendor trust rather than data minimization. The application treated analytics as harmless telemetry instead of an external data sink subject to privacy constraints.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Analytics pipelines are external data exports. 2. Vendor approval does not justify excessive data sharing. 3. Front-end convenience often bypasses privacy intent. 4. Event schemas must be explicitly designed for minimization. 5. Privacy failures often originate in client-side code.
6. The trade-off nobody mentions.
1. Strict event schemas slow feature experimentation. 2. Product teams lose ad hoc visibility into user behavior. 3. Engineering effort increases to maintain schemas. 4. The benefit is preventing silent third-party data leakage. Here is JavaScript analytics logic showing how sending full user objects leaks private data to third-party platforms. Disclaimer: always test code in a non-production environment. Here is the code snippet sending an analytics event. Everything included in the payload is exported outside the application boundary. This code block passes the full user object, which may contain emails, identifiers, and internal metadata never intended for analytics.
Follow-up 1. Senior level. How do you prevent analytics from becoming a data leak?
Answer: I enforce strict event schemas with explicit allow lists and block arbitrary object serialization. Analytics events are reviewed like APIs, with clear contracts and ownership. In interviews, the key signal is treating analytics as regulated data flows, not debugging tools.
Follow-up 2. Staff level. Why isn't vendor compliance enough here?
Answer: vendor compliance only governs how data is handled after receipt, not whether the data should be sent at all. The responsibility for minimization lies entirely with the application. In interviews, emphasizing outbound data control shows real privacy engineering maturity.
Follow-up curveball. What if product teams demand richer analytics?
Answer: then the trade-off must be explicit and documented. I work with product to define purpose-limited events and anonymization strategies. In interviews, the correct response is to frame analytics scope as a business risk decision, not a technical shortcut.
8. Pro insider tip.
Most analytics leaks happen because front-end developers optimize for speed, not privacy. In interviews, saying analytics is an external data export signals hands-on experience with real privacy failures.
Real-world cybersecurity incident number 34. Overbroad data replication across environments.
Sensitive production data was exposed without any system compromise, credential theft, or misconfigured access controls. The exposure occurred because production datasets were replicated wholesale into non-production environments for convenience. Those environments had significantly weaker security controls.
1. The setup. Everything looks secure.
The organization used infrastructure as code to manage databases and replication across environments. Production data was replicated into staging and development to support testing, analytics, and troubleshooting workflows.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed encryption at rest, access controls in production, and restricted network boundaries. Non-production environments were out of scope for most security reviews and compliance checks.
3. The breach. What failed anyway?
A developer account with access to a development environment retrieved full copies of production customer data. The access was authorized for the environment, but the data should never have existed there in the first place.
4. Where controls broke. Diagnosis.
Security controls assume that environment separation equaled data separation. Infrastructure automation replicated data without enforcing sensitivity boundaries, effectively expanding the production data perimeter.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Environment isolation does not imply data isolation. 2. Replication pipelines are data exfiltration paths. 3. Non-production environments rarely match production security posture. 4. Data sensitivity must be enforced independently of environment. 5. Replication should be selective, not wholesale.
6. The trade-off nobody mentions.
1. Synthetic or masked datasets reduce debugging fidelity. 2. Selective replication increases operational complexity. 3. Engineering teams lose convenient access to real data. 4. The benefit is drastically reduced privacy and compliance risk. Here is Terraform configuration, showing how unrestricted replication copies production data into non-production environments. Disclaimer: always test code in a non-production environment. Here is the code snippet configuring full data replication. This instructs the system to copy all records, regardless of sensitivity or environment. This code block shows production data being explicitly replicated into a development environment with weaker security controls.
Follow-up 1, senior level. How do you allow testing without exposing real data?
Answer: I use masked or synthetic datasets and restrict real data access to controlled, audited workflows. Replication rules enforce column-level filtering based on data classification. In interviews, the key signal is separating data needs from convenience.
Follow-up 2, staff level. Why not rely on access controls in non-production?
Answer: because non-production environments rarely receive the same scrutiny or monitoring as production. Even perfect access control cannot justify placing sensitive data where it does not belong. In interviews, emphasizing data minimization over access control shows maturity.
Follow-up, curveball. What if engineers insist they need real data to debug?
Answer: then that access must be exceptional, time-bound, and audited. I frame real data usage as an operational incident, not a default workflow. In interviews, the correct response is to treat production data access as a high-risk event.
8, pro insider tip.
Most privacy breaches happen because production data travels farther than security controls. In interviews, saying data should not move just because infrastructure makes it easy signals real-world data governance experience.
Real-world cybersecurity incident number 35. Exposed backup snapshots containing sensitive data.
Sensitive customer data was accessed without breaching production systems, credentials, or application logic. The exposure occurred because database backup snapshots were created correctly but stored in a location that was publicly accessible. The backups contained full production datasets.
1. The setup. Everything looks secure.
The organization used automated backups for all production databases. Infrastructure as code defined snapshot creation, retention policies, and storage locations. Backups were considered operational artifacts rather than security-sensitive assets.
2. What passed audits? Security incidents that passed every audit.
Audits verified encryption on production databases, restricted database access, and regular backup creation. Backup storage permissions were not reviewed as part of data exposure or privacy assessments.
3. The breach. What failed anyway?
An attacker discovered publicly accessible backup snapshots containing full database exports. Because the backups were stored outside the primary database systems, no database access controls or monitoring were triggered.
4. Where controls broke. Diagnosis.
Security controls protected live databases, but not derived data. Backup artifacts were treated as operational outputs instead of high-risk data stores requiring the same protections as production systems.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Backups are full copies of production data. 2. Derived data inherits the sensitivity of its source. 3. Storage misconfiguration is a data exposure vector. 4. Backup locations must be treated as production systems. 5. Encryption alone does not prevent exposure.
6. The trade-off nobody mentions.
1. Restricting backup access complicates recovery workflows. 2. Operational teams lose convenient snapshot access. 3. Recovery processes require tighter coordination. 4. The benefit is preventing silent bulk data leaks. Here is Terraform configuration, showing how publicly accessible storage exposes database backup snapshots. Disclaimer: always test code in a non-production environment. Here is the code snippet explicitly making the backup bucket publicly readable. This allows anyone to download sensitive backup data. This code block shows production database backups being stored in a publicly accessible location without additional access controls.
Follow-up 1, senior level. How do you secure backups without harming recovery time?
Answer: I restrict backup access to dedicated recovery roles enforce private storage, and audit every restore operation. Recovery workflows are documented and tested so security controls do not delay incidents. In interviews, the key signal is treating backups as production data.
Follow-up 2, staff level. Why isn't encryption enough to protect backups?
Answer: encryption protects data at rest, not against unauthorized access to decrypted copies. If attackers can download backups and keys are accessible, encryption provides little protection. In interviews, emphasizing access control over encryption shows depth.
Follow-up, curveball. What if teams need quick access to snapshots for debugging?
Answer: then access must be temporary, audited, and purpose-limited. I frame snapshot access as a controlled operational event, not a default capability. In interviews, the correct response is to treat backup access as high risk.
8, pro insider tip.
Most massive data leaks come from backups, not live systems. In interviews, saying backups are production data in disguise signals real-world incident experience.
Real-world cybersecurity incident number 36. Inference attacks on anonymized data.
Sensitive individual information was reconstructed without accessing any raw personal data. The organization shared anonymized datasets for analytics and research purposes. No direct identifiers were present, yet individuals could be inferred through correlation and external data sources.
1. The setup. Everything looks secure.
The organization removed names, emails, and identifiers from datasets before sharing them internally and with partners. Data anonymization techniques followed documented best practices, and no single record contained obvious personal identifiers.
2. What passed audits? Security incidents that passed every audit.
Audits verified that datasets were anonymized, direct identifiers were removed, and access to raw production data was restricted. The anonymized datasets were classified as low risk.
3. The breach. What failed anyway?
By combining anonymized records with external datasets, attackers inferred sensitive attributes about specific individuals. No single dataset revealed identities, but correlations across data sources reconstructed private information.
4. Where controls broke. Diagnosis.
Security controls treated anonymization as irreversible. The system failed to account for linkage attacks, background knowledge, and the growing availability of external datasets that enable re-identification.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Anonymization reduces risk but does not eliminate it. 2. Inference attacks exploit correlations, not direct access. 3. Privacy risk increases as more datasets become available. 4. Data sharing decisions must consider external context. 5. Anonymized data can still be personal data.
6. The trade-off nobody mentions.
1. Stronger anonymization reduces data utility. 2. Analytical accuracy decreases as noise increases. 3. Product insights become less granular. 4. The benefit is reducing re-identification risk.
Follow-up 1. Senior level. How do you reduce inference risk without killing analytics?
Answer: I apply techniques like aggregation, differential privacy, and query-level controls rather than raw data sharing. Access is purpose-limited and monitored continuously. In interviews, the key signal is acknowledging that privacy is probabilistic, not binary.
Follow-up 2. Staff level. Why isn't removing identifiers sufficient?
Answer: because identity can emerge from combinations of seemingly harmless attributes. Location, timestamps, and behavior patterns can uniquely identify individuals. In interviews, explaining linkage risk shows depth beyond compliance checklists.
Follow-up curveball. What if leadership insists anonymized data is safe?
Answer: then I present concrete re-identification examples and frame the risk as reputational and regulatory, not theoretical. In interviews, the correct response is to show how to communicate probabilistic risk to non-technical stakeholders.
8. Pro insider tip.
Anonymization is not a delete button for privacy risk. In interviews, saying inference risk grows over time signals real-world data protection experience.
Real-world cybersecurity incident number 37. Improper data masking in non-production environments.
Sensitive customer data was exposed to engineers and contractors without any unauthorized access to production systems. The exposure occurred because data masking was applied inconsistently when copying production data into non-production environments. Masking rules existed, but failed silently.
1. The setup, everything looks secure.
The organization replicated production data into staging and development environments to support testing. Data masking scripts were applied during replication, and access to production remained tightly controlled.
2. What passed audits? Security incidents that passed every audit.
Audits verified that production access was restricted and that masking scripts existed in source control. Non-production data quality and masking effectiveness were not validated as part of security reviews.
3. The breach, what failed anyway.
Due to a schema change, masking logic failed to apply to newly added columns. As a result, sensitive fields such as email addresses and identification numbers were copied in clear text into development databases.
4. Where controls broke, diagnosis.
Security controls assumed masking scripts would continue to function as schemas evolved. There was no verification step to ensure masking completeness, and failures did not block replication.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Masking is a control, not a transformation. 2. Schema drift breaks security assumptions silently. 3. Non-production data deserves production-level scrutiny. 4. Masking must be validated, not assumed. 5. Failures should block data movement, not warn later.
6. The trade-off nobody mentions.
1. Strict masking validation slows data refresh cycles. 2. Engineering teams lose immediate access to fresh data. 3. Automation becomes more complex to maintain. 4. The benefit is preventing uncontrolled internal exposure. Here is SQL masking logic showing how missing column coverage exposes sensitive data during replication. Disclaimer: always test code in a non-production environment. Here is the code snippet copying the email column without masking. This directly exposes personally identifiable information in non-production. This code block shows a highly sensitive field being replicated in clear text because masking logic was not applied to this column.
Follow-up 1. Senior level. How do you prevent masking failures as schemas evolve?
Answer: I enforce schema-aware masking with automated validation that fails replication if any sensitive column is unmasked. Masking rules are generated from data classification metadata, not hand-maintained scripts. In interviews, the key signal is designing masking to fail closed.
Follow-up 2. Staff level. Why isn't access control enough in non-production?
Answer: because non-production access is broader by design and rarely monitored as strictly as production. Once sensitive data exists there, exposure becomes inevitable. In interviews, emphasizing data placement over access checks shows maturity.
Follow-up, curveball. What if teams need real data for complex bugs?
Answer: then access must be temporary, audited, and purpose-bound, with data destroyed afterward. I treat real data access as an exception workflow, not a default. In interviews, the correct response is to reframe convenience as risk.
8. Pro insider tip.
Most internal data leaks happen because masking silently fails. In interviews, saying masking must be continuously validated signals real-world data governance experience.
Real-world cybersecurity incident number 38. GDPR and regulatory scope violations.
The organization faced regulatory penalties and forced data deletion without suffering a traditional breach. Systems were secure, access controls functioned correctly, and no attacker was involved. The failure occurred because data was collected, processed, and retained outside the scope of user consent and regulatory authorization.
1. The setup, everything looks secure.
The application enforced authentication, encrypted all sensitive data, and restricted access through role-based controls. Privacy policies were documented, and compliance reviews were conducted during major releases.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed technical safeguards, encryption standards, and access controls. Compliance checks focused on system security posture rather than end-to-end data lifecycle enforcement.
3. The breach, what failed anyway.
The application continued collecting and storing user data for secondary purposes that were not covered by consent. Data processing expanded incrementally over time without updating consent flows or regulatory assessments.
4. Where controls broke, diagnosis.
Security and compliance were treated as point-in-time checks. There was no continuous enforcement ensuring that data usage remained within approved regulatory and consent boundaries as features evolved.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Compliance is about data purpose, not just protection. 2. Secure systems can still violate privacy law. 3. Consent scope must evolve with system behavior. 4. Data lifecycle enforcement is continuous, not static. 5. Regulatory failures often stem from product drift.
6. The trade-off nobody mentions.
1. Strict consent enforcement slows feature experimentation. 2. Product teams must coordinate closely with legal and privacy. 3. Engineering effort increases to track data purpose. 4. The benefit is avoiding regulatory penalties and forced data deletion.
Follow-up 1. Senior level. How do you prevent scope creep in data usage?
Answer: I tie every data field to an explicit purpose and consent scope enforced in code. Any new usage requires a review and, if necessary, a consent update. In interviews, the key signal is treating consent as a runtime constraint, not a document.
Follow-up 2. Staff level. Why isn't encrypting and securing data enough for compliance?
Answer: because privacy regulations govern why data is used, not just how it is protected. Perfectly secure systems can still be non-compliant if data usage exceeds consent. In interviews, highlighting purpose limitation shows real regulatory understanding.
Follow-up curveball. What if leadership prioritizes growth over compliance?
Answer: then the risk must be explicitly accepted and documented at the executive level. I frame compliance failures as existential business risks, not technical inconveniences. In interviews, the correct response is to show how to escalate and communicate risk.
8. Pro insider tip.
Many regulatory violations are discovered long after systems ship. In interviews, saying compliance fails through product drift, not breaches, signals real-world privacy leadership.
Real-world cybersecurity incident number 39. Excessive data retention beyond policy.
Sensitive personal data was retained far longer than documented policy allowed, increasing breach impact and regulatory exposure. No attacker exploited a vulnerability. The failure occurred because infrastructure defaults retained data indefinitely, silently violating retention requirements.
1. The setup. Everything looks secure.
The organization documented data retention limits and enforced access controls. Storage systems were provisioned via infrastructure as code, and backups were enabled for reliability and recovery.
2. What passed audits? Security incidents that passed every audit.
Audits verified encryption, access restrictions, and backup success. Retention enforcement was assumed to be handled operationally and was not validated against infrastructure configuration.
3. The breach. What failed anyway?
Data that should have been deleted after policy-defined periods remained stored for years. When an internal investigation occurred, historical data far outside consent and regulatory scope was discovered.
4. Where controls broke, diagnosis.
Retention was treated as a process rather than a control. Infrastructure defaults favored durability and recovery, and no automated deletion policies were enforced at the storage layer.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Data that is not deleted becomes a liability. 2. Retention policies must be enforced in infrastructure. 3. Manual deletion does not scale or survive turnover. 4. Storage defaults optimize for durability, not compliance. 5. Deletion is a security control, not housekeeping.
6. The trade-off nobody mentions.
1. Automated deletion reduces historical analysis capability. 2. Data recovery options become more limited. 3. Retention rules require careful coordination with legal. 4. The benefit is reduced blast radius and regulatory exposure. Here is Terraform configuration, showing how missing lifecycle rules cause indefinite data retention. Disclaimer: always test code in a non-production environment. Here is the code snippet defining a storage bucket without any retention or lifecycle controls. By default, Data is retained indefinitely. This code block shows a production data store being created without enforced deletion policies, allowing data to persist beyond approved retention periods.
Follow-up 1, senior level. How do you enforce retention reliably?
Answer: I encode retention directly into infrastructure using lifecycle policies and automated deletion. Retention rules are derived from data classification and legal requirements. In interviews, the key signal is treating deletion as an architectural guarantee.
Follow-up 2, staff level. Why not rely on manual cleanup jobs?
Answer: manual processes fail under scale, staffing changes, and incident pressure. Infrastructure-enforced deletion is deterministic and auditable. In interviews, emphasizing automation over process shows maturity.
Follow-up, curveball. What if business teams want long-term historical data?
Answer: then the scope must be explicitly justified and consented, with aggregation or anonymization applied. I separate analytical retention from raw data retention. In interviews, the correct response is to frame retention as a business risk decision.
8, pro insider tip.
Most compliance failures are caused by data that should no longer exist. In interviews, saying retention is a security control signals real-world data governance experience.
Real-world cybersecurity incident number 40. Internal dashboards leaking sensitive business data.
Sensitive business and customer data was exposed without any external attack or credential theft. The exposure occurred through an internal dashboard that aggregated operational metrics and customer records. Access was granted broadly for convenience, and the data was never intended to be visible to all internal users.
1. The setup. Everything looks secure.
The organization used internal dashboards to monitor business health, support operations, and executive reporting. Authentication was required, and dashboards were deployed behind corporate network controls.
2. What passed audits? Security incidents that passed every audit.
Audits verified that dashboards were not publicly accessible and required valid user accounts. Internal access was considered low risk, and fine-grained authorization within dashboards was not reviewed.
3. The breach. What failed anyway?
Employees without a business need access dashboards containing sensitive financial metrics and customer details. The access was fully authenticated and logged, but the data visibility exceeded job responsibilities.
4. Where controls broke. Diagnosis.
Security controls focused on perimeter access rather than data-level authorization. Internal users were treated as trusted by default, and dashboards lacked role-based data filtering.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Internal systems are not inherently safe. 2. Authentication does not imply authorization to view all data. 3. Dashboards often bypass data minimization principles. 4. Role-based filtering must apply to internal tools. 5. Least privilege applies inside the organization as well.
6. The trade-off nobody mentions.
1. Implementing fine-grained access increases development effort. 2. Product and operations teams lose broad visibility. 3. Dashboards become more complex to maintain. 4. The benefit is preventing internal data misuse and leakage. Here is Java dashboard controller logic showing how missing role-based filtering exposes sensitive internal data. Disclaimer: always test code in a non-production environment. Here is the code snippet defining a dashboard endpoint that returns aggregated metrics without evaluating the caller's role or business need. This code block returns all available metrics, exposing sensitive business and customer data to any authenticated internal user.
Follow-up 1. Senior level. How do you secure internal dashboards properly?
Answer: I enforce role-based access and data-level filtering tied to explicit business responsibilities. Dashboards expose only the minimum data required for each role. In interviews, the key signal is treating internal tools with the same rigor as customer-facing systems.
Follow-up 2. Staff level. Why isn't network isolation enough for internal tools?
Answer: because internal access is broad and constantly changing. Employees, contractors, and service accounts all operate inside the network. In interviews, explaining that insider risk dominates internal systems shows real-world experience.
Follow-up, curveball. What if leadership wants company-wide transparency?
Answer: then transparency must be balanced against data sensitivity. I advocate for aggregated and anonymized views rather than raw data access. In interviews, the correct response is to frame transparency as a design choice, not unrestricted access.
8. Pro insider tip.
Many serious data leaks happen internally through dashboards. In interviews, saying internal visibility must be intentionally constrained signals real-world privacy and security leadership.
Category 4 wrap-up. Data exposure and privacy failures.
Every incident in this category shared a critical pattern. Systems behaved correctly, access was authorized, and no perimeter was breached. The failures occurred because data was exposed through normal application behavior. These incidents remind us that security controls are meaningless if data flows are not intentionally constrained.
Transition from data exposure to API and application logic abuse.
So far, damage occurred because systems revealed too much. Next, we examine incidents where applications are abused through perfectly valid requests. These failures are invisible to WAFs, scanners, and protocol-level defenses because the application does exactly what it was coded to do.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 5. API and application logic abuse.
API and logic abuse incidents exploit gaps between authentication and business intent. Requests are valid. Tokens are legitimate. The system is not hacked. It is misused. These are among the hardest incidents to detect and the most common reasons senior engineers fail security interviews.
Why logic abuse evades traditional security controls.
Firewalls, scanners, and identity systems protect protocols and identities, not business rules. Logic abuse occurs when applications fail to enforce ownership, intent, and constraints at the domain level.
Category 5. API and application logic abuse scenarios we will cover.
In this category, we will analyze the following real-world failure modes. 41. Broken Object Level Authorization (BOLA). 42. Mass Assignment Vulnerabilities. 43. Rate Limit Bypass through Logic Gaps. 44. Business Logic Abuse without Technical Exploits. 45. Enumeration Attacks using Valid Identifiers. 46. GraphQL Overfetching and Excessive Data Exposure. 47. Webhook Spoofing and Trust Abuse. 48. Cross-Site Request Forgery in Single-Page Applications. 49. Overtrusting Internal APIs. 50. Replay Attacks on idempotent endpoints. Logic abuse is where secure systems fail quietly.
Real-world cybersecurity incident number 41. Broken Object Level Authorization BOLA.
Millions of sensitive records were accessed without exploiting authentication, tokens, or infrastructure. The attacker simply requested objects they did not own. Every request was valid, authenticated, and logged. The application failed to verify ownership.
1. The setup. Everything looks secure.
The API enforced authentication using JWTs and validated scopes for access. Endpoints required valid user sessions, and authorization checks existed at the controller level.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed authentication, scope checks, and absence of injection vulnerabilities. API requests were authenticated and authorized according to documented access rules.
3. The breach. What failed anyway.
Users modified object identifiers in API requests and accessed records belonging to other users. Because the objects existed and the requests were authenticated, the application returned the data without restriction.
4. Where controls broke. Diagnosis.
Authorization validated who the user was, but not whether the user owned the requested object. The application assumed object access based on existence, not entitlement.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Authentication proves identity, not ownership. 2. Authorization must bind users to specific objects. 3. Valid identifiers are not proof of entitlement. 4. APIs must enforce domain-level ownership rules. 5. Logic abuse bypasses perimeter security entirely.
6. The trade-off nobody mentions.
1. Ownership checks increase query complexity. 2. Additional joins can impact performance. 3. Developers must understand domain boundaries deeply. 4. The benefit is preventing mass data exposure. Here is Java API logic showing how missing ownership checks enable broken object-level authorization. Disclaimer: always test code in a non-production environment. Here is the code snippet fetching an order by identifier only. There is no verification that the order belongs to the authenticated user. This code block shows the API trusting client-supplied object identifiers without enforcing ownership constraints.
Follow-up 1. Senior level. Why don't scopes prevent BOLA?
Answer: scopes define what actions a user may perform, not which specific objects they may access. Without ownership enforcement, a scoped user can act on any object identifier. In interviews, the key signal is distinguishing capability from entitlement.
Follow-up 2. Staff level. How do you implement ownership checks efficiently?
Answer: I enforce ownership at the data access layer using queries that bind object retrieval to the authenticated user context. This ensures checks cannot be bypassed accidentally. In interviews, emphasizing enforcement depth shows maturity.
Follow-up curveball. What if ownership checks hurt performance?
Answer: then the data model must evolve to support secure access patterns. I treat performance impact as a design constraint, not a reason to skip security. In interviews, the correct response is to frame performance as solvable, exposure as unacceptable.
8. Pro insider tip.
Most large-scale API breaches are BOLA failures. In interviews, saying, "We bind authorization to data ownership, not endpoints," signals real-world application security experience.
Real-world cybersecurity incident number 42. Mass assignment vulnerabilities.
Sensitive fields were modified without exploiting authentication, authorization, or infrastructure controls. The attacker submitted valid API requests with additional fields that the application automatically mapped to backend objects. The system accepted the input exactly as designed.
1. The setup. Everything looks secure.
The API used modern frameworks with automatic request-to-object binding. Authentication and role-based access controls were enforced, and input validation existed for required fields.
2. What passed audits. Security incidents that passed every audit.
Audits verified authentication, authorization, and absence of injection flaws. The API schema documented allowed fields, but binding behavior was not examined for overposting risk.
3. The breach. What failed anyway.
An attacker included additional JSON fields in a legitimate request, such as role and account status. The framework automatically populated these fields on the backend object, elevating privileges and bypassing business rules.
4. Where controls broke, diagnosis.
The application trusted client input too broadly. Automatic object binding treated all fields as writable unless explicitly restricted, allowing clients to modify internal state they should never control.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Framework convenience can become an attack surface. 2. Clients must never control internal object state. 3. Write permissions must be explicit, not implicit. 4. DTOs are security boundaries, not boilerplate. 5. Mass assignment is a trust failure, not a validation bug.
6. The trade-off nobody mentions.
1. Explicit DTOs increase development effort. 2. Mapping logic becomes more verbose. 3. Schema changes require coordinated updates. 4. The benefit is eliminating entire classes of logic abuse. Here is Java request binding logic showing how automatic field mapping enables mass assignment attacks. Disclaimer: always test code in a non-production environment. Here is the code snippet binding the entire request body directly to the user entity. Any writable field can be modified by the client. This code block persists all client-controlled fields, including sensitive ones that should never be user-modifiable.
Follow-up 1. Senior level. How do you prevent mass assignment systematically?
Answer: I introduce explicit request DTOs with allow-listed fields and map them manually to domain objects. Only fields required for the specific operation are writable. In interviews, the key signal is treating object boundaries as security boundaries.
Follow-up 2. Staff level. Why isn't input validation sufficient here?
Answer: validation checks correctness, not authorization. A field can be valid but unauthorized. In interviews, explaining that validation and authorization solve different problems shows architectural depth.
Follow-up, curveball. What if the team prefers rapid development over manual mapping?
Answer: then the organization is trading speed for systemic risk. I frame DTO mapping as a one-time cost that prevents repeated incidents. In interviews, the correct response is to acknowledge the trade-off and defend safety.
8. Pro insider tip.
Mass assignment vulnerabilities exist because frameworks optimize for convenience, not intent. In interviews, saying automatic binding is a security decision signals real-world application security experience.
Real-world cybersecurity incident number 43. Rate limit bypass through application logic.
Sensitive operations were abused at scale without triggering any rate limit alerts. No infrastructure controls were bypassed. The failure occurred because rate limiting was applied to endpoints, not to the underlying business actions, allowing attackers to restructure requests to avoid limits.
1. The setup. Everything looks secure.
The API enforced rate limits at the gateway and application layer. Limits were applied per endpoint and per IP address. Monitoring showed expected request volumes.
2. What passed audits? Security incidents that passed every audit.
Audits verified that rate limits existed, thresholds were configured, and alerts were triggered on limit violations. The logic behind how limits aligned with business actions was not reviewed.
3. The breach. What failed anyway?
Attackers performed high-impact operations by distributing them across multiple endpoints and parameters. Each individual request stayed within configured limits, but the aggregate business impact exceeded intended thresholds.
4. Where controls broke, diagnosis.
Rate limiting focused on transport-level characteristics rather than business intent. The application failed to recognize that multiple code paths executed the same sensitive operation.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Rate limits must align with business actions. 2. Endpoints are an implementation detail. 3. Attackers optimize around control placement. 4. Aggregation matters more than individual requests. 5. Logic-level throttling closes structural gaps.
6. The trade-off nobody mentions.
1. Business-level throttling requires state tracking. 2. Implementation complexity increases significantly. 3. False positives may block legitimate bursts. 4. The benefit is preventing large-scale abuse. Here is Java service logic showing how endpoint-based rate limits fail to protect sensitive business operations. Disclaimer: always test code in a non-production environment. Here is the code snippet representing a sensitive business operation that can be triggered through multiple endpoints. This code block executes the operation without enforcing any business-level rate limiting, allowing abuse across request paths.
Follow-up 1. Senior level. How do you implement business-level rate limiting?
Answer: I enforce throttling at the service layer based on user identity and action type rather than endpoint. Limits are tracked over rolling windows. In interviews, the key signal is aligning controls with intent, not URLs.
Follow-up 2. Staff level. Why isn't API gateway rate limiting enough?
Answer: gateways see requests, not meaning. They cannot infer when different requests trigger the same business action. In interviews, emphasizing semantic limits over transport limits shows architectural maturity.
Follow-up curveball. What if business users legitimately need bursts?
Answer: then limits must be adaptive and role-aware rather than static. I design throttles that distinguish between abuse and legitimate spikes. In interviews, the correct response is balancing protection with usability.
8. Pro insider tip.
Most rate limit bypasses exploit logic placement, not configuration gaps. In interviews, saying, "We throttle actions, not endpoints," signals deep application security experience.
Real-world cybersecurity incident number 44. Business logic abuse without technical exploits.
Significant financial loss occurred without exploiting authentication, authorization, or infrastructure controls. The attacker followed the application rules precisely, but exploited unintended interactions between business rules. Every action was valid, expected, and logged.
1. The setup. Everything looks secure.
The application enforced authentication, input validation, and role-based access control. Business rules were implemented correctly in isolation and covered by unit tests.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed no injection flaws, no authorization bypass, and correct validation logic. Individual workflows behaved as designed.
3. The breach. What failed anyway?
Attackers chained valid operations in an unexpected order to maximize discounts and refunds. Each step followed documented rules, but the combined effect violated business intent.
4. Where controls broke. Diagnosis.
Security reviews focused on technical correctness rather than system behavior under adversarial sequencing. The application lacked global constraints across workflows.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Valid steps can produce invalid outcomes. 2. Business intent must be enforced globally. 3. Attackers optimize for rule interaction. 4. Tests must cover adversarial workflows. 5. Logic abuse is a design failure, not a bug.
6. The trade-off nobody mentions.
1. Global rule enforcement increases system complexity. 2. Feature velocity slows as constraints grow. 3. Product logic becomes harder to reason about. 4. The benefit is preventing systemic exploitation. Here is Java business logic, showing how valid workflows combine into unintended financial abuse. Disclaimer: always test code in a non-production environment. Here is the code snippet applying a coupon, without considering whether it should stack with other discounts. This code block applies an additional discount independently, allowing attackers to combine benefits beyond intended limits.
Follow-up 1. Senior level. How do you prevent business logic abuse?
Answer: I introduce invariant checks that enforce global constraints across workflows. These checks represent business intent, not implementation details. In interviews, the key signal is reasoning about system behavior, not just code correctness.
Follow-up 2. Staff level. Why don't unit tests catch this?
Answer: unit tests validate isolated logic, not emergent behavior across workflows. Abuse arises from combinations tests rarely cover. In interviews, explaining emergent risk shows architectural maturity.
Follow-up curveball. What if product wants maximum flexibility?
Answer: then flexibility must be bounded by safety constraints. I collaborate to define acceptable outcomes explicitly. In interviews, The correct response is balancing revenue with resilience.
8. Pro Insider Tip.
Business logic abuse thrives where rules are evaluated locally. In interviews, saying, "We enforce global invariance," signals deep system design experience.
Real-world cybersecurity incident number 45. Enumeration attacks using valid identifiers.
Large volumes of sensitive records were harvested without breaking authentication, authorization, or rate limits. The attacker iterated through valid-looking identifiers and received legitimate responses. Every request was authorized, logged, and compliant with API contracts.
1. The setup. Everything looks secure.
The API required authentication, enforced scopes, and validated request formats. Object identifiers used UUIDs, and no sequential IDs were exposed publicly.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed authentication, authorization, and absence of injection vulnerabilities. Identifier formats were reviewed and deemed non-guessable.
3. The breach. What failed anyway.
Attackers enumerated identifiers through response behavior and timing differences. Valid-looking UUIDs were tested at scale, and the API revealed whether objects existed through distinct responses.
4. Where controls broke. Diagnosis.
The application leaked object existence through error messages and response patterns. Authorization verified access rights, but did not conceal whether a resource existed.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Existence is sensitive information. 2. Error behavior can leak domain knowledge. 3. Identifiers do not need to be guessable to be enumerable. 4. Uniform responses reduce reconnaissance value. 5. Enumeration is a logic leak, not brute force.
6. The trade-off nobody mentions.
1. Uniform error responses reduce debuggability. 2. Clients receive less specific failure information. 3. Monitoring must compensate for lost signals. 4. The benefit is preventing large-scale data harvesting. Here is Java API error handling, showing how distinct responses enable object enumeration. Disclaimer: always test code in a non-production environment. Here is the code snippet returning a distinct error when an object does not exist, confirming identifier validity to the caller. This code block shows the API directly exposing object lookup behavior based on client-supplied identifiers.
Follow-up 1. Senior level. How do you prevent enumeration without hiding real errors?
Answer: I standardize responses so unauthorized and non-existent resources are indistinguishable to the caller. Internally, detailed errors are logged for operators. In interviews, the key signal is separating client behavior from operator visibility.
Follow-up 2. Staff level. Why aren't UUIDs enough to stop enumeration?
Answer: because enumeration relies on feedback, not guessing. Attackers learn from responses over time. In interviews, emphasizing feedback channels over identifier entropy shows depth.
Follow-up curveball. What if product needs precise error messages?
Answer: then precision must be limited to trusted clients or internal tooling. Public APIs should prioritize safety over clarity. In interviews, the correct response is to frame error detail as an exposure decision.
8. Pro Insider Tip.
Enumeration attacks succeed because systems talk too much. In interviews, saying, "We treat existence as sensitive," signals real-world API security experience.
Real-world cybersecurity incident number 46. GraphQL overfetching and excessive data exposure.
Sensitive fields were exposed without breaking authentication or authorization. The attacker issued valid GraphQL queries that requested more fields than the front-end ever used. The server returned exactly what was asked for, revealing internal and sensitive data.
1. The setup. Everything looks secure.
The application used GraphQL to give clients flexible data access. Authentication was enforced, and resolvers validated user identity. Front-end queries were reviewed and appeared safe.
2. What passed audits. Security incidents that passed every audit.
Audits verified authentication, authorization, and schema validation. The GraphQL endpoint was protected, and no injection vulnerabilities were found.
3. The breach, what failed anyway.
Attackers crafted custom GraphQL queries requesting additional fields such as internal flags, audit metadata, and sensitive attributes. Because the schema allowed access and resolvers returned full objects, the data was exposed.
4. Where controls broke, diagnosis.
Authorization was enforced at the object level, but not at the field level. The system assumed clients would only request fields used by the front end, treating schema flexibility as harmless.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. GraphQL exposes intent, not just data. 2. Field-level access must be explicitly controlled. 3. Front-end usage does not define back-end exposure. 4. Schemas are public contracts, not UI helpers. 5. Overfetching is a design risk, not misuse.
6. The trade-off nobody mentions.
1. Field-level authorization increases resolver complexity. 2. Schema evolution becomes more constrained. 3. Developer velocity slows with granular controls. 4. The benefit is preventing silent data overexposure. Here is Java GraphQL resolver logic showing how returning full objects enables overfetching of sensitive fields. Disclaimer: always test code in a non-production environment. Here is the code snippet returning the full user object. Any field exposed in the GraphQL schema becomes accessible to the caller. This code block shows the resolver trusting the schema to limit access instead of enforcing field-level authorization.
Follow-up 1. Senior level. How do you secure GraphQL without losing flexibility?
Answer: I implement field-level authorization and schema directives that enforce access rules per field. Sensitive fields require explicit checks regardless of object access. In interviews, the key signal is treating schemas as security boundaries.
Follow-up 2. Staff level. Why isn't object-level authorization enough?
Answer: because objects often contain fields with different sensitivity levels. Object access does not imply entitlement to every attribute. In interviews, highlighting attribute-level risk shows maturity.
Follow-up, curveball. What if front-end teams want unrestricted queries?
Answer: then unrestricted queries must be limited to trusted internal clients. Public schemas should be intentionally constrained. In interviews, the correct response is separating internal convenience from external exposure.
8. Pro insider tip.
Most GraphQL leaks happen because schemas grow faster than authorization rules. In interviews, saying fields are the real attack surface signals real-world GraphQL security experience.
Real-world cybersecurity incident number 47. Webhook spoofing and trust abuse.
Sensitive state changes were triggered without breaching authentication systems or internal services. The attacker sent forged webhook requests that appeared legitimate. Because the application trusted the source implicitly, the requests were processed as valid events.
1. The setup. Everything looks secure.
The application integrated with third-party services using webhooks for asynchronous events. Endpoints were unlinked from public documentation. HTTPS was enforced, and inbound traffic appeared to originate from expected providers.
2. What passed audits? Security incidents that passed every audit.
Audits verified HTTPS usage, endpoint obscurity, and firewall rules. The webhook endpoint required no authentication by design, assuming trust based on network origin and provider reputation.
3. The breach. What failed anyway?
Attackers reverse-engineered the webhook payload format and sent forged requests directly to the endpoint. Because no signature verification or replay protection existed, the application processed the events as legitimate.
4. Where controls broke, diagnosis.
The application trusted the transport and source rather than validating message authenticity. Webhooks were treated as trusted internal signals instead of untrusted external input.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Webhook endpoints are public attack surfaces. 2. Network trust does not equal message authenticity. 3. Every webhook must be cryptographically verified. 4. Replay protection is as important as signature checks. 5. Event-driven systems require zero trust assumptions.
6. The trade-off nobody mentions.
1. Signature verification adds implementation complexity. 2. Key rotation must be coordinated with providers. 3. Debugging webhook failures becomes harder. 4. The benefit is preventing forged state changes. Here is Java webhook handler logic showing how missing signature validation allows spoofed external events. Disclaimer: always test code in a non-production environment. Here is the code snippet accepting webhook payloads without verifying the sender's authenticity or intent. This code block processes the event immediately, allowing forged requests to trigger sensitive business actions.
Follow-up 1, senior level. How do you secure webhooks properly?
Answer: I enforce cryptographic signature verification using shared secrets or public keys, validate timestamps, and reject replays. Webhooks are treated as untrusted input until verified. In interviews, the key signal is framing webhooks as public APIs.
Follow-up 2, staff level. Why isn't IP allow listing sufficient?
Answer: because IP ranges change, can be spoofed through proxies, and do not prove message integrity. Trusting IPs shifts risk without eliminating it. In interviews, emphasizing message authenticity over network trust shows depth.
Follow-up, curveball. What if the provider does not support signatures?
Answer: then I treat the integration as high risk and add compensating controls such as out-of-band verification and strict idempotency checks. In interviews, the correct response is to articulate residual risk explicitly.
8, pro insider tip.
Most webhook breaches succeed because teams trust delivery instead of authenticity. In interviews, saying every webhook is an unauthenticated API signals real-world event-driven security experience.
Real-world cybersecurity incident number 48, cross-site request forgery, CSRF, in single-page applications.
Authenticated user actions were executed without user intent, password compromise, or token theft. The attacker exploited browser behavior and implicit trust in cookies. Every request was valid, authenticated, and indistinguishable from legitimate user activity.
1. The setup. Everything looks secure.
The application was a modern SPA using cookies for session management and JWTs for API authentication. HTTPS was enforced, authentication worked correctly, and no cross-site scripting vulnerabilities were present.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed authentication, secure cookies, and correct CORS configuration. CSRF protection was assumed unnecessary because the application used modern frameworks and APIs.
3. The breach. What failed anyway?
Attackers embedded malicious requests in third-party sites. When logged-in users visited those sites, their browsers automatically included session cookies, executing sensitive actions without user awareness.
4. Where controls broke. Diagnosis.
The application trusted cookies as proof of intent. There was no CSRF token, origin validation, or double submit protection. The system assumed authenticated requests were intentional.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Browsers automatically attach credentials. 2. Authentication does not imply user intent. 3. CSRF exploits ambient authority. 4. SPAs are not immune to browser-based attacks. 5. Intent must be proven, not assumed.
6. The trade-off nobody mentions.
1. CSRF tokens add state and complexity. 2. Front-end-back-end coordination increases. 3. Caching and prefetching become harder. 4. The benefit is preventing silent user abuse. Here is JavaScript request logic showing how missing CSRF tokens allows browsers to perform unintended authenticated actions. Disclaimer: always test code in a non-production environment. Here is the code snippet instructing the browser to automatically attach authentication cookies, even when the request is triggered cross-site. This code block shows a sensitive action being executed without any proof of user intent beyond existing session state.
Follow-up 1. Senior level. Why doesn't same-site cookies fully solve CSRF?
Answer: same site reduces risk but does not cover all browser behaviors and legacy flows. It also fails when cross-site functionality is required. In interviews, the key signal is treating same site as a mitigation, not a guarantee.
Follow-up 2. Staff level. Why aren't JWTs enough to prevent CSRF?
Answer: JWTs stored in cookies are still automatically sent by the browser. CSRF targets the browser's credential handling, not token format. In interviews, distinguishing token type from transport behavior shows depth.
Follow-up, curveball. What if CSRF protection breaks legitimate integrations?
Answer: then those integrations must use explicit authentication mechanisms like API keys or signed requests. User cookies should never be reused for machine-to-machine actions. In interviews, the correct response is separating user intent from automation.
8. Pro Insider Tip.
CSRF succeeds because browsers are obedient, not because systems are broken. In interviews, saying cookies are ambient authority signals real-world web security expertise.
Real-world cybersecurity incident number 49. Overtrusting internal APIs.
Sensitive operations were performed without user context, authorization checks, or intent validation. The abuse originated from within the network boundary using a compromised service. Every request was authenticated and appeared legitimate in logs.
1. The setup. Everything looks secure.
The architecture relied on internal APIs for service-to-service communication. Network segmentation, mutual TLS, and service authentication were enforced. Internal APIs were not exposed to the public internet.
2. What passed audits? Security incidents that passed every audit.
Audits verified MTLS configuration, service identities, and restricted network access. Internal endpoints were assumed to be trusted and were excluded from detailed authorization reviews.
3. The breach. What failed anyway?
A compromised internal service invoked high-privilege APIs intended only for administrative workflows. Because the requests originated from a trusted service, they were processed without user-level authorization.
4. Where controls broke. Diagnosis.
The system conflated network trust with authorization. Internal APIs enforced identity, but failed to enforce intent, scope, or caller responsibility.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Internal does not mean trusted. 2. Service identity is not user intent. 3. Authorization must apply east-west. 4. Network controls cannot replace logic checks. 5. Zero trust applies inside the perimeter.
6. The trade-off nobody mentions.
1. Adding authorization to internal APIs slows development. 2. Service contracts become more rigid. 3. Debugging requires more context propagation. 4. The benefit is preventing lateral abuse. Here is Java internal API logic, showing how trusting internal callers enables unauthorized privileged actions. Disclaimer: always test code in a non-production environment. Here is the code snippet exposing a privileged internal operation without validating caller intent or authorization scope. This code block executes a destructive action solely based on internal access, enabling lateral movement after service compromise.
Follow-up 1. Senior level. How do you secure internal APIs properly?
Answer: I enforce the same authorization rigor internally as externally, including scopes, purpose checks, and audit context. Internal APIs require explicit contracts defining allowed callers and actions. In interviews, the key signal is applying zero trust consistently.
Follow-up 2. Staff level. Why isn't MTLS enough here?
Answer: MTLS proves service identity, not authorization to perform a specific action. Once a service is compromised, MTLS becomes meaningless. In interviews, explaining identity versus intent shows architectural depth.
Follow-up, curveball. What if teams push back due to latency and complexity?
Answer: then the organization is explicitly accepting lateral movement risk. I advocate phased enforcement starting with high-impact operations. In interviews, the correct response is acknowledging trade-offs without dismissing risk.
8. Pro Insider Tip.
Most catastrophic breaches spread through trusted internal APIs. In interviews, saying internal APIs are the primary blast radius amplifier signals real-world security leadership.
Real-world cybersecurity incident number 50. Replay attacks on idempotent endpoints.
Financial and state-changing operations were executed multiple times without breaking authentication, authorization, or rate limits. The attacker simply replayed previously valid requests. Each request was syntactically correct, authenticated, and processed as intended by the application.
1. The setup. Everything looks secure.
The API used idempotent endpoints for reliability and retries. Authentication was enforced using JWTs, and endpoints validated request structure and required parameters. Retries were encouraged to improve client resilience.
2. What passed audits? Security incidents that passed every audit.
Audits verified authentication, authorization, and absence of injection flaws. Idempotency was documented as a best practice for client reliability, and replay risk was not assessed.
3. The breach. What failed anyway?
Attackers captured valid requests and replayed them repeatedly within and across sessions. Because the application treated each request independently and lacked replay detection, the same operation executed multiple times.
4. Where controls broke. Diagnosis.
The application conflated idempotency with safety. While the endpoint accepted duplicate requests by design, it failed to enforce single execution semantics for sensitive operations.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Idempotency improves reliability, not security. 2. Valid requests can still be maliciously replayed. 3. Sensitive operations require execution guarantees. 4. Replay protection must exist above transport layers. 5. Request uniqueness is a security concern.
6. The trade-off nobody mentions.
1. Replay detection introduces statefulness. 2. Storage is required for request identifiers. 3. Legitimate retries may be rejected. 4. The benefit is preventing repeated state manipulation. Here is Java API logic showing how missing request uniqueness checks allow replay of idempotent operations. Disclaimer: always test code in a non-production environment. Here is the code snippet accepting a payment request without verifying whether it has already been processed. This code block executes the operation every time it is received, allowing attackers to replay the same request to trigger repeated effects.
Follow-up 1. Senior level. How do you prevent replay attacks on idempotent endpoints?
Answer: I require a unique, single-use request identifier and enforce exactly once execution semantics for sensitive operations. Processed identifiers are stored with expiration. In interviews, the key signal is distinguishing reliability patterns from security guarantees.
Follow-up 2. Staff level. Why isn't HTTPS enough to stop replays?
Answer: HTTPS protects data in transit but does not prevent a valid request from being resent. Replay attacks reuse correctness, not interception. In interviews, explaining this separation shows protocol-level understanding.
Follow-up curveball. What if replay protection breaks legitimate retries?
Answer: then retries must be explicitly modeled and distinguished from duplicates using idempotency keys with clear semantics. Reliability should not come at the cost of correctness. In interviews, the correct response is designing retries intentionally.
8. Pro insider tip.
Replay attacks succeed because systems assume correctness equals intent. In interviews, saying idempotent does not mean safe signals deep application security experience.
Category 5. Wrap-up. API and application logic abuse.
Every incident in this category demonstrated the same uncomfortable truth. Modern breaches rarely exploit broken authentication or missing encryption. They exploit gaps between identity, authorization, and business intent. These failures evade scanners because the system behaves exactly as designed.
Transition from logic abuse to ransomware and lateral movement.
So far, attackers abused what applications allowed them to do. Next, we shift to incidents where attackers move laterally, escalate impact, and destroy availability. These scenarios explain why ransomware is no longer a malware problem. It is an identity and configuration problem.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario, based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 6. Ransomware and lateral movement.
Modern ransomware incidents rarely begin with exploits. They begin with legitimate access. Attackers authenticate, enumerate, move laterally, disable recovery paths, and only then encrypt or extort. This category focuses on how infrastructure and identity decisions quietly enable that progression.
Category 6. Ransomware and lateral movement scenarios we will cover.
In this category, we will analyze the following real-world failure modes. 51. Credential-based initial access without exploits. 52. Living off-the-land techniques using native tools. 53. Privilege escalation through Active Directory misconfiguration. 54. Backup destruction prior to encryption. 55. Double extortion without service disruption. 56. Delayed detonation ransomware. 57. Endpoint detection and response evasion. 58. Cloud workload encryption. 59. Cross-environment lateral spread. 60. Insider-assisted ransomware events. Ransomware succeeds when identity and recovery controls fail silently.
Real-world cybersecurity incident number 51. Credential-based initial access.
A ransomware campaign began without malware exploits, phishing kits, or 0 days. The attacker authenticated using valid credentials obtained earlier and operated entirely within normal access patterns. Every action was authorized, logged, and compliant with existing IAM policies.
1. The setup. Everything looks secure.
The environment enforced MFA for human users, used role-based access for services, and restricted administrative access. IAM policies were reviewed periodically and followed documented least privilege guidelines.
2. What passed audits? Security incidents that passed every audit.
Audits verified MFA enforcement, credential rotation policies, and absence of hard-coded secrets. Access logs showed only successful, authenticated activity from valid identities.
3. The breach. What failed anyway?
An attacker authenticated using valid credentials and began enumerating resources. Because the access was legitimate and permissions were broad enough, the attacker pivoted across systems and prepared the environment for ransomware deployment.
4. Where controls broke. Diagnosis.
IAM validated identity, but failed to constrain blast radius. Credentials granted access across unrelated systems, enabling reconnaissance and lateral movement without triggering alerts.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Ransomware starts with identity, not malware. 2. Valid credentials are assumed to be compromised eventually. 3. Blast radius matters more than login strength. 4. Authentication success is not a security signal. 5. Containment must be enforced by design.
6. The trade-off nobody mentions.
1. Tighter identity scoping increases operational friction. 2. Engineers lose broad visibility and convenience. 3. Access requests increase across teams. 4. The benefit is preventing organization-wide ransomware impact. Here is IAM policy JSON, showing how broad identity permissions enable ransomware lateral movement after credential compromise. Disclaimer: always test code in a non-production environment. Here is the code snippet granting unrestricted actions. Once credentials are compromised, attackers inherit full operational capability. This code block shows unrestricted resource access, allowing lateral movement across environments without additional escalation.
Follow-up 1. Senior level. Why doesn't MFA stop ransomware here?
Answer: MFA protects initial authentication, not post-authentication behavior. Once credentials are valid, MFA is no longer in the execution path. In interviews, the key signal is recognizing that MFA is a gate, not a containment mechanism.
Follow-up 2. Staff level. How do you reduce blast radius without blocking teams?
Answer: I segment access by responsibility and environment, enforcing narrow roles and just-in-time elevation. Compromise of one identity should not grant meaningful reach. In interviews, emphasizing segmentation over restriction shows maturity.
Follow-up curveball. What if leadership wants fewer IAM roles?
Answer: then the organization is choosing simplicity over resilience. I present blast radius diagrams to make risk visible. In interviews, the correct response is framing IAM sprawl versus ransomware impact as a business decision.
8. Pro insider tip.
Most ransomware groups log in before they deploy anything. In interviews, saying ransomware is an IAM failure first signals real-world incident experience.
Real-world cybersecurity incident number 52. Living off the land techniques.
A ransomware campaign progressed deep into the environment without deploying custom malware or exploiting vulnerabilities. The attacker relied entirely on built-in operating system tools and cloud-native utilities. Every command executed was legitimate, signed, and commonly used by administrators.
1. The setup. Everything looks secure.
Endpoints were fully patched, antivirus was enabled, and EDR agents were deployed across the fleet. Administrative access was restricted to approved users, and security tooling showed no malware detections.
2. What passed audits? Security incidents that passed every audit.
Audits verified patch levels, EDR deployment, and absence of unsigned binaries. Security posture reports showed high compliance and low malware risk.
3. The breach. What failed anyway?
Attackers used native tools such as PowerShell, remote management utilities, and cloud CLIs to enumerate systems, disable defenses, and move laterally. Because the tools were legitimate, activity blended into normal administrative noise.
4. Where controls broke. Diagnosis.
Security controls focused on detecting malicious binaries rather than malicious behavior. The environment assumed trusted tools would only be used for legitimate purposes.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Attackers prefer tools defenders trust. 2. Signed binaries are not proof of benign intent. 3. Behavior matters more than file reputation. 4. Administrative tools amplify blast radius. 5. Detection must focus on misuse patterns.
6. The trade-off nobody mentions.
1. Behavioral detection generates more false positives. 2. Legitimate admin activity may be interrupted. 3. Security teams require deeper context to respond. 4. The benefit is visibility into stealthy attacks.
Follow-up 1. Senior level. How do you detect living off the land activity?
Answer: I focus on behavioral baselines rather than tool signatures. Administrative actions are monitored for unusual timing, scope, and sequencing. In interviews, the key signal is prioritizing behavior over binaries.
Follow-up 2. Staff level. Why doesn't EDR stop this by default?
Answer: because EDRs are optimized to detect malware, not legitimate tools used maliciously. When attackers stay within normal tool chains, alerts are harder to trigger. In interviews, explaining this gap shows operational experience.
Follow-up curveball. What if restricting admin tools slows operations?
Answer, then controls must be adaptive and risk-based rather than blanket restrictions. I advocate for just-in-time admin access and strong auditing. In interviews, the correct response is balancing operability with containment.
8. Pro Insider Tip.
The most dangerous attacks look like normal administration. In interviews, saying, "We hunt for abuse of legitimate tools," signals real-world ransomware defense experience.
Real-world cybersecurity incident number 53. Privilege escalation via Active Directory misconfiguration.
Ransomware operators escalated from a standard domain user to domain administrator without exploiting software vulnerabilities. The escalation occurred through legitimate Active Directory permissions that were misconfigured years earlier. Every action used built-in directory capabilities.
1. The setup. Everything looks secure.
The environment used centralized Active Directory with delegated administration. Permissions were assigned to groups for operational efficiency, and no obvious domain admin accounts were exposed.
2. What passed audits? Security incidents that passed every audit.
Audits verified that domain admin membership was restricted, and MFA was enforced for privileged accounts. Delegated permissions and ACL inheritance were not deeply reviewed.
3. The breach. What failed anyway?
Attackers abused delegated permissions to modify group memberships and escalate privileges. Because the permissions were valid and inherited, the changes did not trigger alerts.
4. Where controls broke. Diagnosis.
Active Directory authorization focused on role membership rather than effective permissions. Inherited ACLs silently granted escalation paths that were never intended.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Effective permissions matter more than group names. 2. Delegation creates hidden privilege paths. 3. AD security failures are usually configuration failures. 4. Inheritance amplifies blast radius silently. 5. Privilege reviews must include ACL analysis.
6. The trade-off nobody mentions.
1. Tightening AD permissions increases admin workload. 2. Operational delegation becomes more complex. 3. Legacy automation may break. 4. The benefit is preventing domain-wide compromise. Here is PowerShell Active Directory configuration, showing how delegated permissions enable unintended privilege escalation. Disclaimer: always test code in a non-production environment. Here is the code snippet modifying membership of a highly privileged group using delegated permissions rather than direct admin access. This code block adds a broadly scoped group, unintentionally granting domain admin privileges to all its members.
Follow-up 1. Senior level. How do you detect hidden AD escalation paths?
Answer: I analyze effective permissions and group inheritance using directory graph tools and periodic ACL reviews. Delegation is treated as privileged access. In interviews, the key signal is focusing on effective rights, not titles.
Follow-up 2. Staff level. Why aren't domain admin audits enough?
Answer: because attackers rarely start as domain admins. They exploit delegated rights and inheritance to get there. In interviews, explaining lateral privilege paths shows deep AD understanding.
Follow-up, curveball. What if tightening delegation slows IT operations?
Answer: then risk must be explicitly accepted or mitigated with just-in-time elevation. Permanent delegation is convenient but dangerous. In interviews, the correct response is balancing operational speed with blast radius.
8. Pro Insider Tip.
Most AD breaches succeed through permissions nobody remembers granting. In interviews, saying, "We audit effective permissions, not just group membership," signals real-world directory security experience.
Real-world cybersecurity incident number 54. Backup destruction prior to ransomware encryption.
Ransomware caused catastrophic business impact not because encryption was sophisticated, but because recovery was impossible. Attackers destroyed or disabled backups before encrypting production systems. No backup integrity alerts fired until it was too late.
1. The setup. Everything looks secure.
The organization used automated backups for databases and file systems. Infrastructure as code defined backup schedules and retention. Backups were considered reliable and were regularly created without errors.
2. What passed audits? security incidents that passed every audit.
Audits verified that backups existed, were encrypted, and met retention requirements. Restore procedures were documented. Access controls on backup management operations were not reviewed in depth.
3. The breach, what failed anyway.
After gaining valid credentials, attackers disabled backup schedules and deleted existing recovery points. When ransomware was deployed, no usable backups remained. Recovery options were eliminated before encryption began.
4. Where controls broke, diagnosis.
Backups were protected at rest, but not protected from administrative actions. The same identities that could manage production systems could also delete backups, eliminating the last line of defense.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Backups must be protected from administrators. 2. Recovery systems are attack targets. 3. Deletion is as dangerous as encryption. 4. Backup immutability breaks ransomware playbooks. 5. Separation of duties is critical for resilience.
6. The trade-off nobody mentions.
1. Immutable backups complicate legitimate cleanup. 2. Operational flexibility is reduced. 3. Recovery testing requires special workflows. 4. The benefit is guaranteed recoverability. Here is Terraform configuration, showing how backups without immutability can be deleted before ransomware execution. Disclaimer: always test code in a non-production environment. Here is the code snippet defining a backup vault without any immutability or deletion protection controls. This code block shows a production backup vault that can be modified or deleted by any identity with backup permissions.
Follow-up 1. Senior level. How do you protect backups from administrators?
Answer: I enforce backup immutability with write-once retention and separate identities for backup management. Backup deletion requires break-glass workflows. In interviews, the key signal is protecting recovery paths from the same compromise.
Follow-up 2. Staff level. Why isn't encryption enough for backups?
Answer: encryption protects confidentiality, not availability. If backups are deleted or disabled, encryption provides no recovery value. In interviews, emphasizing availability as a security pillar shows depth.
Follow-up curveball. What if immutable backups increase cost?
Answer: then the cost must be compared against existential business loss. I frame immutability as insurance, not overhead. In interviews, the correct response is quantifying recovery risk.
8. Pro insider tip.
Ransomware succeeds when recovery is disabled first. In interviews, saying, "We protect backups from administrators," signals real-world resilience engineering experience.
Real-world cybersecurity incident, number 55. Double extortion without service disruption.
The organization was extorted without experiencing downtime, encryption, or visible system failure. Attackers quietly exfiltrated sensitive data and threatened public release. Operations continued normally, making the incident harder to detect and easier to underestimate.
1. The setup. Everything looks secure.
Production systems were stable, backups were healthy, and no anomalous performance issues were observed. Security monitoring focused heavily on availability and malware indicators.
2. What passed audits? Security incidents that passed every audit.
Audits verified backup integrity, incident response plans, and ransomware preparedness focused on encryption scenarios. Data exfiltration detection and data movement monitoring were limited.
3. The breach. What failed anyway?
Attackers accessed sensitive datasets and exfiltrated them over time using legitimate credentials and approved data paths. No encryption occurred. The organization learned of the breach only after receiving an extortion demand.
4. Where controls broke, diagnosis.
Security strategy equated ransomware with service disruption. Controls were optimized to detect encryption and downtime rather than silent data theft and coercion.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Extortion does not require encryption. 2. Availability is not the only ransomware goal. 3. Data theft enables leverage without disruption. 4. Silent breaches are strategically preferred. 5. Detection must include outbound data abuse.
6. The trade-off nobody mentions.
1. Monitoring data movement increases operational noise. 2. False positives are common during large transfers. 3. Security teams require better data context. 4. The benefit is early detection of coercion campaigns.
Follow-up 1, senior level. How do you detect double extortion early?
Answer: I monitor for unusual data access and outbound transfer patterns rather than waiting for encryption signals. Detection focuses on intent, not outcome. In interviews, the key signal is recognizing that ransomware goals have evolved.
Follow-up 2, staff level. Why didn't backups help here?
Answer: because backups protect availability, not confidentiality. Double extortion attacks bypass recovery entirely. In interviews, explaining the separation of security objectives shows architectural understanding.
Follow-up, curveball. What if leadership only cares about uptime?
Answer: then the risk must be reframed as reputational, regulatory, and legal exposure. I show how silent breaches often cause more damage than outages. In interviews, the correct response is translating technical risk into business impact.
8, pro insider tip.
Many ransomware groups prefer not to encrypt at all. In interviews, saying extortion succeeds without downtime signals modern threat awareness.
Real-world cybersecurity incident, number 56. Delayed detonation ransomware.
Ransomware was deployed into the environment weeks before activation. Systems operated normally during this period, backups appeared healthy, and no alerts fired. The payload activated only after recovery paths and incident response readiness had degraded.
1, the setup, everything looks secure.
The organization maintained regular patching, endpoint protection, and backup schedules. Security posture dashboards showed green across all monitored dimensions.
2, what passed audits? Security incidents that passed every audit.
Audits validated backup existence, malware signatures, and endpoint compliance. No indicators of compromise were detected during routine scans.
3, the breach, what failed anyway?
Attackers planted ransomware payloads and waited for operational changes such as reduced staffing, delayed patching, or backup window misalignment. When activated, encryption coincided with maximum organizational vulnerability.
4, where controls broke, diagnosis.
Security controls assumed immediate execution. Monitoring focused on real-time detection rather than long-term persistence and latent threats.
5, the interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Time is a weapon for attackers. 2. Persistence is more dangerous than speed. 3. Security assumptions decay over time. 4. Detection must include dormant threats. 5. Operational drift increases blast radius.
6, the trade-off nobody mentions.
1. Long-term monitoring increases data volume. 2. False positives may rise over time. 3. Investigation timelines become longer. 4. The benefit is disrupting stealth campaigns.
Follow-up 1, senior level. How do you detect delayed ransomware?
Answer: I look for persistence mechanisms, unusual scheduled tasks, and changes that survive reboots. Detection emphasizes longitudinal analysis. In interviews, the key signal is thinking beyond real-time alerts.
Follow-up 2, staff level. Why don't endpoint tools catch this earlier?
Answer: because dormant payloads do not exhibit malicious behavior. Without execution, signatures and heuristics remain silent. In interviews, explaining attacker patience demonstrates threat maturity.
Follow-up, curveball. What if delayed activation is unavoidable to detect?
Answer: then resilience must assume breach and focus on containment and recovery readiness at all times. In interviews, the correct response is designing for compromise, not perfection.
8, pro insider tip.
The most dangerous ransomware is the one that waits. In interviews, saying, "We monitor for long-lived persistence," signals advanced defensive thinking.
Real-world cybersecurity incident, number 57. EDR evasion using signed binaries.
Attackers executed ransomware preparation steps without triggering endpoint detection alerts by using digitally signed, trusted binaries already present on the system. No malicious executables were introduced. Every process appeared legitimate to security tooling.
1, the setup, everything looks secure.
Endpoints were protected by modern EDR solutions with up-to-date signatures and behavioral rules. Application allow listing was enabled, and unsigned binaries were blocked by policy.
2, what passed audits? security incidents that passed every audit.
Audits confirmed EDR deployment, signature currency, and enforcement of trusted publisher policies. The environment showed no unauthorized binaries or suspicious file hashes.
3. The breach, what failed anyway.
Attackers abused signed system utilities to disable protections, move laterally, and stage ransomware. Because the binaries were trusted and signed, EDR treated the activity as benign administration.
4. Where controls broke, diagnosis.
Security controls trusted publisher signatures more than execution context. The system assumed signed binaries would not be used maliciously, ignoring behavioral abuse.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Signed does not mean safe. 2. EDR trust models can be abused. 3. Behavior matters more than binary origin. 4. Attackers weaponize trusted tooling. 5. Detection must include intent analysis.
6. The trade-off nobody mentions.
1. Behavioral rules increase false positives. 2. Administrative workflows may be interrupted. 3. Security tuning requires domain expertise. 4. The benefit is visibility into stealthy attacks.
Follow-up 1. Senior level. How do you defend against signed binary abuse?
Answer: I shift detection from file reputation to behavior and sequence analysis. Even trusted tools must be constrained by expected usage patterns. In interviews, the key signal is distrust of implicit trust models.
Follow-up 2. Staff level. Why don't allow lists stop this?
Answer: allow lists prevent unknown binaries, not misuse of known ones. Attackers intentionally choose pre-approved tools. In interviews, explaining this limitation shows operational realism.
Follow-up curveball. What if security teams can't tune EDR deeply?
Answer: then compensating controls such as privilege restriction and execution auditing must be strengthened. Defense must assume some layers will be imperfect. In interviews, the correct response is layered resilience.
8. Pro insider tip.
Attackers love tools defenders trust. In interviews, saying, "We hunt misuse of signed binaries," signals advanced endpoint security experience.
Real-world cybersecurity incident number 58. Cloud workload encryption.
Ransomware operators encrypted cloud workloads directly at the infrastructure layer rather than deploying traditional malware. Virtual machines and attached storage were rendered unusable through legitimate cloud API operations. Every action was authenticated, authorized, and logged.
1. The setup. Everything looks secure.
The organization ran production workloads on cloud infrastructure, defined entirely through infrastructure as code. Access to cloud APIs was restricted to approved roles, and encryption at rest was already enabled by default.
2. What passed audits? Security incidents that passed every audit.
Audits verified encryption at rest, key management policies, and role-based access controls. No unauthorized API calls or configuration drift were detected during routine reviews.
3. The breach. What failed anyway?
After compromising valid cloud credentials, attackers re-encrypted workloads using attacker-controlled keys. Because the operations were legitimate API calls, cloud security tooling treated them as normal administrative activity.
4. Where controls broke, diagnosis.
The environment protected data at rest, but failed to protect encryption control paths. Key management operations were not isolated from general infrastructure administration.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Encryption is only as strong as key control. 2. Cloud APIs can be weaponized for ransomware. 3. Legitimate admin actions can destroy availability. 4. Key ownership defines data ownership. 5. Separation of key management is mandatory.
6. The trade-off nobody mentions.
1. Separating key management increases operational overhead. 2. Recovery workflows become more complex. 3. Access requests may slow down incident response. 4. The benefit is preventing infrastructure-level encryption attacks. Here is Terraform configuration showing how unrestricted key management enables cloud workload encryption by attackers. Disclaimer: always test code in a non-production environment. Here is the code snippet binding production storage to a broadly accessible KMS key. allowing any identity with key access to re-encrypt workloads. This code block shows encryption enabled, which protects data at rest but does not protect against malicious key rotation or replacement.
Follow-up 1, Senior Level. How do you prevent cloud-native ransomware like this?
Answer: I isolate key management behind tightly controlled roles and deny encryption changes from general infrastructure identities. Key operations require explicit approval paths. In interviews, the key signal is separating data protection from infrastructure control.
Follow-up 2, Staff Level. Why doesn't encryption at rest prevent this?
Answer: because encryption protects against disk theft, not malicious key control. Attackers who control keys control availability. In interviews, emphasizing key ownership shows cloud security depth.
Follow-up Curveball. What if separating KMS slows deployments?
Answer: then the organization must accept slower change in exchange for survivability. I frame key separation as blast radius containment. In interviews, the correct response is prioritizing recovery over speed.
8, Pro Insider Tip.
Cloud ransomware rarely installs malware. It revokes access through keys. In interviews, saying, "Who controls the keys controls recovery," signals real-world cloud incident experience.
Real-world cybersecurity incident number 59. Cross-environment lateral spread.
Ransomware spread from a lower trust environment into production without exploiting vulnerabilities or breaching perimeter defenses. The attacker authenticated once and pivoted across environments using shared identity and trust relationships. Every action was authorized and logged.
1. The setup. Everything looks secure.
The organization used multiple cloud environments for development, staging, and production. Infrastructure was managed through infrastructure as code, and access was controlled via centralized IAM policies.
2. What passed audits? Security incidents that passed every audit.
Audits verified environment separation, distinct accounts, and documented access controls. Shared roles and trust relationships were approved to reduce operational overhead.
3. The breach. What failed anyway?
An attacker compromised credentials in a development environment and assumed roles that were trusted by production. Because the trust was explicit and intended, the attacker moved laterally without triggering alarms.
4. Where controls broke. Diagnosis.
Environment boundaries existed on paper but not in identity design. Trust relationships collapsed isolation, allowing compromise to propagate across tiers.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Identity trust defines blast radius. 2. Environment separation must include IAM. 3. Shared roles defeat isolation guarantees. 4. Lower environments are attacker entry points. 5. Trust relationships require explicit threat modeling.
6. The trade-off nobody mentions.
1. Removing cross-CNV trust increases friction. 2. Deployments require more explicit approvals. 3. Operational convenience is reduced. 4. The benefit is containing compromise. Here is IAM Trust Policy JSON, showing how cross-environment role assumption enables ransomware spread. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing identities from another environment to assume this role, collapsing isolation boundaries. This code block trusts an entire external account, enabling any compromised identity in that environment to pivot into production.
Follow-up 1. Senior Level. How do you prevent cross-environment spread?
Answer: I eliminate broad trust relationships and require environment-specific identities with narrowly scoped permissions. Production never trusts lower environments implicitly. In interviews, the key signal is treating IAM as the primary isolation layer.
Follow-up 2. Staff Level. Why isn't network segmentation enough?
Answer: because IAM bypasses network boundaries entirely. If identity can cross environments, the network becomes irrelevant. In interviews, explaining this demonstrates cloud-native security understanding.
Follow-up Curveball. What if teams insist on shared roles for speed?
Answer: then leadership must explicitly accept the risk of full environment compromise. I present blast radius diagrams to make the impact clear. In interviews, the correct response is forcing visibility of the trade-off.
8. Pro Insider Tip.
Most cloud ransomware spreads through trust, not exploits. In interviews, saying identity is the real environment boundary signals senior cloud security experience.
Real-world cybersecurity incident number 60. Insider-assisted ransomware.
A ransomware incident succeeded not through technical exploitation, but through insider assistance. The insider did not deploy malware or bypass controls directly. Instead, they provided access, timing, and context that allowed attackers to operate with maximum effectiveness.
1. The setup. Everything looks secure.
The organization enforced MFA, used role-based access controls, and maintained strong perimeter defenses. Insider risk was considered low because employees were trusted, and access reviews were performed periodically.
2. What passed audits. Security incidents that passed every audit.
Audits verified access approvals, role assignments, and compliance with security policies. Insider threat programs existed on paper, but focused primarily on policy violations rather than behavioral indicators.
3. The breach. What failed anyway.
An insider shared credentials, access paths, or operational timing with external attackers. The attackers entered with full context, avoided detection, and disabled recovery mechanisms before deploying ransomware.
4. Where controls broke. Diagnosis.
Security controls assumed insiders were either fully trusted or fully malicious. There were no controls to detect gradual misuse, collusion, or assistance that stayed within nominal access boundaries.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Insider risk is not binary. 2. Trusted access can still be abused. 3. Context leakage amplifies attacker effectiveness. 4. Behavioral signals matter more than intent labels. 5. Defense must assume partial insider compromise.
6. The trade-off nobody mentions.
1. Insider monitoring raises privacy concerns. 2. False positives can erode trust. 3. Investigations require careful governance. 4. The benefit is early detection of collusion.
Follow-up 1. Senior level. How do you reduce insider-assisted ransomware risk?
Answer: I limit standing access, enforce just-in-time elevation, and monitor for behavioral anomalies rather than assuming trust. Insider risk programs must focus on misuse patterns. In interviews, the key signal is acknowledging insider complexity.
Follow-up 2. Staff level. Why don't traditional access reviews catch this?
Answer: because access reviews validate permission existence, not how access is used. Insiders can operate entirely within approved boundaries. In interviews, explaining this distinction shows operational maturity.
Follow-up curveball. What if leadership resists insider monitoring?
Answer: then risk must be explicitly accepted and documented. I advocate for proportional, transparent controls tied to high-risk actions. In interviews, the correct response is balancing trust with verification.
8. Pro insider tip.
The most damaging ransomware attacks often involve insiders who never touch malware. In interviews, saying, "We design for insider assistance, not just insider malice," signals senior security leadership.
Category 6 wrap-up. Ransomware and lateral movement.
Every ransomware incident in this category demonstrated that attackers rarely break in loudly. They authenticate, blend in, and expand impact through identity, recovery, and trust failures. Malware is the final step, not the root cause.
Transition from external attackers to insider threats.
So far, we assumed an external adversary abusing legitimate access. Now, we remove that assumption. Insider incidents occur when the threat actor already has access, context, and trust, making detection and response significantly harder.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs. cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 7. Insider threats.
Insider threats are not always malicious, and they are rarely obvious. These incidents involve employees, contractors, or support staff using valid access in unintended ways. The challenge is distinguishing normal behavior from harmful misuse without breaking trust or productivity.
Category 7. Insider threat scenarios we will cover.
In this category, we will examine the following real-world insider failure modes. 61. Excessive internal access misuse. 62. Accidental data sharing. 63. Credential reuse across systems. 64. Misuse of administrative tools. 65. Privilege creep over time. 66. Contractors with lingering access. 67. Shadow IT data leakage. 68. Data exfiltration via personal devices. 69. Abuse of customer support tools. 70. Insider-assisted fraud. Insider incidents succeed when trust outpaces containment.
Real-world cybersecurity incident number 61. Excessive internal access misuse.
Sensitive internal data was accessed and misused by an employee without bypassing controls or escalating privileges. The access was fully authorized, reviewed, and logged. The incident was discovered only after downstream business anomalies appeared.
1. The setup. Everything looks secure.
The employee had broad access to multiple internal systems due to role requirements and historical approvals. IAM policies were reviewed periodically, and access requests had documented business justification.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed that access was approved, roles were valid, and no privilege escalation occurred. Logs showed legitimate access patterns originating from known user accounts and devices.
3. The breach. What failed anyway.
The employee accessed data outside their operational need and used it for unintended purposes. Because the access fell within approved permissions, no alerts were triggered during the activity.
4. Where controls broke. Diagnosis.
Access controls enforced identity, but not purpose. Roles were designed for convenience and coverage rather than strict responsibility boundaries, expanding blast radius.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Authorized access can still be misused. 2. Roles must reflect responsibility, not convenience. 3. Blast radius applies to insiders as well. 4. Logging without intent detection is insufficient. 5. Containment matters more than trust.
6. The trade-off nobody mentions.
1. Narrower roles increase access requests. 2. Operational flexibility decreases. 3. Managers must actively own access decisions. 4. The benefit is limiting insider damage. Here is IAM policy JSON, showing how broad internal roles enable insider misuse without policy violations. Disclaimer: always test code in a non-production environment. Here is the code snippet granting access across all resources, expanding blast radius even when actions are legitimate. This code block shows a single role bundling unrelated permissions, allowing misuse without escalation.
Follow-up 1. Senior level. How do you prevent excessive insider access misuse?
Answer: I redesign roles around single responsibilities and enforce regular permission pruning. Access is granted for what a role does today, not what it might need later. In interviews, the key signal is prioritizing blast radius reduction.
Follow-up 2, staff level. Why don't access reviews catch this earlier?
Answer: because access reviews validate justification, not behavior. Insiders can misuse access long after approval. In interviews, explaining this distinction shows real-world governance experience.
Follow-up, curveball. What if teams complain about too many roles?
Answer: then the organization must decide between convenience and containment. I frame role sprawl as a resilience cost. In interviews, the correct response is acknowledging friction without dismissing risk.
8, pro insider tip.
Most insider incidents involve valid access, not privilege escalation. In interviews, replacing least privilege with blast radius reduction signals mature insider risk thinking.
Real-world cybersecurity incident, number 62. Accidental data sharing by trusted employees.
Sensitive internal data was exposed without malicious intent, compromised credentials, or policy violations. A trusted employee shared information through an approved collaboration channel, unaware that the audience scope exceeded what was appropriate.
1, the setup, everything looks secure.
The organization used approved collaboration tools for file sharing and communication. Access controls were enforced, data classification policies existed, and employees received periodic security awareness training.
2, what passed audits? Security incidents that passed every audit.
Audits confirmed that collaboration tools were approved, access was authenticated, and sharing actions complied with documented policies. No external sharing rules were violated.
3, the breach, what failed anyway?
An employee shared a document containing sensitive data with a broader internal group than intended. The data propagated organically through forwarding and downloads before the mistake was noticed.
4, where controls broke, diagnosis.
Controls focused on access authorization, not audience awareness. The system assumed users would correctly understand visibility scope and data sensitivity during sharing actions.
5, the interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Most data leaks are accidental, not malicious. 2. Authorization does not equal appropriateness. 3. Sharing interfaces influence user behavior. 4. Audience scope must be explicit and visible. 5. Prevention requires guardrails, not blame.
6, the trade-off nobody mentions.
1. Additional prompts slow down collaboration. 2. Users may experience alert fatigue. 3. Overclassification can reduce usability. 4. The benefit is preventing silent data spread.
Follow-up 1, senior level. How do you reduce accidental data sharing?
Answer: I implement contextual warnings, default restrictive sharing, and real-time visibility of audience scope. Controls should guide users at the moment of action. In interviews, the key signal is designing for human error.
Follow-up 2, staff level. Why doesn't training alone prevent this?
Answer: because training cannot override interface-driven mistakes under time pressure. Systems must be resilient to normal human behavior. In interviews, explaining this shows practical security thinking.
Follow-up, curveball. What if users complain about too many warnings?
Answer: then warnings must be risk-based and contextual, not constant. I focus friction on high-sensitivity data only. In interviews, the correct response is balancing usability with protection.
8, pro insider tip.
Most insider leaks are mistakes made under pressure. In interviews, saying, "We design for accidental misuse," signals real-world insider risk maturity.
Real-world cybersecurity incident, number 63. Credential reuse across internal systems.
An insider incident occurred without phishing, malware, or brute force attacks. A single set of credentials was reused across multiple internal systems. When one system was compromised, the attacker gained access to several others without additional effort.
1, the setup, everything looks secure.
The organization used centralized identity with single sign-on for employee convenience. Password complexity and MFA were enforced, and credential reuse was discouraged through policy.
2, what passed audits? Security incidents that passed every audit.
Audits verified MFA enforcement, password policies, and SSO configuration. Individual applications complied with authentication standards, and no login anomalies were detected.
3. The breach, what failed anyway.
An attacker obtained valid credentials through a compromised endpoint. Because the same credentials granted access across multiple systems, the attacker pivoted laterally without triggering additional authentication challenges.
4. Where controls broke, diagnosis.
Identity controls optimized for convenience over containment. Credential reuse collapsed isolation boundaries between systems, turning a single compromise into a multi-system incident.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. SSO reduces friction but increases blast radius. 2. Credential reuse creates implicit trust links. 3. Authentication success is not containment. 4. Isolation must exist beyond login. 5. Identity design defines lateral movement.
6. The trade-off nobody mentions.
1. Reducing credential reuse increases login friction. 2. Users may resist additional authentication steps. 3. Application integration becomes more complex. 4. The benefit is limiting compromise propagation.
Follow-up 1. Senior level. How do you mitigate risks of credential reuse?
Answer: I combine SSO with strong session isolation, conditional access, and step-up authentication for sensitive systems. A single credential should not grant uniform access everywhere. In interviews, the key signal is separating convenience from containment.
Follow-up 2. Staff level. Why doesn't MFA fully solve credential reuse?
Answer: MFA protects authentication events, not post-authentication access scope. Once authenticated, reused credentials still enable lateral movement. In interviews, explaining this distinction shows real-world identity experience.
Follow-up curveball. What if leadership mandates universal SSO?
Answer: then additional segmentation and conditional access must be layered on top. Universal SSO without containment is a single point of failure. In interviews, the correct response is acknowledging mandates while mitigating risk.
8. Pro insider tip.
Credential reuse turns identity into an attack highway. In interviews, saying SSO increases blast radius if not segmented signals mature identity architecture thinking.
Real-world cybersecurity incident. Number 64. Misuse of administrative tools by insiders.
A trusted administrator caused significant business impact without exploiting vulnerabilities or bypassing controls. The incident involved legitimate use of an internal admin tool in a way that exceeded operational intent. Every action was authenticated, authorized, and logged.
1. The setup. Everything looks secure.
The organization provided administrators with powerful internal tools to manage users, data, and system state. Access was restricted to approved roles, MFA was enforced, and usage was audited for compliance.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that only authorized admins could access the tool, actions were logged, and no privilege escalation occurred. The tool itself was considered trusted and exempt from fine-grained authorization reviews.
3. The breach. What failed anyway?
An administrator used bulk operations within the tool to perform actions far outside normal workflows. Because the tool allowed broad operations by design, misuse went undetected until downstream effects appeared.
4. Where controls broke, diagnosis.
The system enforced who could use the tool but not how it should be used. Administrative power was bundled without intent checks, guardrails, or anomaly detection.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Admin tools are high-risk applications. 2. Authorization must include intent and scope. 3. Bulk actions amplify insider blast radius. 4. Logging without guardrails is insufficient. 5. Admin power must be constrained by design.
6. The trade-off nobody mentions.
1. Adding guardrails slows administrative workflows. 2. Bulk operations become more complex to approve. 3. Admins may perceive reduced autonomy. 4. The benefit is preventing catastrophic misuse. Here is Java admin tool logic showing how missing scope checks allow destructive bulk operations by trusted users. Disclaimer: Always test code in a non-production environment. Here is the code snippet exposing a bulk administrative operation without validating intent, scope, or approval context. This code block executes a high-impact action repeatedly, amplifying damage when misused by a trusted admin.
Follow-up 1, Senior Level. How do you secure administrative tools?
Answer: I add explicit scope limits, approval workflows, and anomaly detection to admin actions. High-impact operations require additional verification. In interviews, the key signal is treating admin tools as attack surfaces.
Follow-up 2, Staff Level. Why aren't logs enough here?
Answer: logs are forensic, not preventative. By the time misuse is reviewed, damage is already done. In interviews, explaining prevention versus detection shows maturity.
Follow-up, Curveball. What if admins push back on restrictions?
Answer: then leadership must decide how much risk admin convenience justifies. I present misuse scenarios to make risk concrete. In interviews, the correct response is acknowledging power-risk trade-offs.
8, Pro Insider Tip.
Most insider disasters involve admin tools doing exactly what they were built to do. In interviews, saying admin tools need guardrails signals real-world insider threat experience.
Real-world cybersecurity incident, number 65. Privilege creep over time.
An insider incident emerged gradually rather than through a single action. Over multiple role changes and project transitions, an employee accumulated permissions far beyond current responsibilities. No individual change appeared risky, but the aggregate access created significant exposure.
1, The setup. Everything looks secure.
The organization used role-based access control with formal approval workflows. Access was granted incrementally as employees moved between teams, and removals were handled manually during transitions.
2, What passed audits? Security incidents that passed every audit.
Audits reviewed individual access grants and confirmed approvals existed. No single permission violated policy, and each role assignment had a valid historical justification.
3, The breach. What failed anyway?
The employee leveraged accumulated access to view and manipulate data across multiple systems unrelated to their current role. Because access was built up over time, the misuse did not appear anomalous in isolation.
4, Where controls broke. Diagnosis.
Access governance focused on additions, not removals. There was no systematic enforcement of least responsibility or periodic pruning tied to current job function.
5, The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Privilege creep is cumulative risk. 2. Historical approvals outlive business need. 3. Least privilege must be enforced continuously. 4. Access removal is harder than access grant. 5. Governance must track effective permissions.
6, The trade-off nobody mentions.
1. Automated access removal can disrupt workflows. 2. Managers must actively revalidate permissions. 3. Role redesign requires organizational effort. 4. The benefit is long-term insider risk reduction. Here is IAM policy JSON showing how accumulated permissions enable privilege creep without explicit escalation. Disclaimer: always test code in a non-production environment. Here is the code snippet showing unrelated permissions accumulated into a single identity over time, expanding effective capability. This code block demonstrates how broad resource scope magnifies the impact of gradual permission accumulation.
Follow-up 1, Senior Level. How do you prevent privilege creep?
Answer: I enforce time-bound access and periodic revalidation tied to current role responsibilities. Permissions expire unless explicitly renewed. In interviews, the key signal is designing for removal, not just approval.
Follow-up 2, Staff Level. Why don't quarterly access reviews catch this?
Answer: because reviews often validate ownership, not necessity. Reviewers approve what already exists to avoid disruption. In interviews, explaining review fatigue shows governance realism.
Follow-up, Curveball. What if automated removal breaks production?
Answer: then access models are too tightly coupled to individuals. I redesign roles to align with stable responsibilities. In interviews, the correct response is fixing structure, not disabling controls.
8, Pro Insider Tip.
Privilege creep is invisible until it isn't. In interviews, saying, "We design access to decay over time," signals mature insider risk management.
Real-world cybersecurity incident number 66. Contractors with lingering access.
A security incident originated from an external contractor whose access was never fully revoked after their engagement ended. No credentials were stolen and no controls were bypassed. The access remained valid, approved, and unnoticed long after the contract expired.
1. The setup. Everything looks secure.
The organization used contractors for short-term projects and granted them access through standard IAM roles. Access requests were approved by managers, and contractor accounts were clearly labeled in identity systems.
2. What passed audits? Security incidents that passed every audit.
Audits verified that contractor access was approved and documented at the time of onboarding. There were no active projects flagged as requiring immediate offboarding actions.
3. The breach. What failed anyway?
Months after the contract ended, the contractor's credentials were used to access internal systems. Because the account was still valid and rarely used, the activity blended into normal background noise.
4. Where controls broke. Diagnosis.
Offboarding relied on manual processes and human memory rather than automated enforcement. There was no hard linkage between contract end dates and access expiration.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Temporary access must be technically temporary. 2. Human-driven offboarding does not scale. 3. Dormant accounts are high-risk identities. 4. Access expiration should be automatic. 5. Contractor identity must be lifecycle bound.
6. The trade-off nobody mentions.
1. Automated expiration can interrupt extended engagements. 2. Managers must actively renew access. 3. Identity systems require tighter HR integration. 4. The benefit is eliminating forgotten access paths. Here is IAM policy JSON showing how contractor access without expiration enables long-term insider exposure. Disclaimer: always test code in a non-production environment. Here is the code snippet granting baseline read access that appears low risk, but becomes dangerous when it persists indefinitely. This code block shows unrestricted resource scope, allowing lingering contractor access across the environment.
Follow-up 1. Senior level. How do you enforce contractor offboarding reliably?
Answer: I bind access expiration directly to contract end dates and require explicit renewal for extensions. Offboarding should be automatic by default. In interviews, the key signal is removing reliance on memory and manual cleanup.
Follow-up 2. Staff level. Why don't periodic access reviews catch this?
Answer: because reviews often focus on active employees and critical roles. Dormant contractor accounts are easy to overlook. In interviews, explaining review blind spots shows governance maturity.
Follow-up curveball. What if a contractor needs ad hoc access after offboarding?
Answer: then access should be granted through temporary, auditable reactivation with clear ownership. Permanent access for convenience is unacceptable. In interviews, the correct response is prioritizing lifecycle control.
8. Pro insider tip.
Most contractor incidents are caused by access that should no longer exist. In interviews, saying contractor access always expires by default signals strong identity lifecycle discipline.
Real-world cybersecurity incident number 67. Shadow IT data leaks.
Sensitive business data was exposed without breaching perimeter defenses, compromising credentials, or bypassing controls. Employees used unapproved tools to store and share information for convenience. The data left managed environments without triggering security alerts.
1. The setup. Everything looks secure.
The organization had approved SaaS platforms, enforced SSO, and deployed data loss prevention on managed systems. Policies prohibited the use of unapproved tools, and employees received periodic security training.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed compliance with approved tooling lists, DLP deployment, and access controls. No sanction system showed signs of data leakage or unauthorized sharing.
3. The breach. What failed anyway?
Employees uploaded sensitive documents to personal cloud storage and unapproved collaboration tools to work faster. Because the tools were outside managed visibility, Data left the organization silently.
4. Where controls broke, diagnosis.
Security controls assumed work would occur inside approved platforms. There were limited guardrails to prevent or detect data movement into unmanaged applications.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Shadow IT emerges from productivity gaps. 2. Policy alone does not stop convenience-driven behavior. 3. Visibility ends at managed boundaries. 4. Data protection must follow the data. 5. Blocking without alternatives increases risk.
6. The trade-off nobody mentions.
1. Restricting tools frustrates employees. 2. Monitoring cloud apps raises privacy concerns. 3. False positives increase with broad visibility. 4. The benefit is preventing silent data loss.
Follow-up 1. Senior level. How do you control shadow IT without breaking productivity?
Answer: I focus on providing secure, usable alternatives and monitoring data flows rather than blanket bans. Controls must align with how people actually work. In interviews, the key signal is reducing shadow IT demand, not just enforcing policy.
Follow-up 2. Staff level. Why doesn't DLP catch this?
Answer: because DLP is often limited to managed endpoints and approved applications. Once data moves outside that scope, visibility drops sharply. In interviews, explaining control boundaries shows operational realism.
Follow-up curveball. What if leadership resists restricting tools?
Answer: then the risk must be acknowledged and mitigated through monitoring, education, and compensating controls. Ignoring shadow IT does not make it safer. In interviews, the correct response is making invisible risk visible.
8. Pro insider tip.
Shadow IT exists because official tools don't meet real needs. In interviews, saying, "We compete with shadow IT on usability," signals mature insider risk management.
Real-world cybersecurity incident. Number 68. Data exfiltration via personal devices.
Sensitive corporate data was exfiltrated without malware, privilege escalation, or external intrusion. An employee accessed data using valid credentials and transferred it to a personal device for convenience. The activity remained within approved access boundaries and evaded detection.
1. The setup. Everything looks secure.
The organization supported remote work and allowed personal devices under a bring-your-own-device policy. Access controls, MFA, and endpoint security were enforced on corporate managed systems.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed authentication controls, acceptable use policies, and secure access to internal systems. Personal devices were permitted for certain workflows and considered low risk.
3. The breach. What failed anyway?
An employee downloaded sensitive files to a personal device to work offline and later shared them externally. Because the access and download were authorized, no alerts were triggered during the transfer.
4. Where controls broke, diagnosis.
Controls focused on access authentication, but not on data movement after access. The organization lacked visibility and enforcement once data left managed environments.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Access does not equal permission to extract. 2. Personal devices break containment assumptions. 3. Data must remain protected after access. 4. Visibility ends where management ends. 5. Policies must be enforced technically.
6. The trade-off nobody mentions.
1. Restricting downloads impacts remote productivity. 2. Device management increases employee friction. 3. Privacy considerations complicate monitoring. 4. The benefit is preventing silent data loss.
Follow-up 1. Senior level. How do you prevent data exfiltration to personal devices?
Answer: I restrict sensitive data access to managed environments and enforce view-only or virtual access when necessary. Data should not be portable by default. In interviews, the key signal is designing for containment beyond authentication.
Follow-up 2. Staff level. Why don't access logs detect this?
Answer: logs show who accessed data, not what happened after download. Once data leaves managed systems, visibility drops. In interviews, explaining this boundary shows real-world data protection awareness.
Follow-up curveball. What if leadership insists on BYOD flexibility?
Answer, then compensating controls such as containerization and data virtualization must be applied. Flexibility without containment is an accepted risk. In interviews, the correct response is balancing usability with enforceable controls.
8. Pro insider tip.
Most insider data theft looks like legitimate work activity. In interviews, saying, "We assume data will be copied unless prevented," signals practical insider risk experience.
Real-world cybersecurity incident number 69. Abuse of customer support tools.
Sensitive customer accounts were accessed and modified without exploiting vulnerabilities or bypassing authentication. A support agent used a trusted internal tool to perform actions beyond legitimate support intent. All actions were authorized, logged, and appeared routine.
1. The setup. Everything looks secure.
Customer support agents were granted access to internal tools to reset passwords, update profiles, and assist with account recovery. Access was role-based, MFA was enforced, and all actions were audited.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that only support roles could access the tool, actions were logged, and workflows matched documented support procedures. No privilege escalation or unauthorized access paths were identified.
3. The breach. What failed anyway?
A support agent used legitimate workflows to access high-value accounts and perform repeated actions unrelated to active support tickets. Because the actions were allowed and common, detection systems did not flag the behavior.
4. Where controls broke. Diagnosis.
The tool validated role membership but not business context. There was no linkage between support actions and active tickets, customer consent, or anomaly thresholds.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Support tools are privileged systems. 2. Authorization must include business context. 3. Valid roles can still be misused. 4. High-value accounts require additional controls. 5. Abuse looks identical to normal operations.
6. The trade-off nobody mentions.
1. Context validation slows support workflows. 2. Agents face additional verification steps. 3. False positives may increase initially. 4. The benefit is preventing insider-enabled fraud. Here is Java support tool logic showing how missing ticket and intent validation enables abuse of legitimate customer operations. Disclaimer: always test code in a non-production environment. Here is the code snippet exposing a powerful support action without validating ticket context or customer consent. This code block performs a high-impact operation that can be repeatedly abused when intent is not enforced.
Follow-up 1. Senior level. How do you secure customer support tools?
Answer: I bind sensitive actions to active tickets, enforce reason codes, and add anomaly detection for high-risk accounts. Support access must be contextual, not blanket. In interviews, the key signal is treating support tools as privileged systems.
Follow-up 2. Staff level. Why don't audits catch this misuse?
Answer: audits validate access and logging, not intent or behavior patterns. Abuse occurs within approved workflows. In interviews, explaining this gap shows operational security depth.
Follow-up curveball. What if support leadership resists added friction?
Answer: then the risk must be explicitly accepted for high-impact actions only. I prioritize protections around sensitive accounts first. In interviews, the correct response is risk-based control placement.
8. Pro insider tip.
Support tools are a common insider attack surface because misuse looks like help. In interviews, saying support actions require business context signals senior insider risk awareness.
Real-world cybersecurity incident number 70. Insider-assisted fraud.
A large-scale fraud incident occurred without breaching systems, exploiting vulnerabilities, or bypassing controls. An insider knowingly assisted an external actor by using valid access and trusted workflows to manipulate outcomes for financial gain.
1. The setup. Everything looks secure.
The organization enforced strong authentication, role-based access control, and transaction logging. Employees had access aligned to job responsibilities, and fraud detection focused on external attackers.
2. What passed audits? security incidents that passed every audit.
Audits verified access controls, approvals, and segregation of duties on paper. Transactions followed documented workflows, and no technical policy violations were detected.
3. The breach, what failed anyway.
An employee coordinated with an external party to initiate and approve fraudulent transactions using legitimate processes. Because each step appeared valid in isolation, the activity evaded real-time detection.
4. Where controls broke, diagnosis.
Controls assumed employees acted independently and honestly. There were limited safeguards against collusion, pattern-based abuse, or insider external coordination.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Fraud often exploits trust, not technology. 2. Segregation of duties fails under collusion. 3. Valid workflows can still produce invalid outcomes. 4. Detection must focus on patterns, not permissions. 5. Insider risk extends beyond accidental misuse.
6. The trade-off nobody mentions.
1. Behavioral monitoring raises privacy concerns. 2. False positives can strain trust with employees. 3. Fraud controls add friction to legitimate workflows. 4. The benefit is preventing systemic financial loss.
Follow-up 1. Senior level. How do you detect insider-assisted fraud?
Answer: I focus on cross-user pattern analysis, transaction sequencing, and unusual approval correlations. Controls must assume the possibility of collusion. In interviews, the key signal is shifting from rule-based to behavior-based detection.
Follow-up 2. Staff level. Why don't traditional access controls stop this?
Answer: because access controls enforce permission, not honesty. Insiders already have what they need. In interviews, explaining this distinction demonstrates real-world fraud awareness.
Follow-up, curveball. What if leadership fears employee monitoring backlash?
Answer: then the organization must define clear governance, transparency, and proportional controls. Ignoring insider fraud risk is itself a business decision. In interviews, the correct response is balancing ethics with risk management.
8. Pro insider tip.
The most damaging fraud incidents involve insiders who never break rules. In interviews, saying, "We design controls assuming collusion," signals senior-level fraud and insider threat maturity.
Category 7 wrap-up, insider threats.
Across these incidents, the common failure was not broken controls, but misplaced trust. Insiders operated entirely within approved boundaries, using systems exactly as designed. The lesson is clear: security must assume misuse even when access is valid.
Transition from insider trust to observability failures.
Insider incidents are hard to detect because activity looks legitimate. Observability failures make this problem worse. When visibility is reduced or incomplete, misuse, internal or external, persists longer and causes deeper damage.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's Why given 50 question and answers for each section? These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 8. Observability and monitoring failures.
Observability failures do not create breaches, but they allow them to survive. These incidents occur when logging, monitoring, and detection systems are missing, misconfigured, or ignored. In senior interviews, this category separates theoretical security from operational reality.
Category 8. Observability and monitoring incidents we will cover.
In this category, we will analyze the following real-world visibility failures. 71. Logs disabled to reduce cost. 72. Sensitive data written to logs. 73. Alert fatigue masking real incidents. 74. Missing audit trails. 75. Log tampering after compromise. 76. SIM blind spots. 77. Metric overaggregation hiding anomalies. 78. No correlation across systems. 79. Short log retention periods. 80. No integrity validation on logs. Security without observability is theater.
Real-world cybersecurity incident number 71. Logs disabled to save cost.
A breach persisted for weeks without detection because critical logs were disabled in production. No alerts fired, no investigations began, and no anomalies were visible. The incident was discovered only after customer impact forced a manual review.
1. The setup. Everything looks secure.
The organization used cloud-native infrastructure with centralized logging services available. Cost controls were in place, and teams were encouraged to optimize usage of observability tooling.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that logging services existed and could be enabled. Security tooling was deployed in lower environments, and logging configurations were reviewed at a high level.
3. The breach. What failed anyway?
To reduce operational cost, detailed logs were disabled in production. When malicious activity occurred, there was no telemetry to detect, investigate, or scope the incident.
4. Where controls broke. Diagnosis.
Observability was treated as optional overhead rather than a security control. Cost optimization decisions were made without understanding the security impact of reduced visibility.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Logs are a security control, not a debugging aid. 2. You cannot detect what you do not record. 3. Cost optimization without risk context creates blind spots. 4. Production visibility is non-negotiable. 5. Incident response depends on historical telemetry.
6. The trade-off nobody mentions.
1. Comprehensive logging increases cloud spend. 2. Storage and ingestion costs grow quickly. 3. Teams must tune log volume carefully. 4. The benefit is reduced breach dwell time. Here is Terraform configuration showing how disabling production logging creates complete detection blind spots. Disclaimer: always test code in a non-production environment. Here is the code snippet configuring extremely short log retention, effectively erasing historical evidence before incidents are discovered. This code block shows logging technically enabled, but operationally useless due to retention choices.
Follow-up 1. Senior level. How do you balance logging cost versus security?
Answer: I treat security-critical logs as mandatory and optimize volume through filtering, not deletion. Cost decisions must include incident response impact. In interviews, the key signal is framing observability as risk management.
Follow-up 2. Staff level. Why didn't audits flag this earlier?
Answer: because audits often check for existence, not effectiveness. Logging was technically present. In interviews, explaining this gap shows operational audit experience.
Follow-up. Curveball. What if leadership demands aggressive cost cuts?
Answer: then the security impact must be documented and accepted explicitly. Blind spots are a business risk. In interviews, the correct response is making trade-offs visible, not silent.
8. Pro insider tip.
Most breaches last longer than log retention. In interviews, saying, "We log for investigations, not dashboards," signals real-world observability maturity.
Real-world cybersecurity incident number 72. sensitive data written to application logs.
Sensitive customer information was exposed through internal log files without any external breach or privilege escalation. The application behaved correctly from a functional perspective, but logged more data than intended. Logs became a secondary data store for secrets.
1. The setup. Everything looks secure.
The application used structured logging, centralized log aggregation, and role-based access to observability platforms. Logs were considered internal only and were heavily relied upon for debugging and support.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed access controls on log systems, encryption at rest, and secure transport. No production databases were exposed, and application access controls were functioning as designed.
3. The breach. What failed anyway?
Application logs captured sensitive fields such as tokens, personal identifiers, and request payloads. Users with legitimate log access were able to view data far beyond their operational need.
4. Where controls broke. Diagnosis.
Logging was treated as harmless metadata rather than sensitive data handling. Developers logged full objects for convenience, assuming logs were low risk and tightly controlled.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Logs are data stores with wide access. 2. Sensitive data spreads faster through logs than databases. 3. Debug convenience creates long-term exposure. 4. Redaction must happen before logging. 5. Observability pipelines require data governance.
6. The trade-off nobody mentions.
1. Redacted logs reduce debugging detail. 2. Developers need better tooling for safe inspection. 3. Retroactive cleanup of logs is difficult. 4. The benefit is preventing silent data exposure. Here is Java logging logic showing how full request logging exposes sensitive data beyond intended access. Disclaimer: always test code in a non-production environment. Here is the code snippet logging the entire request object, which often includes credentials or tokens. This code block shows logging placed at the application boundary, causing sensitive input data to persist in logs.
Follow-up 1. Senior level. How do you prevent sensitive data from leaking into logs?
Answer: I enforce structured logging with explicit field allow lists and automatic redaction libraries. Developers should never log raw request objects. In interviews, the key signal is treating logs as sensitive assets.
Follow-up 2. Staff level. Why isn't access control on logs enough?
Answer: because log access is broader than database access and often includes support and operations teams. Once sensitive data is logged, it spreads quickly. In interviews, explaining access surface expansion shows maturity.
Follow-up curveball. What if developers insist on detailed logs for debugging?
Answer: then debugging must occur in controlled environments with synthetic data. Production logs should be safe by default. In interviews, the correct response is separating debugging needs from production risk.
8. Pro insider tip.
If sensitive data appears in logs, assume it has been widely copied. In interviews, saying logs are high-risk data stores signals real-world observability and privacy experience.
Real-world cybersecurity incident number 73. Alert fatigue masking real incidents.
A genuine security breach went undetected for an extended period because it was buried among thousands of low-quality alerts. Monitoring systems were functioning, alerts were firing, and dashboards were full. The failure was not lack of signals, but an excess of noise.
1. The setup. Everything looks secure.
The organization deployed multiple monitoring tools, SIM rules, and automated alerts across infrastructure and applications. Alerting thresholds were configured conservatively to avoid missing potential issues.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that alerts were configured, incidents were tracked, and on-call rotations existed. Alert coverage appeared comprehensive, and response procedures were documented.
3. The breach. What failed anyway?
A high-severity security signal was generated but ignored because it resembled dozens of routine alerts. Analysts dismissed it as another false positive, allowing the attacker to continue operating undetected.
4. Where controls broke. Diagnosis.
Alerting prioritized quantity over quality. There was no effective prioritization, suppression, or correlation to distinguish genuine threats from background noise.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Alert fatigue is a system design failure. 2. Humans cannot compensate for noisy automation. 3. Severity must be meaningful, not theoretical. 4. Detection quality matters more than coverage. 5. Security teams must design for attention.
6. The trade-off nobody mentions.
1. Reducing alerts risks missing rare events. 2. Tuning rules requires deep system knowledge. 3. Initial blind spots may appear during cleanup. 4. The benefit is faster response to real threats.
Follow-up 1. Senior level. How do you reduce alert fatigue without increasing risk?
Answer: I focus on alerting only on actionable conditions and suppress known benign patterns. Correlation and context reduce noise more effectively than thresholds alone. In interviews, the key signal is designing alerts for human response.
Follow-up 2. Staff level. Why don't more alerts make systems safer?
Answer: because human attention is finite. Excessive alerts degrade response quality and trust in the system. In interviews, explaining cognitive limits shows operational maturity.
Follow-up curveball. What if leadership demands 0 missed alerts?
Answer: then expectations must be reset around trade-offs. 0 misses with 0 fatigue is unrealistic. In interviews, the correct response is articulating human and system limits clearly.
8. Pro insider tip.
The most dangerous alerts are the ones people stop believing. In interviews, saying, "We alert for action, not awareness," signals real-world detection engineering experience.
Real-world cybersecurity incident number 74. Missing audit trails for sensitive actions.
A security incident could not be fully investigated because critical actions were never recorded. Systems functioned correctly, users were authorized, and business workflows completed successfully. When questions arose, there was no reliable history to reconstruct what actually happened.
1. The setup. Everything looks secure.
The application enforced authentication and role-based authorization for sensitive operations. Logging existed for errors and performance metrics, and operational dashboards showed healthy system behavior.
2. What passed audits? Security incidents that passed every audit.
Audits verified access controls, code reviews, and change management processes. The application met functional requirements, and no failures were observed during routine testing.
3. The breach. What failed anyway?
A sensitive administrative action was performed, leading to downstream impact. When investigators attempted to trace the action, there was no audit record identifying who performed it, when it occurred, or from where.
4. Where controls broke. Diagnosis.
The system enforced access but did not enforce accountability. Audit logging was optional, inconsistently applied, and omitted for high-risk operations that developers assumed were rare.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Authorization without auditability is incomplete security. 2. Sensitive actions must always be attributable. 3. Rare operations are often the most dangerous. 4. Audit trails enable investigation, not prevention. 5. Security failures compound when history is missing.
6. The trade-off nobody mentions.
1. Comprehensive auditing increases log volume. 2. Developers must design audit schemas intentionally. 3. Retroactive reconstruction is impossible without logs. 4. The benefit is accountability during incidents. Here is Java application logic showing how missing audit logging allows sensitive actions to occur without accountability. Disclaimer: always test code in a non-production environment. Here is the code snippet defining a high-impact operation without any audit context, such as actor identity or request source. This code block commits a sensitive state change with no accompanying audit record, making post-incident investigation impossible.
Follow-up 1. Senior level. What actions require mandatory audit trails?
Answer: any operation that changes security posture, access rights, financial state, or customer data must be audited by default. I assume every rare action will eventually be investigated. In interviews, the key signal is prioritizing accountability.
Follow-up 2. Staff level. Why can't database logs replace application audits?
Answer: database logs lack business context such as intent, actor role, and request origin. Application-level audits provide semantic meaning. In interviews, explaining this distinction shows system-level thinking.
Follow-up curveball. What if teams forget to add audit logs?
Answer: then auditing must be enforced through shared libraries or frameworks, not developer discipline. Security controls should be hard to omit. In interviews, the correct response is building guardrails into platforms.
8. Pro insider tip.
If you can't answer who did what and when, you don't have security. In interviews, saying, "We treat audit logs as first-class data," signals real-world operational maturity.
Real-world cybersecurity incident number 75. Log tampering after compromise.
An attacker modified and deleted logs after gaining access, obscuring the true scope and timeline of the breach. No alerts were triggered during the tampering because logging systems trusted the same environment that was already compromised.
1. The setup. Everything looks secure.
The organization centralized logs and restricted access through role-based permissions. Logs were writable by applications and administrators, and log access was considered an internal-only concern.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed logging was enabled, retention policies existed, and access to log systems was restricted. No controls explicitly prevented modification or deletion by privileged users.
3. The breach. What failed anyway?
After compromising a privileged account, the attacker altered and deleted logs to remove traces of activity. Investigators later found gaps and inconsistencies that prevented accurate reconstruction of events.
4. Where controls broke. Diagnosis.
Logging systems trusted the same identities and infrastructure as production workloads. There was no immutability, externalization, or integrity protection for logs.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Logs must be protected from the systems they observe. 2. Write access enables evidence destruction. 3. Integrity matters more than availability for logs. 4. Post-compromise controls are still security controls. 5. Assume attackers will clean up after themselves.
6. The trade-off nobody mentions.
1. Immutable logging increases storage cost. 2. Operational flexibility is reduced. 3. Incident response workflows must adapt. 4. The benefit is trustworthy forensic evidence.
Follow-up 1. Senior level. How do you prevent log tampering?
Answer: I externalize logs to immutable storage and enforce append-only access with integrity validation. Logging must survive a full system compromise. In interviews, the key signal is separating observation from execution.
Follow-up 2. Staff level. Why isn't access control sufficient?
Answer: because attackers often gain privileged access. Once inside, access control alone cannot protect evidence. In interviews, explaining post-compromise assumptions shows maturity.
Follow-up curveball. What if immutable logging is too expensive?
Answer: then the organization must accept reduced forensic confidence. I prioritize immutability for high-risk systems first. In interviews, the correct response is risk-based deployment.
8. Pro insider tip.
If attackers can edit logs, logs are not evidence. In interviews, saying logs must be tamper-resistant signals senior incident response experience.
Real-world cybersecurity incident number 76. SIM blind spots from incomplete log ingestion.
A security incident went undetected because critical telemetry never reached the SIM. Logs existed, systems were functioning, and alerts were configured. The failure was incomplete ingestion, not missing events.
1. The setup. Everything looks secure.
The organization deployed a centralized SIM with multiple data sources onboarded. Infrastructure and application teams assumed that enabling logging automatically meant visibility inside the SIM.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed the SIM was operational, dashboards were populated, and alerts existed. A sample of sources showed successful ingestion, creating a false sense of completeness.
3. The breach. What failed anyway?
High-risk systems were never onboarded to the SIM due to misconfiguration. Malicious activity occurred entirely within these blind spots, generating logs that no one ever saw.
4. Where controls broke, diagnosis.
Visibility assumptions replaced verification. There was no enforcement or validation that all required log sources were actually ingested and parsed correctly by the SIM.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. A SIM is only as good as its inputs. 2. Missing telemetry creates silent failure modes. 3. Onboarding is a security control, not a setup task. 4. Verification matters more than dashboards. 5. Blind spots persist until explicitly tested.
6. The trade-off nobody mentions.
1. Full ingestion increases licensing costs. 2. Parsing and normalization require ongoing effort. 3. False confidence must be actively challenged. 4. The benefit is eliminating undetected attack paths. Here is Terraform configuration showing how missing log subscriptions create SIM blind spots, despite enabled logging. Disclaimer: always test code in a non-production environment. Here is the code snippet showing a single log group explicitly forwarded, leaving all other production logs invisible to the SIM. This code block demonstrates that SIM visibility is opt-in per log group, creating easy-to-miss ingestion gaps.
Follow-up 1. Senior level. How do you eliminate SIM blind spots?
Answer: I enforce mandatory onboarding for all security-relevant log sources and continuously validate ingestion coverage. Visibility is verified through testing, not assumed. In interviews, the key signal is treating ingestion as a control.
Follow-up 2. Staff level. Why don't dashboards reveal blind spots?
Answer: dashboards show what is present, not what is missing. Absence is invisible without explicit checks. In interviews, explaining negative space monitoring shows operational depth.
Follow-up curveball. What if SIM costs limit ingestion?
Answer: then risk-based prioritization is required, but blind spots must be documented and tested. Cost constraints do not remove responsibility. In interviews, the correct response is explicit risk acceptance.
8. Pro insider tip.
If a system is not in the SIM, it does not exist during an incident. In interviews, saying, "We continuously test SIM coverage," signals senior detection engineering maturity.
Real-world cybersecurity incident, number 77. Metric overaggregation, hiding security anomalies.
A sustained attack went undetected because security-relevant metrics were aggregated too aggressively. Dashboards looked healthy, error rates were flat, and latency remained within thresholds. The system was under attack, but the metrics were lying by omission.
1. The setup, everything looks secure.
The application emitted metrics for authentication, authorization, and API usage. Metrics were aggregated at service level and visualized through centralized dashboards used by engineering and operations teams.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that metrics existed, dashboards were monitored, and alerts were configured on error rates and latency. From a high-level perspective, the system appeared stable and healthy.
3. The breach, what failed anyway?
An attacker targeted a small subset of users and endpoints. Because metrics were aggregated across all traffic, localized abuse was averaged out and never crossed alert thresholds.
4. Where controls broke, diagnosis.
Metrics optimized for performance monitoring, not security detection. High cardinality dimensions such as user, endpoint, and region were dropped to reduce cost and complexity.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Averages hide localized abuse. 2. Security anomalies live in the tails. 3. Aggregation trades visibility for simplicity. 4. Metrics must preserve investigative dimensions. 5. Detection requires zoom, not just summary.
6. The trade-off nobody mentions.
1. High cardinality metrics increase cost. 2. Dashboards become more complex. 3. Alert tuning requires deeper analysis. 4. The benefit is detecting targeted attacks. Here is Java metrics instrumentation, showing how service-level aggregation hides per user and per endpoint abuse. Disclaimer: always test code in a non-production environment. Here is the code snippet incrementing a single global counter, averaging all traffic and erasing localized attack signals. This code block shows endpoint information being ignored, preventing detection of abuse concentrated on specific APIs.
Follow-up 1, senior level. How do you design metrics for security detection?
Answer: I preserve critical dimensions such as user, endpoint, and outcome, and aggregate only after analysis. Metrics should support investigation, not just reporting. In interviews, the key signal is designing metrics for abuse detection.
Follow-up 2, staff level. Why don't logs alone solve this?
Answer: logs are retrospective and require prior suspicion. Metrics provide early signals when designed correctly. In interviews, explaining the complementary roles of logs and metrics shows observability maturity.
Follow-up curveball. What if metric costs become too high?
Answer: then I apply sampling and risk-based retention, not blind aggregation. Cost optimization must not destroy detection capability. In interviews, the correct response is preserving signal under constraints.
8, pro insider tip.
If your metrics only show averages, attackers will hide in the edges. In interviews, saying, "We design metrics for tail behavior," signals senior observability expertise.
Real-world cybersecurity incident, number 78. No correlation across systems.
A multi-stage security incident went undetected because signals were scattered across systems that never correlated data. Each system showed minor anomalies, but no single view revealed the full attack path. The breach was discovered only after business impact became visible.
1, the setup. Everything looks secure.
The organization deployed logs, metrics, and alerts across applications, infrastructure, and identity systems. Each domain had its own dashboards, ownership, and on-call rotations.
2, what passed audits? Security incidents that passed every audit.
Audits confirmed that logging existed in all major systems, and alerts were configured per platform. Each team met its observability requirements independently.
3, the breach. What failed anyway?
An attacker moved through identity, application, and infrastructure layers. Each step generated signals, but because no correlation existed, no single alert represented the full attack sequence.
4, where controls broke. Diagnosis.
Observability was siloed by system rather than unified by attack path. There was no shared context, timeline, or entity correlation across telemetry sources.
5, the interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Attacks span multiple systems by design. 2. Siloed visibility fragments detection. 3. Correlation reveals intent, not just events. 4. Timelines matter more than isolated alerts. 5. Security requires cross-domain context.
6, the trade-off nobody mentions.
1. Correlation increases system complexity. 2. Ownership boundaries must be crossed. 3. False correlations require tuning. 4. The benefit is detecting multi-stage attacks.
Follow-up 1, senior level. How do you implement effective correlation?
Answer: I standardize entity identifiers and timestamps across systems and build detection around attack paths rather than individual events. Correlation must be intentional. In interviews, the key signal is thinking in sequences, not alerts.
Follow-up 2, staff level. Why don't individual system alerts catch this?
Answer: because each alert represents only a fragment of the attack. Without context, fragments look benign. In interviews, explaining fragmentation shows detection engineering maturity.
Follow-up curveball. What if teams resist shared telemetry?
Answer: then leadership must align incentives around collective security outcomes. Siloed success metrics hide systemic risk. In interviews, the correct response is addressing organizational barriers directly.
8, pro insider tip.
If you cannot connect events into a story, attackers will write it for you. In interviews, saying, "We detect attack paths, not alerts," signals senior-level security thinking.
Real-world cybersecurity incident, number 79. Short log retention periods destroy forensic visibility.
A security incident could not be fully investigated because relevant logs had already expired. The breach was detected late, and by the time response began, the historical evidence required to understand scope, entry point, and dwell time no longer existed.
1, the setup. Everything looks secure.
The organization enabled logging across critical systems and centralized logs for analysis. Retention policies were configured to minimize storage cost, and comply with internal data minimization goals.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that logging was enabled, retention policies were documented, and storage limits were enforced. From a compliance perspective, the organization was retaining logs exactly as configured.
3. The breach. What failed anyway?
When suspicious activity was identified weeks after initial compromise, the relevant authentication and access logs had already expired. Investigators were forced to rely on partial data and assumptions.
4. Where controls broke. Diagnosis.
Retention policies were optimized for cost, not incident response. The organization underestimated breach detection lag and overestimated how quickly incidents are discovered.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Detection is rarely immediate. 2. Retention must exceed expected dwell time. 3. Expired logs equal lost evidence. 4. Forensics depends on historical context. 5. Retention is a security decision, not just storage.
6. The trade-off nobody mentions.
1. Longer retention increases storage cost. 2. Compliance and privacy requirements must be balanced. 3. Data management becomes more complex. 4. The benefit is effective incident reconstruction. Here is Terraform configuration, showing how short log retention periods erase critical security evidence. Disclaimer: always test code in a non-production environment. Here is the code snippet setting retention far below typical breach discovery timelines, guaranteeing loss of forensic data. This code block shows retention enforced at the infrastructure level, making log loss automatic and irreversible.
Follow-up 1. Senior level. How do you choose appropriate log retention periods?
Answer: I base retention on realistic detection and response timelines, not best-case assumptions. High-risk systems retain logs longer by default. In interviews, the key signal is designing for delayed discovery.
Follow-up 2. Staff level. Why can't backups replace expired logs?
Answer: because backups are not indexed, searchable, or complete for telemetry. Logs are optimized for investigation, backups are not. In interviews, explaining this distinction shows operational depth.
Follow-up curveball. What if compliance requires minimal retention?
Answer: then security-critical logs must be scoped, protected, and justified separately. Compliance minimums are not security maximums. In interviews, the correct response is reconciling legal and security needs explicitly.
8. Pro insider tip.
If logs expire before incidents are found, logging is cosmetic. In interviews, saying retention is sized for investigation, not storage, signals real-world incident response experience.
Real-world cybersecurity incident. Number 80. No log integrity validation.
A breach investigation failed because log records could not be trusted. Logs existed and were retained, but there was no cryptographic assurance that entries had not been altered. Investigators could not prove what was real and what had been modified.
1. The setup. Everything looks secure.
The organization centralized logs in cloud storage and restricted access through IAM. Retention policies were configured, and logs were considered authoritative during incident response.
2. What passed audits? Security incidents that passed every audit.
Audits verified that logs were collected, retained, and access controlled. There were no explicit requirements for cryptographic integrity or tamper evidence in the logging pipeline.
3. The breach. What failed anyway?
After a compromise, logs were subtly altered to remove key indicators without deleting entire records. Because there was no integrity validation, the tampering went unnoticed during initial analysis.
4. Where controls broke. Diagnosis.
Logging focused on collection and retention, not trust. Without integrity checks, logs were assumed correct simply because they existed.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Logs must be provably tamper-evident. 2. Existence does not imply integrity. 3. Attackers modify evidence before deleting it. 4. Integrity validation enables trust in forensics. 5. Security evidence requires cryptographic guarantees.
6. The trade-off nobody mentions.
1. Integrity validation increases storage and compute cost. 2. Log pipelines become more complex. 3. Verification adds operational overhead. 4. The benefit is trustworthy incident evidence. Here is Terraform configuration, showing how logs without integrity validation can be altered without detection. Disclaimer: always test code in a non-production environment. Here is the code snippet relying solely on access control, which restricts who can write logs but does not detect modification. This code block shows storage configured without object locking, versioning, or integrity enforcement.
Follow-up 1, Senior Level. How do you guarantee log integrity?
Answer: I enable append-only storage, object versioning, and cryptographic hashing or signing of log streams. Integrity must be verifiable independently. In interviews, the key signal is treating logs as evidence.
Follow-up 2, Staff Level. Why isn't restricted access enough?
Answer: because attackers often obtain privileged access after compromise. Once inside, access control alone cannot protect evidence. In interviews, explaining post-compromise assumptions shows maturity.
Follow-up Curveball. What if integrity features are unavailable?
Answer: then forensic confidence is reduced and must be explicitly acknowledged. I prioritize integrity for the highest-risk systems first. In interviews, the correct response is explicit risk ownership.
8, Pro Insider Tip.
Logs without integrity are opinions, not evidence. In interviews, saying, "We cryptographically verify logs," signals senior incident response and forensic experience.
Category 8, Wrap-Up. Observability and monitoring failures.
These incidents demonstrate that most breaches persist not because defenses fail, but because visibility fails. When logs are missing, metrics are misleading, or signals are siloed, attackers gain time. In security, time is impact.
Transition from visibility gaps to availability failures.
When attackers are not detected early, they often shift from stealth to disruption. Availability attacks do not always steal data. They exhaust systems, budgets, and trust. In modern systems, availability is a first-class security property.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 9, Availability and Resilience Attacks.
Availability failures occur when systems cannot sustain legitimate or abusive load. These incidents exploit retry logic, dependencies, quotas, and graceful degradation paths. Senior engineers are evaluated on how systems fail under pressure, not how they perform when healthy.
Category 9, Availability and Resilience Incidents we will cover.
In this category, we will examine the following real-world availability failure modes. 81. Application layer distributed denial of service. 82. Cost exhaustion attacks. 83. Retry storms. 84. Dependency amplification failures. 85. Queue poisoning. 86. Cache eviction attacks. 87. Slow LoRa-style connection exhaustion. 88. Throttling cascades. 89. Regional dependency failures. 90. Graceful degradation failures. If a system cannot stay up, nothing else matters.
Real-world cybersecurity incident number 81. Application layer DDoS.
A production system suffered prolonged outages without any network-level attack. Traffic volumes appeared legitimate, TLS handshakes succeeded, and requests followed normal API paths. The service failed because expensive application logic was abused at scale.
1. The setup. Everything looks secure.
The application was protected by network-level DDoS defenses, a CDN, and a web application firewall. Requests were authenticated, rate limits existed, and infrastructure auto-scaling was enabled.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed DDoS protection, rate limiting, and capacity planning. Load tests focused on average traffic patterns and common request paths.
3. The breach. What failed anyway?
Attackers repeatedly invoked an expensive but valid API endpoint. Each request triggered heavy database queries and downstream calls. Because traffic was authenticated and well-formed, it bypassed network defenses and exhausted application resources.
4. Where controls broke. Diagnosis.
Rate limits applied uniformly and did not account for request cost. The system treated all endpoints as equal, allowing attackers to weaponize expensive logic using valid traffic.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Not all requests cost the same. 2. Authentication does not imply safety. 3. Application logic can be weaponized. 4. Rate limits must be cost-aware. 5. Availability failures are security failures.
6. The trade-off nobody mentions.
1. Cost-aware limits add implementation complexity. 2. Some legitimate users may be throttled. 3. Capacity planning becomes endpoint-specific. 4. The benefit is surviving abuse with valid traffic. Here is Java API logic showing how expensive endpoints enable application layer denial of service with valid requests. Disclaimer: always test code in a non-production environment. Here is the code snippet triggering an unbounded database query, making each request computationally expensive. This code block exposes heavy logic behind a simple GET request, allowing attackers to exhaust resources with valid traffic.
Follow-up 1. Senior level. How do you defend against application layer DDoS?
Answer: I classify endpoints by cost, apply stricter limits to expensive operations, and cache or pre-compute results where possible. Availability controls must understand application behavior. In interviews, the key signal is cost-aware defense design.
Follow-up 2. Staff level. Why don't network DDoS tools stop this?
Answer: because traffic is valid, authenticated, and low volume at the network level. The attack happens inside the application. In interviews, explaining this distinction shows real-world availability expertise.
Follow-up curveball. What if product teams resist stricter limits?
Answer: then the risk must be demonstrated with failure scenarios and load simulations. Availability trade-offs are business decisions. In interviews, the correct response is making impact visible.
8. Pro insider tip.
Most modern DDoS attacks use valid requests. In interviews, saying, "We rate limit by cost, not count," signals senior availability and resilience thinking.
Real-world cybersecurity incident number 82. Cost exhaustion attacks.
A cloud-native system remained technically available but caused severe financial damage. No services crashed, no limits were exceeded, and no alerts fired. The attack succeeded by forcing the system to scale exactly as designed until costs became unsustainable.
1. The setup. Everything looks secure.
The platform relied on auto-scaling infrastructure, managed cloud services, and pay-per-use pricing. Capacity limits were intentionally high to ensure reliability during peak demand.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed auto-scaling policies, redundancy, and fault tolerance. From a reliability perspective, the system behaved correctly under load.
3. The breach, what failed anyway.
Attackers generated sustained but valid workloads that triggered continuous scaling of compute and downstream services. The platform stayed online, but operational costs spiked dramatically within hours.
4. Where controls broke, diagnosis.
Availability controls focused on uptime, not spend. There were no guardrails to cap resource usage or alert on abnormal cost acceleration.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Cloud elasticity can be abused. 2. Scaling without spend controls is dangerous. 3. Availability and cost are coupled risks. 4. Financial exhaustion is a denial of service vector. 5. Security must include economic constraints.
6. The trade-off nobody mentions.
1. Spend limits can cap legitimate growth. 2. Cost controls add operational complexity. 3. False positives may block valid traffic. 4. The benefit is preventing runaway financial damage. Here is Terraform auto-scaling configuration, showing how unlimited scaling enables cost exhaustion attacks. Disclaimer: always test code in a non-production environment. Here is the code snippet allowing extreme scaling, enabling attackers to drive costs upward without triggering failures. This code block shows availability prioritized over economic safety, creating a financial denial of service risk.
Follow-up 1. Senior level. How do you defend against cost exhaustion?
Answer: I implement spend-based alerts, scaling caps tied to risk profiles, and circuit breakers for abnormal growth. Availability must be bounded by economic reality. In interviews, the key signal is treating cost as a security metric.
Follow-up 2. Staff level. Why isn't auto-scaling itself a protection?
Answer: auto-scaling protects uptime, not budgets. Attackers can exploit that separation. In interviews, explaining this distinction shows cloud-native security maturity.
Follow-up curveball. What if leadership demands unlimited scaling?
Answer: then the financial risk must be explicitly acknowledged and monitored. Unlimited scaling without guardrails is an accepted exposure. In interviews, the correct response is transparent risk ownership.
8. Pro insider tip.
If an attacker can bankrupt you without breaking anything, availability controls are incomplete. In interviews, saying, "We cap spend, not just scale," signals senior cloud security judgment.
Real-world cybersecurity incident. Number 83. Retry storms causing self-inflicted denial of service.
A partial outage escalated into a full system failure without any external attack. Services behaved exactly as designed, retries fired automatically, and no rate limits were breached. The system collapsed under its own recovery logic.
1. The setup. Everything looks secure.
The platform used microservices with automatic retries for resiliency. Timeouts were configured, circuit breakers existed, and retry logic was standardized across services.
2. What passed audits. Security incidents that passed every audit.
Audits verified retry policies, resilience libraries, and failure handling patterns. Chaos testing focused on isolated service failures rather than systemic retry interactions.
3. The breach. What failed anyway.
A downstream dependency slowed but did not fail. Upstream services retried aggressively, multiplying request volume and overwhelming shared infrastructure. The retry logic amplified the failure.
4. Where controls broke, diagnosis.
Retry logic lacked global coordination and back-off discipline. Each service acted independently, turning resilience mechanisms into a denial of service vector.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Retries amplify load during partial failure. 2. Resilience mechanisms can become attack surfaces. 3. Uncoordinated retries multiply traffic. 4. Backoff and jitter are mandatory. 5. Availability failures can be self-inflicted.
6. The trade-off nobody mentions.
1. Reduced retries can increase perceived errors. 2. Backoff increases response latency. 3. Global coordination adds complexity. 4. The benefit is preventing cascading failure. Here is Java retry logic showing how aggressive retries amplify partial failures into full outages. Disclaimer: always test code in a non-production environment. Here is the code snippet performing immediate retries without backoff, multiplying load during downstream slowness. This code block shows each retry executing the same expensive call, amplifying traffic instead of relieving pressure.
Follow-up 1, senior level. How do you design safe retry strategies?
Answer: I limit retries, add exponential backoff with jitter, and coordinate retries across services. Retries must reduce load, not increase it. In interviews, the key signal is understanding retry amplification.
Follow-up 2, staff level. Why aren't retries always good for resilience?
Answer: because retries increase traffic exactly when systems are weakest. Without discipline, they accelerate failure. In interviews, explaining this inversion shows real-world reliability experience.
Follow-up, curveball. What if product teams demand aggressive retries?
Answer: then the blast radius must be demonstrated through load testing and failure simulation. Retries are a risk trade-off, not a free safety net. In interviews, the correct response is data-driven pushback.
8, pro insider tip.
If retries are not coordinated, they will take your system down faster than attackers. In interviews, saying, "We treat retries as load multipliers," signals senior resilience engineering judgment.
Real-world cybersecurity incident, number 84. Dependency amplification causing cascading outages.
A minor slowdown in a single downstream service caused widespread outages across unrelated systems. No component fully failed, and no external traffic spike occurred. The outage was caused by internal dependency amplification, multiplying a small problem into a systemic failure.
1, the setup, everything looks secure.
The application relied on multiple internal and external services to fulfill a single request. Each dependency was reliable under normal conditions, and individual SLAs were met during testing.
2, what passed audits? Security incidents that passed every audit.
Audits verified dependency inventories, timeout settings, and resilience libraries. System design reviews focused on individual service reliability rather than compounded call graphs.
3, the breach, what failed anyway?
A single dependency experienced elevated latency. Each incoming request triggered multiple downstream calls, amplifying load and saturating shared resources. The slowdown propagated rapidly across the system.
4, where controls broke, diagnosis.
The system lacked awareness of call fan-out and cumulative dependency cost. Requests were treated as constant cost, even though they expanded exponentially through dependency chains.
5, the interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Dependency fan-out multiplies risk. 2. Small slowdowns propagate nonlinearly. 3. Reliability is systemic, not local. 4. Call graphs must be cost-aware. 5. Availability depends on controlling amplification.
6, the trade-off nobody mentions.
1. Reducing fan-out limits feature richness. 2. Caching increases data consistency complexity. 3. Call consolidation requires refactoring. 4. The benefit is preventing cascading outages. Here is Java service logic showing how request fan-out amplifies dependency latency into systemic failure. Disclaimer: always test code in a non-production environment. Here is the code snippet adding an additional synchronous dependency call, increasing latency sensitivity for every request. This code block shows how downstream computation compounds delay when upstream dependencies slow down.
Follow-up 1, senior level. How do you reduce dependency amplification?
Answer: I flatten call graphs, cache-derived data, and enforce strict time budgets per request. Dependencies must be treated as multiplicative risk. In interviews, the key signal is understanding fan-out economics.
Follow-up 2, staff level. Why don't individual SLAs prevent this?
Answer: because SLAs measure components in isolation. Amplification emerges only when components interact. In interviews, explaining this system's effect shows architectural maturity.
Follow-up, curveball. What if the product requires rich aggregation?
Answer: then aggregation must be asynchronous, cached, or pre-computed. Real-time fan-out should be minimized. In interviews, the correct response is separating user experience from dependency cost.
8, pro insider tip.
If one request fans out into many, latency becomes contagious. In interviews, saying, "We design APIs with fan-out budgets," signals senior distributed systems judgment.
Real-world cybersecurity incident number 85. Queue poisoning causing persistent availability failures.
A message queue became the single point of failure for an otherwise resilient system. No infrastructure limits were exceeded, and workers continued running. The outage persisted because malformed or toxic messages repeatedly crashed consumers, blocking healthy traffic.
1. The setup. Everything looks secure.
The architecture relied on asynchronous queues to decouple services and absorb spikes. Consumers scaled horizontally, retries were enabled, and dead-letter queues were configured but rarely used.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed queue durability, retry policies, and consumer scaling. Functional testing validated that valid messages were processed correctly under load.
3. The breach. What failed anyway?
A single malformed message triggered an unhandled exception in the consumer. The message was retried repeatedly, crashing workers over and over, preventing all subsequent messages from being processed.
4. Where controls broke. Diagnosis.
The system assumed messages were well-formed once enqueued. There was no validation or isolation of toxic messages before retries, allowing one bad payload to poison the entire queue.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Queues amplify failures when consumers crash deterministically. 2. Retries without isolation create infinite failure loops. 3. A single message can block an entire processing pipeline. 4. Poison messages must be quarantined quickly. 5. Availability depends on isolating bad inputs.
6. The trade-off nobody mentions.
1. Strict validation can reject borderline messages. 2. Dead letter handling adds operational overhead. 3. Some failures require manual intervention. 4. The benefit is preventing total queue paralysis. Here is Java queue consumer logic, showing how unhandled exceptions allow a single message to poison the queue. Disclaimer: always test code in a non-production environment. Here is the code snippet assuming every message can be parsed successfully, allowing malformed input to crash the consumer. This code block shows no try-catch or quarantine logic, causing the same message to be retried indefinitely.
Follow-up 1. Senior level. How do you design consumers to handle poison messages?
Answer: I validate inputs early, catch deterministic failures, and route toxic messages to a dead-letter queue immediately. Retries are reserved for transient failures only. In interviews, the key signal is differentiating failure types.
Follow-up 2. Staff level. Why don't retries solve this automatically?
Answer: because deterministic failures do not heal with time. Retrying only repeats the crash. In interviews, explaining this distinction shows real-world queue experience.
Follow-up curveball. What if dead-letter queues are ignored operationally?
Answer: then the system is operationally incomplete. Dead-letter queues must be monitored and owned. In interviews, the correct response is pairing technical controls with operational responsibility.
8. Pro insider tip.
If one message can stop the line, your queue is fragile. In interviews, saying, "We isolate poison messages immediately," signals senior event-driven architecture experience.
Real-world cybersecurity incident number 86. Cache eviction attacks causing latent availability failures.
A high-traffic application experienced repeated brownouts without obvious spikes or failures. Infrastructure remained healthy, databases were sized correctly, and no rate limits were exceeded. The failure emerged because attackers manipulated cache behavior, forcing constant eviction of hot data.
1. The setup. Everything looks secure.
The system relied heavily on in-memory caching to protect downstream databases. Cache hit rates were monitored, eviction policies were configured, and capacity was sized for normal access patterns.
2. What passed audits? Security incidents that passed every audit.
Audits verified cache configuration, eviction policies, and capacity planning. Load tests focused on common access paths and typical key distributions.
3. The breach. What failed anyway?
Attackers issued requests with a high cardinality of unique cache keys. Each request was valid, but collectively they forced constant eviction of frequently used entries, driving cache hit rates down and overwhelming the database.
4. Where controls broke, diagnosis.
The cache assumed benign access patterns. There were no limits on key diversity, no protection for hot entries, and no detection of eviction-based abuse.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Caches can be weaponized through key diversity. 2. Eviction is a form of denial of service. 3. Hit rate alone is an incomplete signal. 4. Hot data must be protected explicitly. 5. Availability depends on cache abuse controls.
6. The trade-off nobody mentions.
1. Protecting hot keys reduces cache flexibility. 2. Admission control adds complexity. 3. Some requests may bypass cache entirely. 4. The benefit is stable downstream performance. Here is Java cache access logic showing how unbounded key usage enables cache eviction attacks. Disclaimer: always test code in a non-production environment. Here is the code snippet inserting unbounded keys into the cache, allowing attackers to force eviction through high cardinality access. This code block shows cache access directly keyed on user-controlled input, enabling eviction abuse without violating any limits.
Follow-up 1. Senior level. How do you defend against cache eviction attacks?
Answer: I implement admission control, protect hot keys, and monitor eviction rates alongside hit rates. Cache behavior must be abuse-aware. In interviews, the key signal is treating eviction as a security concern.
Follow-up 2. Staff level. Why don't larger caches solve this?
Answer: because attackers can always generate more unique keys. Capacity alone does not fix unbounded cardinality. In interviews, explaining this shows depth in caching mechanics.
Follow-up curveball. What if product teams need arbitrary key access?
Answer: then cache usage must be segmented and guarded by policy. Not all data belongs in the same cache. In interviews, the correct response is isolating risk domains.
8. Pro insider tip.
If attackers can evict your cache, they control your latency. In interviews, saying, "We monitor eviction as an attack signal," signals senior performance and availability expertise.
Real-world cybersecurity incident, number 87. Slowlora-style connection exhaustion.
A customer-facing service became unavailable without any traffic spike or malformed requests. Network utilization remained low, CPU was idle, and no rate limits were exceeded. The attack succeeded by slowly exhausting connection capacity rather than overwhelming throughput.
1. The setup. Everything looks secure.
The application ran behind a load balancer with TLS termination, idle timeouts, and connection limits. Traffic patterns appeared normal, and infrastructure monitoring showed no resource saturation.
2. What passed audits? Security incidents that passed every audit.
Audits verified DDoS protection, rate limiting, and firewall rules. Penetration tests focused on request floods and malformed packets, none of which were present.
3. The breach. What failed anyway?
Attackers opened many legitimate connections and sent data extremely slowly, keeping them alive indefinitely. Connection pools filled up, preventing new legitimate clients from being served.
4. Where controls broke, diagnosis.
The system protected bandwidth and request rate, but not connection occupancy. Slow clients were treated the same as healthy ones, allowing attackers to monopolize finite connection resources.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Throughput and concurrency are different risks. 2. Connections are finite even when traffic is low. 3. Slow clients can be malicious. 4. Idle and read timeouts are security controls. 5. Availability failures can be silent.
6. The trade-off nobody mentions.
1. Aggressive timeouts can impact slow legitimate clients. 2. Connection policing adds tuning complexity. 3. False positives may disconnect valid sessions. 4. The benefit is protecting concurrency capacity.
Follow-up 1. Senior level. How do you defend against Slowlora-style attacks?
Answer: I enforce strict read and idle timeouts, limit concurrent connections per client, and offload connection handling to infrastructure designed for it. Availability controls must account for concurrency abuse. In interviews, the key signal is understanding non-throughput attacks.
Follow-up 2. Staff level. Why don't rate limits stop this?
Answer: because rate limits control requests per second, not how long a connection stays open. Slow Loris exploits that gap. In interviews, explaining this distinction shows deep protocol-level understanding.
Follow-up, curveball. What if the business requires long-lived connections?
Answer, then connection handling must be isolated, capacity limited, and protected separately from request processing. Long-lived does not mean unbounded. In interviews, the correct response is architectural isolation.
8. Pro insider tip.
If connections are cheap to open and expensive to hold, attackers will hold them. In interviews, saying, "We protect concurrency, not just throughput," signals senior availability engineering insight.
Real-world cybersecurity incident, number 88. Throttling cascades causing system-wide outages.
A localized traffic spike caused a complete outage across multiple services. No single component failed catastrophically, and infrastructure limits were respected. The outage emerged because throttling controls interacted in unexpected ways, cascading failure across the system.
1. The setup. Everything looks secure.
Each service enforced its own rate limits and throttling policies. Dependencies were protected individually, and backpressure mechanisms existed at multiple layers of the stack.
2. What passed audits? Security incidents that passed every audit.
Audits verified that rate limits were configured, throttling was enforced, and services failed gracefully under isolated load tests. No single service exceeded its capacity thresholds.
3. The breach. What failed anyway?
A spike in traffic triggered throttling in one service, causing retries and rerouting in upstream services. Those retries triggered throttling elsewhere, amplifying the disruption until all critical paths were affected.
4. Where controls broke. Diagnosis.
Throttling policies were designed in isolation. There was no coordination or awareness of how throttling decisions propagated across dependencies, turning protection mechanisms into failure multipliers.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Throttling shifts load rather than eliminating it. 2. Uncoordinated limits cause cascading retries. 3. Backpressure must be end-to-end. 4. Local protection can cause global failure. 5. Availability requires system-wide rate design.
6. The trade-off nobody mentions.
1. Coordinated throttling increases design complexity. 2. Global rate models require cross-team alignment. 3. Misconfiguration can underutilize capacity. 4. The benefit is preventing cascading outages. Here is Java request handling logic showing how local throttling triggers cascading retries across services. Disclaimer: always test code in a non-production environment. Here is the code snippet enforcing local throttling without coordinating downstream impact, shifting load upstream. This code block forces upstream retries and rerouting, amplifying traffic instead of applying controlled backpressure.
Follow-up 1. Senior level. How do you prevent throttling cascades?
Answer: I design rate limits end-to-end, propagate backpressure signals upstream, and cap retries aggressively. Throttling must reduce load globally, not locally. In interviews, the key signal is systems-level rate thinking.
Follow-up 2. Staff level. Why don't independent limits work?
Answer: because services interact. Independent limits assume isolation that does not exist. In interviews, explaining cross-service coupling shows architectural depth.
Follow-up curveball. What if teams cannot agree on global limits?
Answer: then the highest risk dependency must define the ceiling and others adapt. Coordination is a governance problem, not just technical. In interviews, the correct response is addressing organizational constraints.
8. Pro insider tip.
If throttling causes retries, it is not throttling. In interviews, saying, "We propagate backpressure, not errors," signals senior resilience engineering expertise.
Real-world cybersecurity incident, number 89. Regional dependency failure cascading into global outage.
A single regional cloud outage caused a global service disruption. Core systems remained healthy in most regions, but a hidden regional dependency became unavailable and silently broke critical request paths worldwide.
1. The setup. Everything looks secure.
The application was deployed across multiple regions with active-active traffic routing. Infrastructure redundancy was in place, and failover mechanisms were tested regularly at the service layer.
2. What passed audits? security incidents that passed every audit.
Audits verified multi-region deployments, health checks, and regional failover for compute and storage. Dependency reviews focused on primary application components.
3. The breach, what failed anyway.
A shared dependency was deployed in a single region only. When that region experienced an outage, requests from all regions failed while waiting on the unavailable dependency.
4. Where controls broke, diagnosis.
Resilience was applied to the application tier, but not to all dependencies. Regional isolation assumptions were incorrect, and the blast radius expanded globally.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Multi-region apps require multi-region dependencies. 2. Hidden single-region services break global resilience. 3. Failover must include every critical dependency. 4. Blast radius follows the weakest link. 5. Availability is only as strong as dependency locality.
6. The trade-off nobody mentions.
1. Duplicating dependencies increases cost. 2. Data consistency becomes harder across regions. 3. Operational complexity rises significantly. 4. The benefit is surviving regional cloud failures. Here is Terraform configuration showing how a single region dependency undermines multi-region availability. Disclaimer: always test code in a non-production environment. Here is the code snippet defining a shared service assumed to be globally available, masking its regional deployment reality. This code block shows no regional scoping or redundancy, causing all regions to depend on a single failure domain.
Follow-up 1. Senior level. How do you prevent regional dependency failures?
Answer: I inventory all dependencies and ensure each critical one is regionally redundant or gracefully degradable. Failover must be end-to-end. In interviews, the key signal is thinking beyond compute redundancy.
Follow-up 2. Staff level. Why don't load balancers solve this?
Answer: load balancers can only route to healthy backends. If the dependency exists in one region only, there is nowhere else to route. In interviews, explaining this shows deep cloud architecture understanding.
Follow-up, curveball. What if the dependency cannot be replicated?
Answer: then the system must degrade gracefully or isolate impact regionally. Global hard dependencies are unacceptable risks. In interviews, the correct response is designing explicit failure modes.
8. Pro insider tip.
If one region can take down all regions, you are not multi-region. In interviews, saying, "We eliminate single-region dependencies," signals senior cloud resilience expertise.
Real-world cybersecurity incident, number 90. Graceful degradation failure turning partial outages into total failure.
A system that was designed to degrade gracefully instead failed completely under stress. Non-critical features overwhelmed critical paths, causing total service unavailability. The incident occurred without any malicious traffic or infrastructure failure.
1. The setup. Everything looks secure.
The application defined critical and non-critical features, implemented feature flags, and documented fallback behavior. Load-shedding mechanisms existed on paper and passed functional testing.
2. What passed audits? Security incidents that passed every audit.
Audits verified feature flags, fallback logic, and priority classifications. Testing focused on individual feature toggles rather than system-wide behavior under stress.
3. The breach. What failed anyway?
When downstream dependencies slowed, optional features continued executing expensive logic. Critical request paths competed for the same resources and were starved, leading to full service outage.
4. Where controls broke, diagnosis.
The system degraded features functionally, but not computationally. There was no prioritization or isolation between critical and optional workloads.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Graceful degradation must preserve core functionality. 2. Optional features must shed load first. 3. Resource isolation is mandatory under stress. 4. Feature flags alone do not guarantee resilience. 5. Availability depends on prioritization, not intent.
6. The trade-off nobody mentions.
1. Strict prioritization reduces feature richness during incidents. 2. Implementing isolation adds architectural complexity. 3. Some user experience degradation is unavoidable. 4. The benefit is maintaining core service availability. Here is Java request handling logic showing how lack of prioritization causes graceful degradation to fail. Disclaimer: always test code in a non-production environment. Here is the code snippet executing optional logic on the critical path, allowing non-essential work to consume scarce resources. This code block shows critical and optional logic sharing the same execution path, preventing effective load shedding.
Follow-up 1, Senior Level. How do you design effective graceful degradation?
Answer: I isolate critical workloads, shed optional work early, and enforce resource prioritization under stress. Graceful degradation must be measurable and enforced. In interviews, the key signal is prioritizing core business paths.
Follow-up 2, Staff Level. Why don't feature flags prevent this?
Answer: feature flags control behavior, not resource usage. If optional logic still executes, flags provide false confidence. In interviews, explaining this distinction shows deep resilience understanding.
Follow-up Curveball. What if product teams resist disabling features?
Answer: then degradation policies must be enforced automatically based on system health. Human-in-the-loop decisions are too slow. In interviews, the correct response is automating protection.
8, Pro Insider Tip.
If optional work can starve critical paths, degradation is cosmetic. In interviews, saying, "We shed load by priority," signals senior availability and resilience expertise.
Category 9, Wrap-Up. Availability is a security property.
These incidents show that modern outages are rarely caused by broken infrastructure. They emerge from retry logic, dependency coupling, throttling design, and prioritization failures. When systems cannot remain available under stress, security guarantees collapse regardless of intent.
Transition from system resilience to AI attack surfaces.
As systems become more resilient and automated, attackers shift focus from infrastructure to intelligence. AI and Gen AI systems introduce a new class of security failures where logic, context, and trust boundaries replace traditional exploits.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like Junior Cybersecurity Analyst jobs, Cybersecurity Analyst jobs, Cybersecurity SOC Analyst jobs, Cybersecurity GRC jobs, Cybersecurity CISO jobs, Cybersecurity Incident Responder jobs, Cybersecurity Vulnerability Analyst jobs, Cybersecurity Malware Analyst jobs, Cybersecurity Engineer jobs, Cybersecurity Architect jobs, Cybersecurity Manager jobs, Cybersecurity Consultant jobs, Cybersecurity Specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 10, AI/Gen AI security incidents.
AI systems fail differently than traditional software. They accept natural language as input, infer intent probabilistically, and operate on opaque internal state. Security failures here often look like correct behavior until business or trust impact becomes visible.
Category 10, AI/Gen AI incidents we will cover.
In this category, we will examine the following real-world AI security failure modes. 91. Prompt injection attacks. 92. Training data poisoning. 93. Sensitive data leakage through prompts. 94. Model inversion attacks. 95. Hallucinated authority responses. 96. Excessive context exposure. 97. Vector database leakage. 98. Unauthorized embedding reuse. 99. Cost abuse through prompt manipulation. 100. Lack of auditability and traceability. AI systems expand the attack surface beyond code.
Real-world cybersecurity incident number 91. Prompt injection attacks.
A production AI assistant exposed sensitive internal information without any model compromise or data breach. The model behaved exactly as designed. The failure occurred because untrusted user input was allowed to override system instructions.
1. The setup. Everything looks secure.
The application used a hosted large language model with system prompts defining allowed behavior. Inputs were logged, outputs were monitored, and no fine-tuning data contained sensitive information.
2. What passed audits. Security incidents that passed every audit.
Audits reviewed system prompts, access controls, and API keys. The model provider met compliance requirements, and no direct access to restricted data sources existed.
3. The breach. What failed anyway.
A user crafted input that instructed the model to ignore prior instructions and reveal internal context. The model complied because the application treated user input as trusted prompt content.
4. Where controls broke. Diagnosis.
The application failed to enforce a strict separation between system instructions and user input. Prompt construction allowed untrusted text to influence model behavior directly.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. LLMs follow instructions, not intent. 2. User input is an untrusted execution surface. 3. Prompt boundaries are security boundaries. 4. System instructions must be immutable. 5. Prompt injection is an application flaw, not a model flaw.
6. The trade-off nobody mentions.
1. Strict prompt isolation reduces flexibility. 2. Some user creativity is constrained. 3. Prompt templating adds development overhead. 4. The benefit is preventing instruction override. Here is Python prompt construction logic, showing how untrusted user input enables prompt injection. Disclaimer: always test code in a non-production environment. Here is the code snippet directly concatenating untrusted user input with system instructions, allowing user text to override intended behavior. This code block shows no isolation or sanitization boundary between trusted system context and untrusted user input.
Follow-up 1. Senior level. How do you prevent prompt injection?
Answer: I treat user input as untrusted data, enforce rigid prompt templates, and separate system instructions from user content structurally. The model should never see raw user text as instructions. In interviews, the key signal is treating prompts as attack surfaces.
Follow-up 2. Staff level. Why can't the model just ignore malicious prompts?
Answer: because models do not understand trust boundaries. They optimize for instruction following. In interviews, explaining this limitation shows realistic AI security understanding.
Follow-up curveball. What if product teams want maximum flexibility?
Answer: then the risk must be explicitly accepted and constrained to non-sensitive use cases. Flexibility and safety are a trade-off. In interviews, the correct response is scoping risk, not denying it.
8. Pro insider tip.
If users can change your instructions, they control your system. In interviews, saying, "We treat prompts as executable input," signals senior-level AI security maturity.
Real-world cybersecurity incident number 92. Training data poisoning.
An AI system began producing subtly incorrect and biased outputs months after deployment. There was no model breach, no prompt injection, and no infrastructure compromise. The failure originated upstream in the data used to train and continuously refine the model.
1. The setup. Everything looks secure.
The organization trained models using a mix of internal datasets, third-party data, and user feedback loops. Data pipelines were automated, versioned, and monitored for availability and schema consistency.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed data access controls, pipeline integrity, and model reproducibility. Training jobs completed successfully, and no unauthorized data sources were detected.
3. The breach, what failed anyway.
An attacker slowly injected manipulated data into upstream data sources that were treated as trustworthy. Over time, the poisoned data shifted model behavior in ways that favored the attacker's objectives without triggering obvious anomalies.
4. Where controls broke, diagnosis.
The system validated data structure, but not data intent. There were no controls to detect semantic drift, coordinated manipulation, or adversarial influence within otherwise valid training data.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Training data is part of the attack surface. 2. Valid data can still be malicious. 3. Poisoning works gradually, not explosively. 4. Integrity checks must include semantics. 5. Model behavior reflects data trust assumptions.
6. The trade-off nobody mentions.
1. Stricter data validation slows iteration. 2. Semantic analysis is computationally expensive. 3. False positives can block legitimate data. 4. The benefit is protecting long-term model integrity.
Follow-up 1. Senior level. How do you defend against training data poisoning?
Answer: I restrict data sources, apply provenance tracking, and monitor model behavior for drift rather than trusting data blindly. Defense focuses on detecting change, not preventing all input. In interviews, the key signal is treating data pipelines as security critical.
Follow-up 2. Staff level. Why don't schema checks prevent this?
Answer: because poisoned data is often structurally valid. The attack targets meaning, not format. In interviews, explaining this distinction shows depth in ML security.
Follow-up, curveball. What if training relies on user-generated data?
Answer: then influence must be rate-limited, weighted, and monitored for coordinated patterns. User feedback is inherently adversarial. In interviews, the correct response is assuming malicious participation.
8. Pro insider tip.
If you don't control your data, you don't control your model. In interviews, saying, "We monitor for behavioral drift, not just pipeline health," signals senior AI security experience.
Real-world cybersecurity incident number 93. Sensitive data leakage through prompts.
An AI-powered support assistant unintentionally exposed sensitive internal and customer data during normal interactions. There was no external breach, no database compromise, and no unauthorized access. The data was leaked because the application injected sensitive context directly into prompts.
1. The setup. Everything looks secure.
The application enriched prompts with user profile data and historical context to improve response quality. Access controls were enforced at the database layer, and only authorized services could retrieve sensitive fields.
2. What passed audits? Security incidents that passed every audit.
Audits verified database permissions, API authentication, and model access controls. From an infrastructure perspective, no unauthorized data access paths existed.
3. The breach. What failed anyway?
During normal conversations, the model included sensitive attributes such as internal notes and customer identifiers in its responses. The model was not malicious. It simply reflected everything it was given.
4. Where controls broke, diagnosis.
The application assumed that prompt context was safe because it was generated internally. There was no filtering or classification boundary between data allowed for reasoning and data allowed for disclosure.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Models can only protect what they never see. 2. Prompt context is a disclosure surface. 3. Internal data is not automatically safe data. 4. Reasoning context must differ from response context. 5. AI leaks data by reflection, not intent.
6. The trade-off nobody mentions.
1. Reducing context can degrade answer quality. 2. Data classification requires upfront effort. 3. Prompt filtering adds latency. 4. The benefit is preventing silent data exfiltration. Here is Python prompt construction logic, showing how injecting sensitive context causes AI data leakage. Disclaimer: always test code in a non-production environment. Here is the code snippet injecting sensitive customer and internal data directly into the prompt context. making it available for model output. This code block shows no separation between reasoning context and user-visible response context, allowing sensitive data to be reflected back.
Follow-up 1, Senior Level. How do you prevent sensitive data leakage in AI systems?
Answer: I classify data before it enters prompts and strictly limit what can be included in user-facing context. Sensitive data may be used for decisioning, but never exposed to generation. In interviews, the key signal is separating reasoning from disclosure.
Follow-up 2, Staff Level. Why can't output filtering alone solve this?
Answer: because once the model sees sensitive data, it can influence outputs in unpredictable ways. Prevention must happen before prompt construction. In interviews, explaining pre-generation controls shows maturity.
Follow-up, Curveball. What if product teams want maximum personalization?
Answer: then personalization must be driven by derived attributes, not raw sensitive fields. Convenience must not override disclosure risk. In interviews, the correct response is designing safe abstractions.
8, Pro Insider Tip.
If sensitive data enters the prompt, assume it can exit in the response. In interviews, saying, "We treat prompt context as a data egress path," signals senior AI security judgment.
Real-world cybersecurity incident number 94, Model Inversion Attacks.
An AI model was used to infer sensitive attributes about individuals without ever accessing the underlying training data. No prompts were injected, no permissions were bypassed, and no data stores were compromised. The leakage occurred through repeated, valid model queries.
1, The setup. Everything looks secure.
The model was exposed through a controlled API with authentication, rate limits, and logging. Training data was access restricted, encrypted, and isolated from inference workloads.
2, What passed audits. Security incidents that passed every audit.
Audits confirmed no direct access to training data, validated API authentication, and reviewed infrastructure isolation. The model provider met compliance requirements.
3, The breach. What failed anyway.
By carefully crafting and correlating large volumes of legitimate queries, an attacker inferred sensitive attributes that were statistically embedded in the model. The attack exploited model behavior, not system access.
4, Where controls broke. Diagnosis.
Security controls assumed that protecting training data was sufficient. There were no safeguards limiting inference-based extraction or detecting abnormal query patterns designed to reconstruct sensitive information.
5, The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Models can leak information statistically. 2. Inference is an extraction surface. 3. Access control does not equal privacy protection. 4. Repeated queries amplify leakage. 5. Privacy risk exists even with perfect isolation.
6, The trade-off nobody mentions.
1. Mitigations can reduce model utility. 2. Noise injection affects accuracy. 3. Query restrictions limit legitimate use cases. 4. The benefit is protecting sensitive attributes.
Follow-up 1, Senior Level. How do you mitigate model inversion risk?
Answer: I combine query rate limits, anomaly detection, output noise, and careful feature selection. The goal is to reduce extractable signal rather than relying on access controls alone. In interviews, the key signal is recognizing inference as an attack vector.
Follow-up 2, Staff Level. Why isn't encrypting training data enough?
Answer: because inversion exploits learned patterns, not stored records. Encryption protects data at rest, not model behavior. In interviews, explaining this distinction shows applied ML security understanding.
Follow-up, Curveball. What if the business requires high model transparency?
Answer: then privacy risk must be explicitly assessed and accepted, or mitigated with differential privacy techniques. Transparency and privacy are often in tension. In interviews, the correct response is managing that trade-off consciously.
8, Pro Insider Tip.
If a model can answer questions, it can leak information. In interviews, saying, "We treat inference as a data extraction channel," signals senior AI security maturity.
Real-world cybersecurity incident number 95. Hallucinated authority responses.
An AI assistant confidently provided authoritative-sounding answers about internal policies and regulatory requirements that were partially incorrect. No data was leaked, and no systems were breached. The damage occurred because users trusted the AI's confidence and acted on false guidance.
1. The setup. Everything looks secure.
The AI system was deployed as an advisory assistant for employees, with no direct execution privileges. Responses were generated from general knowledge and internal documentation summaries, and outputs were logged for review.
2. What passed audits? Security incidents that passed every audit.
Audits verified that the model had no right access to systems, no privileged APIs, and no direct control over workflows. From a technical access standpoint, the AI posed no obvious risk.
3. The breach. What failed anyway?
Employees followed incorrect AI guidance related to compliance and incident response, resulting in delayed reporting and improper handling of regulated data. The AI's confident tone masked uncertainty and errors.
4. Where controls broke. Diagnosis.
The system failed to communicate uncertainty and limitations. There were no guardrails distinguishing advisory output from authoritative policy, and no requirement for human verification on high-impact guidance.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Confidence is not correctness. 2. AI output influences human decisions. 3. Hallucinations become dangerous when trusted. 4. Authority must be explicitly bounded. 5. Human verification is a security control.
6. The trade-off nobody mentions.
1. Adding disclaimers reduces perceived usefulness. 2. Human-in-the-loop slows response time. 3. Users may ignore warnings over time. 4. The benefit is preventing operational and compliance harm.
Follow-up 1. Senior level. How do you mitigate hallucinated authority risk?
Answer: I constrain AI usage to advisory roles, clearly label uncertainty, and require human confirmation for decisions with legal or security impact. Authority must never be implicit. In interviews, the key signal is treating trust as a design parameter.
Follow-up 2. Staff level. Why isn't accuracy tuning enough?
Answer: because even high-accuracy systems can fail confidently at the edges. The risk is not frequency of errors, but the impact when they occur. In interviews, explaining impact-based risk shows senior judgment.
Follow-up. Curveball. What if leadership wants AI to replace human decision-making?
Answer: then risk ownership must shift explicitly, and guardrails must be enforced contractually and technically. Replacing humans does not remove accountability. In interviews, the correct response is clarifying responsibility boundaries.
8. Pro insider tip.
The most dangerous AI answers are the confident wrong ones. In interviews, saying, "We bound AI authority explicitly," signals senior-level AI governance maturity.
Real-world cybersecurity incident. Number 96. Excessive context exposure in AI systems.
An AI assistant exposed unrelated internal information during normal conversations. There was no prompt injection and no malicious input. The leakage occurred because the application provided far more contextual data than was required to answer user questions.
1. The setup. Everything looks secure.
The system aggregated multiple data sources to enrich responses, including user history, organizational metadata, and internal reference material. Access controls governed each source independently.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that each data source was accessed legally and that the AI service itself had proper authorization. There were no violations of access control or data ownership rules.
3. The breach. What failed anyway?
The AI combined excessive contextual information into a single prompt. While responding to a simple question, the model surfaced details from unrelated contexts, creating an unintentional disclosure.
4. Where controls broke. Diagnosis.
The application failed to apply the principle of minimum necessary context. Data that was authorized for access was incorrectly assumed to be authorized for disclosure.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Context size is a security boundary. 2. Authorization does not imply disclosure. 3. AI reflects everything it sees. 4. Minimum necessary applies to prompts. 5. Excess context increases blast radius.
6. The trade-off nobody mentions.
1. Reducing context can lower response quality. 2. Context curation requires domain expertise. 3. Dynamic context selection adds complexity. 4. The benefit is preventing cross-context leakage. Here is Python context assembly logic, showing how excessive context exposure causes unintended AI data disclosure. Disclaimer: always test code in a non-production environment. Here is the code snippet appending broad internal documentation regardless of question relevance, expanding the disclosure surface. This code block shows no relevance filtering between the user question and the contextual data being included.
Follow-up 1, senior level. How do you control excessive context exposure?
Answer: I implement relevance-based context selection and strictly cap contextual scope per request. Authorization gates access, but disclosure gates output. In interviews, the key signal is distinguishing access from exposure.
Follow-up 2, staff level. Why isn't access control enough here?
Answer: because access determines what the system can see, not what it should show. AI systems echo context probabilistically. In interviews, explaining that difference shows real-world AI safety awareness.
Follow-up curveball. What if users demand highly personalized answers?
Answer: then personalization must be derived, not raw. I provide summarized or abstracted signals instead of full context. In interviews, the correct response is controlled personalization.
8, pro insider tip.
If the model doesn't need it to answer, it shouldn't see it. In interviews, saying, "We minimize prompt context aggressively," signals senior AI security discipline.
Real-world cybersecurity incident number 97. Vector database leakage.
An AI-powered search feature exposed sensitive internal documents without direct database access. No SQL injection, no credential theft, and no authorization bypass occurred. The leakage happened through semantic similarity queries that returned results outside the user's intended scope.
1. The setup. Everything looks secure.
The application used a vector database to store embeddings of internal documents. Access to the vector store was restricted to the application layer, and users interacted only through a controlled search interface.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed database authentication, network isolation, and role-based access at the service layer. No user could directly query the vector database or retrieve raw embeddings.
3. The breach. What failed anyway?
By crafting queries with semantically broad phrasing, users retrieved documents from unrelated teams and projects. The vector database returned nearest neighbors without enforcing document-level authorization.
4. Where controls broke. Diagnosis.
Authorization was enforced at query entry, but not at retrieval. The system assumed semantic relevance implied permission, allowing similarity scoring to bypass access boundaries.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Similarity is not authorization. 2. Vector search expands access implicitly. 3. Embedding stores require access filters. 4. Retrieval must enforce security boundaries. 5. AI search changes data exposure models.
6. The trade-off nobody mentions.
1. Filtering reduces recall quality. 2. Authorization checks add query latency. 3. Indexing becomes more complex. 4. The benefit is preventing semantic data leaks. Here is Python vector search logic, showing how missing authorization filters cause semantic data leakage. Disclaimer: always test code in a non-production environment. Here is the code snippet executing a similarity search without applying any authorization or metadata filters. This code block shows the system returning nearest neighbors purely by similarity, not by access rights.
Follow-up 1, senior level. How do you secure vector database queries?
Answer: I enforce document-level authorization at retrieval time using metadata filters and post-query access checks. Similarity determines ranking, not permission. In interviews, the key signal is separating relevance from access.
Follow-up 2, staff level. Why can't this be solved at the database level alone?
Answer: because vector databases optimize for similarity, not security. Application logic must enforce policy. In interviews, explaining this limitation shows practical AI system experience.
Follow-up curveball. What if filtering hurts search quality?
Answer: then quality must degrade safely. security boundaries are not optional optimizations. In interviews, the correct response is prioritizing data protection over recall.
8. Pro Insider Tip.
If vector search ignores authorization, it becomes a data exfiltration engine. In interviews, saying, "We enforce access after similarity," signals senior AI architecture judgment.
Real-world cybersecurity incident number 98. Unauthorized embedding reuse across contexts.
Embeddings generated for one business purpose were reused in another context without user consent or authorization. No raw data was exposed, and no access controls were bypassed. The incident occurred because embeddings were treated as non-sensitive artifacts rather than derived representations of protected data.
1. The setup. Everything looks secure.
The application generated embeddings from internal documents and user inputs to support search and recommendation features. Embeddings were stored centrally to improve performance and reduce compute cost.
2. What passed audits. Security incidents that passed every audit.
Audits verified that raw documents were access controlled and that embedding storage contained no plaintext data. From a traditional data security perspective, embeddings were classified as non-sensitive.
3. The breach. What failed anyway.
Teams reused embeddings across unrelated products and tenants. Because embeddings encode semantic meaning, this reuse enabled inference of sensitive attributes and cross-context information leakage.
4. Where controls broke. Diagnosis.
The system assumed that derived data was safe to reuse. There were no controls binding embeddings to their original purpose, scope, or tenant, allowing silent cross-context leakage.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Embeddings are data, not metadata. 2. Derived representations inherit sensitivity. 3. Reuse must respect original purpose. 4. Context binding is a security requirement. 5. AI artifacts require lifecycle controls.
6. The trade-off nobody mentions.
1. Context-bound embeddings increase storage cost. 2. Recomputation impacts performance. 3. Reuse restrictions reduce engineering convenience. 4. The benefit is preventing semantic cross-leakage. Here is Python embedding retrieval logic showing how reuse without context binding enables unauthorized inference. Disclaimer: always test code in a non-production environment. Here is the code snippet retrieving an embedding without validating the tenant, purpose, or scope it was generated for. This code block shows no contextual binding between the embedding and its original authorization boundary.
Follow-up 1. Senior level. How do you prevent embedding reuse abuse?
Answer: I bind embeddings to tenant, purpose, and lifecycle metadata and enforce checks at retrieval time. Reuse is explicitly authorized, not implicit. In interviews, the key signal is treating embeddings as sensitive assets.
Follow-up 2. Staff level. Why can't embeddings be treated as anonymized data?
Answer: because embeddings preserve semantic structure that enables inference. They are lossy but not anonymous. In interviews, explaining this shows practical understanding of representation risk.
Follow-up curveball. What if storage cost becomes prohibitive?
Answer: then embeddings must be regenerated on demand or aggressively scoped. Cost efficiency cannot override data isolation. In interviews, the correct response is prioritizing trust boundaries.
8. Pro Insider Tip.
If you can reuse an embedding freely, you have already lost control of its meaning. In interviews, saying, "We bind embeddings to purpose and tenant," signals senior AI security maturity.
Real-world cybersecurity incident number 99. Cost abuse through prompt manipulation.
An AI service experienced a sudden and sustained cost spike without any increase in legitimate user growth. There was no denial of service attack and no abuse of infrastructure APIs. The incident occurred because users were able to manipulate prompts to trigger excessive token usage and repeated expensive operations.
1. The setup. Everything looks secure.
The application enforced authentication, per-user quotas, and request-level rate limiting. AI usage was monitored at a high level, and billing alerts were configured for monthly spend thresholds.
2. What passed audits. Security incidents that passed every audit.
Audits verified API key protection, quota enforcement, and infrastructure rate limits. From a traditional abuse perspective, no single user exceeded request limits or violated access policies.
3. The breach, what failed anyway.
Users crafted prompts that intentionally expanded context size, forced multi-step reasoning, and triggered repeated tool calls. Each request was valid and within quotas, but the aggregate cost per request exploded.
4. Where controls broke, diagnosis.
The system controlled request count but not computational cost. There were no safeguards limiting tokens, reasoning depth, or tool invocation per request, allowing adversarial prompts to maximize spend.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Cost is an attack surface in AI systems. 2. Valid requests can still be abusive. 3. Token usage matters more than request count. 4. AI abuse targets billing, not availability. 5. Cost controls must exist at prompt level.
6. The trade-off nobody mentions.
1. Strict limits can reduce answer quality. 2. Complex prompts may be truncated. 3. Some advanced use cases are constrained. 4. The benefit is predictable and bounded spend. Here is Python request handling logic, showing how missing token and cost limits enable AI cost abuse. Disclaimer: always test code in a non-production environment. Here is the code snippet invoking the language model, without enforcing any token, step, or tool call limits. This code block shows unbounded user-controlled input directly driving computational cost.
Follow-up 1. Senior level. How do you prevent AI cost abuse?
Answer: I enforce hard caps on tokens, reasoning depth and tool calls per request, and monitor cost per interaction instead of just volume. Abuse is detected by spend anomalies, not traffic spikes. In interviews, the key signal is treating cost as a security dimension.
Follow-up 2. Staff level. Why don't rate limits solve this?
Answer: because a single request can be extremely expensive. Rate limits control frequency, not complexity. In interviews, explaining per request cost amplification shows real AI operational experience.
Follow-up, curveball. What if the business wants unrestricted AI power?
Answer: then cost risk must be explicitly accepted, isolated to specific tiers, and closely monitored. Unlimited power cannot be unlimited liability. In interviews, the correct response is aligning spend with risk ownership.
8. Pro insider tip.
If users can control your token count, they control your bill. In interviews, saying, "We cap cost per prompt," signals senior AI platform maturity.
Real-world cybersecurity incident, number 100. Lack of auditability and traceability.
An organization could not explain why an AI system produced a high-impact decision that affected customers and regulators. There was no breach, no outage, and no malicious input. The failure was the absence of traceability linking outputs to prompts, context, models, and decisions.
1. The setup. Everything looks secure.
The AI system was authenticated, rate-limited, and monitored for uptime and cost. Prompts were generated dynamically, models were versioned internally, and responses were returned to users through a stable API.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed access controls, API key management, and infrastructure logging. From a traditional system perspective, requests were authorized and the service operated within defined limits.
3. The breach. What failed anyway?
When a harmful output was reported, the team could not reconstruct the prompt, context, model version, or parameters that produced it. Without traceability, there was no way to explain, reproduce, or remediate the behavior.
4. Where controls broke, diagnosis.
The system treated AI interactions as ephemeral events rather than auditable decisions. Logging focused on availability and cost, not on decision lineage and accountability.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. AI decisions require lineage, not just logs. 2. Outputs must be traceable to inputs and models. 3. Auditability is a governance requirement. 4. Reproducibility enables accountability. 5. Untraceable AI is an operational risk.
6. The trade-off nobody mentions.
1. Detailed logging increases storage cost. 2. Prompt and context capture raises privacy concerns. 3. Traceability adds implementation complexity. 4. The benefit is explainability and regulatory readiness. Here is Python AI request handling logic showing how missing trace logging prevents auditability of model decisions. Disclaimer: always test code in a non-production environment. Here is the code snippet generating an AI response without recording prompt, model version, parameters, or context. This code block shows no trace identifier or audit record linking the request to the resulting decision.
Follow-up 1, senior level. What does proper AI auditability look like?
Answer: I log prompts, context identifiers, model versions, parameters, and outputs with correlation IDs. This enables reconstruction and accountability. In interviews, the key signal is treating AI outputs as decisions that must be explainable.
Follow-up 2, staff level. How do you balance auditability with privacy?
Answer: I tokenize or hash sensitive fields and store references instead of raw data where possible. Auditability and privacy must be designed together. In interviews, explaining this balance shows mature system thinking.
Follow-up, curveball. What if the system uses multiple models dynamically?
Answer: then model selection must be logged per request with deterministic identifiers. Dynamic does not mean untraceable. In interviews, the correct response is enforcing lineage across all execution paths.
8, pro insider tip.
If you cannot explain why an AI made a decision, you own the risk without evidence. In interviews, saying, "We log full AI decision lineage," signals senior AI governance and security leadership.
Category 10, wrap-up. AI security fails where trust is assumed.
AI incidents rarely look like breaches. They look like normal behavior producing unacceptable outcomes. The failures we covered were not caused by model compromise, but by misplaced trust in prompts, context, cost, and authority. AI security is application security amplified by uncertainty.
Transition from technical failures to organizational reality.
As systems mature, the primary failure mode shifts away from code and configuration. The most damaging incidents happen when people override controls, skip process, or misunderstand risk. Governance failures are where all technical defenses quietly collapse.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 11, governance, process, and human failures.
This category covers incidents where security controls technically existed, but were bypassed, ignored, or rendered ineffective by human decisions. These failures are the hardest to prevent, the hardest to detect, and the most common root cause in postmortems.
Category 11, governance and human failure incidents we will cover.
In this category, we will examine the following real-world governance and process failures. 101. Security controls bypassed for speed. 102. Unclear ownership of assets. 103. Incident response playbooks unused. 104. Poor threat modeling. 105. Security reviews skipped. 106. Over-reliance on tools. 107. Lack of security education. 108. No postmortems. 109. No feedback loops. 110. Compliance mistaken for security. Most breaches are people problems wearing technical disguises.
Real-world cybersecurity incident number 101. Security controls bypassed for speed.
A critical security control was deliberately bypassed to meet a delivery deadline. No exploit was required, no vulnerability was discovered, and no attacker forced entry. The incident happened because engineers chose speed over safety under organizational pressure.
1. The setup. Everything looks secure.
The organization had formal security controls, approval workflows, and automated checks. These controls were documented, reviewed, and enforced under normal operating conditions.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed that security gates existed and were correctly implemented. There was evidence of past enforcement and historical compliance with policy.
3. The breach. What failed anyway.
Under deadline pressure, teams bypassed the control using temporary exceptions and manual overrides. The exception became permanent, undocumented, and invisible to monitoring systems.
4. Where controls broke. Diagnosis.
The system relied on voluntary compliance rather than enforced guardrails. Security controls that can be bypassed easily will be bypassed eventually.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Controls that slow delivery without enforcement will be bypassed. 2. Temporary exceptions become permanent risk. 3. Security must be built into the path of least resistance. 4. Human pressure defeats optional safeguards. 5. Enforcement beats documentation.
6. The trade-off nobody mentions.
1. Hard enforcement can slow emergency response. 2. Strict controls reduce perceived team autonomy. 3. Automation requires upfront investment. 4. The benefit is removing humans from impossible decisions.
Follow-up 1. Senior level. How do you prevent security bypass under pressure?
Answer: I design controls that are technically impossible to bypass without detection and approval. If bypasses are needed, they are time-bound, logged, and automatically revoked. In interviews, the key signal is enforcing guardrails instead of relying on discipline.
Follow-up 2. Staff level. What if the business demands faster delivery?
Answer: then security must be part of delivery, not a gate after it. Faster delivery without enforcement simply moves risk downstream. In interviews, explaining this trade-off shows organizational maturity.
Follow-up curveball. Are exceptions ever acceptable?
Answer: yes, but only when they are explicit, temporary, owned, and auditable. Silent exceptions are failures by design. In interviews, the correct response is controlled deviation, not denial.
8. Pro insider tip.
If security relies on people saying no under pressure, it will fail. In interviews, saying, "We design controls that cannot be silently bypassed," signals senior security leadership.
Real-world cybersecurity incident number 102. Unclear ownership of assets.
A sensitive system was compromised and no team could clearly state who owned it. The application was running in production, processing real data, and generating revenue. Yet responsibility for security, maintenance, and incident response was fragmented across teams.
1. The setup. Everything looks secure.
The system was deployed using approved infrastructure, monitored for uptime, and integrated with shared authentication services. Multiple teams interacted with the system during its life cycle, from development to operations.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed that the platform met baseline security requirements and that controls existed at the infrastructure level. Asset inventories listed the system, but ownership fields were outdated or ambiguous.
3. The breach. What failed anyway.
When suspicious activity was detected, alerts were routed between teams with no clear escalation path. Patches were delayed, access reviews were skipped, and the incident persisted because no single owner was accountable.
4. Where controls broke. Diagnosis.
Security controls assumed clear ownership for response and remediation. Without an accountable owner, Controls existed in theory, but failed operationally.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Unowned assets are unprotected assets. 2. Accountability enables response. 3. Shared responsibility without clarity equals no responsibility. 4. Ownership must be explicit and current. 5. Security depends on human accountability.
6. The trade-off nobody mentions.
1. Assigning ownership creates political friction. 2. Teams may inherit legacy risk unwillingly. 3. Ownership requires ongoing maintenance. 4. The benefit is decisive action during incidents.
Follow-up 1. Senior level. How do you enforce clear asset ownership?
Answer: I require every production asset to have a single accountable owner with escalation responsibility. Ownership is reviewed regularly and tied to operational metrics. In interviews, the key signal is treating ownership as a security control.
Follow-up 2. Staff level. What about shared platforms used by many teams?
Answer: shared platforms still need a primary owner responsible for security posture and response coordination. Consumers do not replace accountability. In interviews, explaining this shows operational clarity.
Follow-up curveball. What if no team wants ownership?
Answer: then leadership must assign it explicitly. Unowned systems represent accepted risk by default. In interviews, the correct response is escalating ownership gaps, not tolerating them.
8. Pro insider tip.
If nobody owns it, nobody will secure it. In interviews, saying every asset has a named owner with escalation authority signals senior governance maturity.
Real-world cybersecurity incident, number 103. Incident response playbooks unused.
A confirmed security incident escalated slowly and inconsistently, despite having documented incident response playbooks. The organization had procedures, roles, and communication plans, yet responders improvised under pressure instead of following the defined process.
1. The setup. Everything looks secure.
The organization maintained incident response playbooks covering detection, triage, containment, communication, and recovery. Roles were defined, contact lists existed, and tabletop exercises had been performed in the past.
2. What passed audits? Security incidents that passed every audit.
Audits verified the existence of playbooks, approval by leadership, and periodic review. Documentation was current and met compliance requirements.
3. The breach. What failed anyway?
During the live incident, responders skipped formal triage steps, failed to escalate on time, and made ad hoc decisions. Confusion over authority and sequence caused delays, allowing the incident to expand in scope.
4. Where controls broke. Diagnosis.
Playbooks existed only as documentation, not as operational muscle memory. Under stress, teams defaulted to improvisation rather than following structured response paths.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Documentation is not readiness. 2. Incident response must be practiced, not referenced. 3. Stress reveals process gaps. 4. Clear authority prevents paralysis. 5. Playbooks must be operationalized.
6. The trade-off nobody mentions.
1. Regular drills consume time and resources. 2. Exercises can feel disruptive or artificial. 3. Maintaining readiness requires repetition. 4. The benefit is decisive action during real incidents.
Follow-up 1. Senior level. How do you ensure playbooks are actually used?
Answer: I embed playbooks into on-call workflows, automate initial steps where possible, and run regular simulations. Familiarity under pressure is built through repetition. In interviews, the key signal is treating response as an operational capability.
Follow-up 2. Staff level. Why do teams ignore playbooks during incidents?
Answer: because stress narrows focus and people revert to habits. If playbooks are not ingrained, they will be skipped. In interviews, explaining human behavior under pressure shows practical experience.
Follow-up curveball. What if playbooks slow response?
Answer: then the playbooks are poorly designed. Good playbooks accelerate decision-making by removing ambiguity. In interviews, the correct response is refining playbooks, not abandoning them.
8. Pro insider tip.
If your first incident is your first time using the playbook, you don't have a playbook. In interviews, saying, "We drill until response is automatic," signals senior incident response leadership.
Real-world cybersecurity incident number 104, poor threat modeling.
A system was compromised through an attack path that had never been considered during design. No vulnerability scanners flagged the issue, no controls were misconfigured, and no alerts fired. The failure occurred because the system was built without systematically modeling how it could be abused.
1. The setup, everything looks secure.
The architecture followed best practices, used approved frameworks, and passed standard security reviews. Authentication, authorization, and encryption were implemented according to guidelines.
2. What passed audits? Security incidents that passed every audit.
Audits verified control implementation, checked configuration baselines, and confirmed compliance with security standards. No known vulnerability patterns were present.
3. The breach, what failed anyway.
Attackers abused a legitimate workflow in an unexpected sequence, combining valid actions to reach an unintended outcome. Because the behavior followed allowed paths, detection systems did not flag it.
4. Where controls broke, diagnosis.
Security reviews focused on individual components rather than system behavior. Without threat modeling, abuse paths and unintended interactions were never identified.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Threat modeling identifies abuse, not just bugs. 2. Valid actions can still be dangerous. 3. Security emerges from system behavior. 4. Design time thinking prevents runtime surprises. 5. Controls must be mapped to threats.
6. The trade-off nobody mentions.
1. Threat modeling takes time early in design. 2. It can feel speculative or uncomfortable. 3. Not all scenarios are immediately actionable. 4. The benefit is preventing entire classes of failure.
Follow-up 1. Senior level. How do you make threat modeling effective?
Answer: I integrate threat modeling into design reviews, involve cross-functional perspectives, and focus on abuse cases rather than theoretical attackers. The goal is coverage, not perfection. In interviews, the key signal is making threat modeling a habit, not an event.
Follow-up 2. Staff level. Why don't security tools catch these issues?
Answer: because tools look for known patterns. Threat modeling addresses unknown interactions and emergent behavior. In interviews, explaining this gap shows architectural thinking.
Follow-up curveball. What if teams resist threat modeling?
Answer: then start small and tie it to real incidents, showing how past failures could have been predicted builds buy-in. In interviews, the correct response is incremental adoption.
8. Pro insider tip.
If you only model threats after incidents, you are paying tuition instead of planning. In interviews, saying, "We model abuse paths before writing code," signals senior security architecture experience.
Real-world cybersecurity incident number 105. Security reviews skipped.
A critical system change introduced a severe security weakness that went unnoticed until after exploitation. No tooling failed, and no alerts were ignored. The incident occurred because a required security review was skipped to meet a delivery deadline.
1. The setup, everything looks secure.
The organization had a defined security review process for architecture changes, including threat assessment, design validation, and approval gates. Under normal conditions, this process was followed consistently.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that the security review process existed, was documented, and had historical evidence of enforcement. Metrics showed high compliance rates across prior releases.
3. The breach, what failed anyway?
During a high-priority release, the security review was waived as an exception. The change introduced an unanticipated exposure that attackers later exploited. The waiver was informal, undocumented, and never revisited.
4. Where controls broke, diagnosis.
Security reviews were treated as a procedural step rather than an enforced control. There were no technical mechanisms preventing deployment when reviews were skipped.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Optional reviews are not controls. 2. Process without enforcement will fail under pressure. 3. Exceptions must be visible and time-bound. 4. Security must block unsafe deployments. 5. Governance requires technical guardrails.
6. The trade-off nobody mentions.
1. Hard gates can delay urgent releases. 2. Strict enforcement frustrates teams initially. 3. Automation requires upfront investment. 4. The benefit is preventing silent risk accumulation.
Follow-up 1. Senior level. How do you prevent security reviews from being skipped?
Answer: I integrate security approval into deployment pipelines so unsafe changes cannot ship without review. Exceptions are explicit, logged, and auto-expire. In interviews, the key signal is enforcing governance through automation.
Follow-up 2. Staff level. What about emergency fixes?
Answer: emergency paths still require review, but the scope is reduced and post-deployment review is mandatory. Speed does not eliminate risk ownership. In interviews, explaining controlled emergency processes shows maturity.
Follow-up curveball. What if leadership pressures teams to bypass reviews?
Answer: then leadership must explicitly accept the risk in writing. Security teams should not absorb silent liability. In interviews, the correct response is clarifying accountability.
8. Pro insider tip.
If a review can be skipped, it eventually will be. In interviews, saying, "We enforce security reviews as code," signals senior governance and platform thinking.
Real-world cybersecurity incident. Number 106. Over-reliance on security tools.
An organization suffered a significant breach despite having industry-leading security tools deployed across the stack. Scanners, SIEM, EDR, and cloud posture tools were all active and reporting green status. The incident occurred because teams assumed tool coverage equaled security.
1. The setup. Everything looks secure.
The environment used automated vulnerability scanning, continuous compliance monitoring, endpoint detection, and centralized alerting. Dashboards showed high coverage and low risk scores across systems.
2. What passed audits? Security incidents that passed every audit.
Audits verified tool deployment, license coverage, alert ingestion, and retention policies. Reports showed that required security tooling was present and operational.
3. The breach. What failed anyway?
Attackers exploited a logic flaw and misused valid credentials. The activity generated no tool alerts because it did not match known signatures or anomaly thresholds. Teams trusted dashboards instead of questioning system behavior.
4. Where controls broke. Diagnosis.
Security responsibility was outsourced to tools. Human judgment, threat modeling, and contextual analysis were de-emphasized, creating blind spots where tools could not reason about intent.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Tools detect patterns, not intent. 2. Coverage does not equal comprehension. 3. Security requires human reasoning. 4. Dashboards can create false confidence. 5. Tools must support, not replace thinking.
6. The trade-off nobody mentions.
1. Human review does not scale as easily as tools. 2. Contextual analysis requires skilled staff. 3. Manual investigation increases operational cost. 4. The benefit is catching failures tools cannot see.
Follow-up 1. Senior level. How do you avoid over-reliance on security tools?
Answer: I treat tools as signal generators, not decision makers, and require human review for high-impact paths. Threat modeling and behavioral analysis complement tooling. In interviews, the key signal is balancing automation with judgment.
Follow-up 2. Staff level. Why do teams fall into tool dependency?
Answer: because tools provide measurable comfort and reduce cognitive load. Green dashboards feel safer than ambiguity. In interviews, explaining this psychological aspect shows real-world experience.
Follow-up curveball. What if leadership wants tool-based assurance?
Answer: then expectations must be reset. Tools reduce risk but never eliminate it. In interviews, the correct response is aligning leadership understanding with reality.
8. Pro insider tip.
If security is something you buy instead of something you do, it will fail. In interviews, saying tools assist decisions, they don't make them, signals senior security leadership.
Real-world cybersecurity incident. Number 107. Lack of security education.
A preventable security incident occurred because engineers misunderstood how existing controls worked. No tools failed, and no policies were violated intentionally. The breach happened because teams lacked practical security education and made unsafe assumptions during implementation.
1. The setup. Everything looks secure.
The organization provided security guidelines, documentation, and mandatory onboarding training. Engineers had access to standards, examples, and internal security portals.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed that security training existed, was documented, and was completed by employees. Compliance checklists showed full participation and policy acknowledgement.
3. The breach. What failed anyway.
Engineers implemented a feature that unintentionally bypassed security assumptions, believing controls would compensate automatically. The misunderstanding persisted until the feature was abused in production.
4. Where controls broke. Diagnosis.
Security knowledge was theoretical rather than practical. Training focused on rules instead of failure modes, leaving teams unprepared to reason about real-world abuse scenarios.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Security education must be experiential. 2. Knowing rules is not the same as understanding risk. 3. Engineers need mental models, not checklists. 4. Training must reflect real incidents. 5. Education is a preventive control.
6. The trade-off nobody mentions.
1. Hands-on training consumes engineering time. 2. Security education slows short-term delivery. 3. Curricula require constant updates. 4. The benefit is reducing entire classes of mistakes.
Follow-up 1. Senior level. How do you make security education effective?
Answer: I base training on real incidents, run hands-on labs, and tie lessons to the systems engineers actually build. Abstract rules are replaced with concrete failure stories. In interviews, the key signal is treating education as risk reduction.
Follow-up 2. Staff level. Why don't mandatory trainings prevent this?
Answer: because passive learning does not change behavior. Without context and practice, knowledge decays quickly. In interviews, explaining this gap shows organizational awareness.
Follow-up curveball. What if teams resist security training?
Answer: then training must be embedded into engineering workflows and career progression. Security competence is part of the job, not an optional add-on. In interviews, the correct response is integrating education, not enforcing attendance.
8. Pro insider tip.
If engineers don't understand how systems fail, they will build them wrong. In interviews, saying, "We train engineers on failure modes, not just policies," signals senior security leadership.
Real-world cybersecurity incident. Number 108. No postmortems conducted.
An organization experienced repeated security incidents with similar root causes over time. Each incident was treated as an isolated event, resolved tactically, and then forgotten. The absence of postmortems allowed the same failures to recur.
1. The setup. Everything looks secure.
Incidents were detected, contained, and closed. Tickets were resolved, services were restored, and leadership was notified. From an operational standpoint, incidents appeared to be handled successfully.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed that incidents were logged and remediated. There was evidence of fixes and documented closure, but no requirement to analyze systemic causes or lessons learned.
3. The breach. What failed anyway.
Similar incidents continued to occur because underlying causes were never addressed. Teams fixed symptoms repeatedly without correcting structural weaknesses.
4. Where controls broke. Diagnosis.
The organization optimized for closure speed instead of learning. Without postmortems, feedback loops never formed and risk accumulated silently.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Incidents without learning are wasted signals. 2. Postmortems turn failures into controls. 3. Systemic causes matter more than immediate fixes. 4. Blameless analysis enables honesty. 5. Learning prevents recurrence.
6. The trade-off nobody mentions.
1. Postmortems require time after incidents. 2. They can feel uncomfortable or political. 3. Follow-up actions require sustained effort. 4. The benefit is compounding security improvement.
Follow-up 1. Senior level. What makes a postmortem effective?
Answer: I focus on systemic causes, contributing factors, and actionable follow-ups with owners. Blame is removed to encourage honesty. In interviews, the key signal is treating postmortems as engineering inputs, not paperwork.
Follow-up 2, staff level. Why do teams avoid postmortems?
Answer: because they take time and expose uncomfortable truths. Without leadership support, learning is deprioritized. In interviews, explaining this resistance shows organizational awareness.
Follow-up curveball. What if incidents are minor?
Answer: minor incidents still reveal system behavior. Lightweight postmortems scale learning without heavy process. In interviews, the correct response is proportional analysis, not avoidance.
8, pro insider tip.
If you fix incidents without learning from them, you guarantee repetition. In interviews, saying, "Every incident produces at least one systemic improvement," signals senior engineering maturity.
Real-world cybersecurity incident, number 109. No feedback loops.
Security signals were generated across the organization, but none were fed back into design, policy, or operational change. Incidents were detected and resolved, yet the system never improved. Risk accumulated because lessons were not institutionalized.
1, the setup. Everything looks secure.
The organization collected alerts, incident tickets, audit findings, and customer reports. Each signal was handled within its own workflow and closed independently.
2, what passed audits? Security incidents that passed every audit.
Audits confirmed that detection, response, and remediation processes existed. There was evidence of resolution, but no requirement to feed outcomes back into preventive controls.
3, the breach. What failed anyway?
The same classes of incidents reappeared because upstream systems never changed. Signals died at the point of closure instead of influencing architecture, training, or policy.
4, where controls broke. Diagnosis.
Security was treated as a linear process rather than a learning system. Without feedback loops, detection and response could not reduce future risk.
5, the interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Security must learn from its own signals. 2. Detection without adaptation is incomplete. 3. Feedback turns incidents into prevention. 4. Controls must evolve based on evidence. 5. Learning loops reduce recurring risk.
6, the trade-off nobody mentions.
1. Closing feedback loops requires cross-team coordination. 2. Changes may challenge existing ownership boundaries. 3. Metrics must be revisited regularly. 4. The benefit is continuous risk reduction.
Follow-up 1, senior level. How do you build effective security feedback loops?
Answer: I ensure incident outcomes directly inform architecture decisions, training updates, and control changes. Feedback is tracked to completion, not just recorded. In interviews, the key signal is treating learning as an operational requirement.
Follow-up 2, staff level. Why are feedback loops often missing?
Answer: because organizations optimize for closure metrics instead of improvement. Learning spans teams and timelines, making it harder to prioritize. In interviews, explaining this dynamic shows organizational insight.
Follow-up curveball. What if teams resist changes driven by past incidents?
Answer: then leadership must reinforce that evidence drives evolution. Security that does not adapt becomes theater. In interviews, the correct response is institutionalizing learning.
8, pro insider tip.
If incidents don't change how you build systems, they will happen again. In interviews, saying, "We close the loop from incident to design," signals senior security architecture maturity.
Real-world cybersecurity incident, number 110. Compliance mistaken for security.
An organization suffered a major security incident shortly after passing multiple compliance audits. All required controls were documented, evidence was provided, and certifications were renewed. The breach occurred because compliance was treated as proof of security rather than a minimum baseline.
1, the setup. Everything looks secure.
The organization aligned its controls to regulatory frameworks, maintained audit evidence, and successfully passed external assessments. Security activities were heavily driven by compliance timelines and checklists.
2, what passed audits? Security incidents that passed every audit.
Auditors confirmed that required controls existed, documentation was complete, and policies matched regulatory expectations. From a compliance perspective, The organization was in good standing.
3. The breach, what failed anyway.
Attackers exploited gaps that were outside the scope of compliance requirements. Because the organization optimized for passing audits, real-world threats went unaddressed and undetected.
4. Where controls broke, diagnosis.
Compliance frameworks defined minimum requirements, but the organization treated them as comprehensive security strategies. Risk-based thinking was replaced with checklist completion.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Compliance defines minimums, not guarantees. 2. Passing audits does not equal being secure. 3. Threats evolve faster than regulations. 4. Security must be risk-driven. 5. Controls must exceed baseline requirements.
6. The trade-off nobody mentions.
1. Going beyond compliance increases cost. 2. Risk-based controls are harder to justify on paper. 3. Security investments may not map cleanly to audits. 4. The benefit is resilience against real threats.
Follow-up 1. Senior level. How do you balance compliance and real security?
Answer: I treat compliance as a floor, not a ceiling, and layer risk-based controls on top. Audit readiness never replaces threat modeling. In interviews, the key signal is explicitly separating regulatory success from security posture.
Follow-up 2. Staff level. Why do organizations conflate compliance with security?
Answer: because compliance is measurable and externally validated, while security is probabilistic. Passing audits feels like closure. In interviews, explaining this distinction shows strategic understanding.
Follow-up, curveball. What if leadership only cares about compliance?
Answer: then risks outside compliance must be explicitly documented and accepted. Security teams should make the gaps visible. In interviews, the correct response is clarifying residual risk, not silently accepting it.
8. Pro insider tip.
If your security strategy ends when the audit passes, your risk begins afterward. In interviews, saying compliance is the starting point, not the goal, signals senior security leadership.
Category 11 wrap-up. Governance failures are the root cause layer.
Every technical failure we covered ultimately traced back to human decisions, unclear accountability, or broken process. Governance is not a separate concern from security. It is the layer that determines whether controls are followed, bypassed, or ignored.
Transition from human failure to runtime reality.
When governance fails, the impact often materializes at runtime. Nowhere is this more visible than in Kubernetes, where a single configuration decision can collapse isolation boundaries across the entire cluster.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 12, Kubernetes and Container Runtime Failures.
Kubernetes is the operating system of modern infrastructure. Most incidents at this layer do not involve 0 days or kernel exploits. They happen because defaults are trusted, privileges are overscoped, and runtime behavior is poorly understood.
Category 12, Kubernetes and Container Incidents we will cover.
In this category, we will examine the following real-world Kubernetes and container runtime failures. 111. Overpermissive Kubernetes RBAC. 112. Exposed kubelet APIs. 113. Insecure admission controllers. 114. Container escape via misconfigured runtimes. 115. Privileged pods running in production. 116. Secrets mounted as plaintext files. 117. Lateral movement via service accounts. 118. Flat clusters without network policies. 119. Image pulls from untrusted registries. 120. Compromised init containers. A secure cloud account can still be fully compromised through Kubernetes.
Real-world cybersecurity incident, number 111. Overpermissive Kubernetes RBAC.
A production Kubernetes cluster was fully compromised without exploiting the control plane or container runtime. The attacker gained access through a service account that was legitimately bound to a highly privileged RBAC role.
1. The setup. Everything looks secure.
The cluster used RBAC namespaces and service accounts. Access was authenticated, TLS was enforced, and workloads were deployed through approved pipelines. No anonymous access was enabled.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed RBAC was enabled. Cluster admin access was limited to automation, and service accounts were used instead of static credentials. From a compliance standpoint, access controls existed.
3. The breach. What failed anyway?
A compromised pod accessed the Kubernetes API using its mounted service account token. Because the role binding granted broad permissions, the attacker listed secrets, created new workloads, and escalated control across namespaces.
4. Where controls broke. Diagnosis.
RBAC verified identity, but failed to enforce intent. The service account was bound to permissions far beyond its operational needs, turning a single pod compromise into cluster-wide control.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. RBAC must reflect workload intent, not convenience. 2. Service accounts are identities with blast radius. 3. Least privilege in Kubernetes is namespace and verb specific. 4. Cluster admin bindings are cluster-wide liabilities. 5. Pod compromise must not equal cluster compromise. API version, rbac.authorization.k8seconds.eo/v1 kind. Cluster role binding metadata. Name, app service admin subjects. Kind, service account name, app service namespace, production role ref. Kind, cluster role name. Cluster admin API group. rbac.authorization.k8seconds.eo.
6. The trade-off nobody mentions.
1. Fine-grained RBAC increases configuration complexity. 2. Teams must manage more roles and bindings. 3. Debugging permission issues takes longer. 4. The benefit is containing compromise to a single workload.
Follow-up 1. Senior level. Why is cluster admin so dangerous in Kubernetes?
Answer: because it bypasses namespace isolation entirely. Any pod using that identity can control workloads, secrets, and RBAC itself. In interviews, calling this out shows real Kubernetes threat modeling experience.
Follow-up 2. Staff level. How do you design safer service account permissions?
Answer: I scope permissions to namespaces, resources, and verbs explicitly. Each service account exists for a single workload purpose. In interviews, explaining verb-level RBAC is a strong signal.
Follow-up curveball. What if teams insist cluster admin is faster?
Answer: then they are trading speed for systemic risk. I allow temporary elevation only through controlled workflows with expiration and audit. In interviews, the correct response is containment, not convenience.
8. Pro insider tip.
If a pod can do everything, it eventually will. In interviews, saying, "We design RBAC so pod compromise cannot escalate beyond its namespace," signals senior Kubernetes security expertise.
Real-world cybersecurity incident, number 112. Exposed kubelet APIs.
A Kubernetes cluster was compromised through direct access to kubelet APIs on worker nodes. No control plane credentials were stolen, and RBAC remained intact. The breach occurred because node-level kubelet endpoints were exposed and trusted implicitly.
1. The setup. Everything looks secure.
The cluster enforced RBAC, authenticated API server access, and restricted control plane endpoints. Nodes were provisioned automatically, and kubelet ran with default configuration.
2. What passed audits. Security incidents that passed every audit.
Audits focused on API server access, RBAC policies, and etcd protection. Node-level services were assumed to be internal and trusted.
3. The breach. What failed anyway.
An attacker accessed the kubelet API on a worker node and executed commands inside running containers. Because kubelet trusted requests from the network, the attacker bypassed RBAC entirely.
4. Where controls broke. Diagnosis.
Security assumed the control plane was the only attack surface. Kubelet APIs were exposed without authentication, turning each node into a privileged entry point.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Kubelet is part of the control surface. 2. Node-level trust is a dangerous assumption. 3. RBAC does not protect exposed kubelet endpoints. 4. Network isolation is a security control. 5. Nodes must be treated as hostile by default. API version. kubelet.config.k8seconds.eo/v1 beta 1 kind. Kubelet configuration authentication. Anonymous, enabled, true authorization. Mode always allow.
6. The trade-off nobody mentions.
1. Securing kubelet complicates node bootstrap. 2. Misconfiguration can break cluster operations. 3. Network isolation requires coordination with infrastructure teams. 4. The benefit is preventing node-level takeover.
Follow-up 1. Senior level. Why isn't RBAC enough to protect kubelet?
Answer: because RBAC applies to the API server, not directly to kubelet endpoints. If kubelet is exposed, attackers bypass RBAC entirely. In interviews, explaining this distinction signals deep Kubernetes security understanding.
Follow-up 2. Staff level. How do you properly secure kubelet?
Answer: I disable anonymous authentication, enforce webhook authorization, and restrict network access to trusted control plane components. In interviews, mentioning node firewalling is a strong signal.
Follow-up curveball. What if legacy clusters rely on open kubelet access?
Answer: then remediation must be phased, starting with network isolation and gradual auth enforcement. Open kubelet access is technical debt, not a requirement. In interviews, acknowledging migration strategy shows maturity.
8. Pro insider tip.
If you can reach kubelet, you can reach containers. In interviews, saying, "We treat kubelet as a first-class attack surface," signals senior Kubernetes security expertise.
Real-world cybersecurity incident. Number 113. Insecure admission controllers.
A Kubernetes cluster was compromised through a trusted admission controller that modified workloads at deploy time. No RBAC rules were violated, no pods escaped the runtime, and no control plane credentials were stolen. The failure occurred because the admission controller was implicitly trusted and insufficiently constrained.
1. The setup. Everything looks secure.
The cluster used validating and mutating admission controllers to enforce policy, inject sidecars, and standardize security settings. Admission webhooks were registered centrally and applied to all namespaces.
2. What passed audits. Security incidents that passed every audit.
Audits confirmed that admission controllers were enabled, TLS was configured, and webhook registrations were present. From a policy perspective, admission control was considered a security enhancement.
3. The breach. What failed anyway.
A compromised admission controller injected privileged settings into workloads at creation time. Because the mutation happened before enforcement, pods were deployed with elevated permissions that were never explicitly requested.
4. Where controls broke. Diagnosis.
The cluster trusted admission controllers as part of the security boundary. There were no restrictions on what fields could be mutated, and no secondary validation of injected configuration.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Admission controllers run with cluster-wide influence. 2. Mutation is equivalent to code execution on manifests. 3. Implicit trust creates invisible privilege escalation. 4. Injected configuration must be constrained. 5. Admission logic is part of the attack surface. API version. Admission registration.k8seconds.eo/v1 kind. Mutating webhook configuration metadata name. Unsafe mutator webhooks name. Mutate.pods.example.com rules API groups. API versions. v1 operations. Create resources. Pods client config service name mutator namespace cube system path/mutate.
6. The trade-off nobody mentions.
1. Restricting mutation reduces flexibility. 2. Additional validation increases latency. 3. Webhook failures can block deployments. 4. The benefit is preventing invisible privilege injection.
Follow-up 1. Senior level. Why are admission controllers such a high-risk component?
Answer: because they operate at the boundary between intent and execution. They can silently change what actually runs. In interviews, calling admission logic a privileged execution path signals deep Kubernetes security awareness.
Follow-up 2. Staff level. How do you secure admission controllers?
Answer: I scope them narrowly, restrict what fields they may mutate, and add validating controllers to enforce invariance. In interviews, mentioning defense in depth for admission is a strong signal.
Follow-up, curveball. What if admission controllers are owned by another team?
Answer: then their changes must be treated as code changes to the cluster itself. Ownership boundaries do not reduce risk. In interviews, the correct response is shared accountability.
8. Pro insider tip.
If you don't know what your admission controllers can inject, you don't know what is running in your cluster. In interviews, saying, "We audit admission mutations," signals senior Kubernetes security expertise.
Real-world cybersecurity incident, number 114. Container escape via misconfigured runtime.
A production Kubernetes workload escaped its container boundary and accessed the underlying host. No kernel 0-day was used, and no vulnerability scanner fired. The escape happened because the container runtime was configured with unsafe defaults.
1. The setup. Everything looks secure.
The cluster enforced RBAC namespaces and network controls. Containers were built from approved images and deployed through standard pipelines. Runtime configuration was assumed to be safe by default.
2. What passed audits? Security incidents that passed every audit.
Audits verified image scanning, RBAC enforcement, and pod security policies. Runtime flags and container isolation settings were not reviewed in detail.
3. The breach. What failed anyway?
A compromised container accessed host-level resources and executed commands outside its namespace. Because the runtime allowed host file system access, the container boundary was effectively meaningless.
4. Where controls broke. Diagnosis.
Isolation relied on assumptions instead of enforced runtime constraints. The container was granted host access that directly violated the security model of containerization.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Containers are not VMs. 2. Runtime configuration defines isolation. 3. Host access negates container boundaries. 4. Escapes often use valid configuration paths. 5. Defense requires strict runtime constraints. Here is Kubernetes pod runtime configuration, showing how host file system mounts enable container escape. Disclaimer: always test code in a non-production environment. Here is the code block enabling direct access to the host file system from inside the container. This code snippet mounts the root file system, allowing the container to read and modify host-level resources.
6. The trade-off nobody mentions.
1. Some workloads rely on host access for performance. 2. Restricting host mounts can break legacy applications. 3. Runtime hardening requires refactoring. 4. The benefit is preserving container isolation.
Follow-up 1. Senior level. Why are host path mounts so dangerous?
Answer: because they bypass container isolation entirely. Once the host file system is accessible, the container can affect other workloads and the node itself. In interviews, explicitly calling host path a boundary break signals real runtime experience.
Follow-up 2. Staff level. How do you prevent container escape at runtime?
Answer: I restrict host mounts, enforce seccomp and app armor profiles, and use pod security standards. Runtime configuration is treated as a first-class security control. In interviews, mentioning layered isolation is a strong signal.
Follow-up, curveball. What if the application genuinely needs host access?
Answer: then it must be isolated onto dedicated nodes with strict monitoring and reduced blast radius. Host access is an exception, not a default. In interviews, the correct response is containment, not denial.
8. Pro insider tip.
If a container can see the host, it can become the host. In interviews, saying, "We audit runtime mounts, not just images," signals senior Kubernetes runtime security expertise.
Real-world cybersecurity incident, number 115. Privileged pods running in production.
A Kubernetes production cluster was compromised without exploiting the control plane or container runtime. The attacker gained full node-level control by abusing a legitimately deployed privileged pod that was intended for operational convenience.
1. The setup. Everything looks secure.
The cluster used namespaces, RBAC, and approved deployment pipelines. Privileged pods were allowed only for specific operational workloads and were assumed to be safe because access was restricted to trusted teams.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed RBAC enforcement, image scanning, and restricted access to deployment pipelines. The existence of privileged pods was documented and justified for operational use.
3. The breach. What failed anyway?
An attacker compromised the application running inside a privileged pod. Because the pod had elevated privileges, the attacker accessed host resources and pivoted to other workloads on the same node.
4. Where controls broke. Diagnosis.
The security model assumed that privileged pods were safe if access was restricted. In reality, any vulnerability inside a privileged pod becomes a direct path to node compromise.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Privileged pods collapse isolation boundaries. 2. Application security failures become node failures. 3. Operational convenience increases blast radius. 4. Privileges must be treated as toxic. 5. Production should default to non-privileged execution. Here is Kubernetes pod security context configuration, showing how privileged execution grants full host access. Disclaimer: always test code in a non-production environment. Here is the code block defining the container security context, which controls runtime privilege levels. This code snippet disables most container isolation mechanisms, granting the pod near-root access to the host.
6. The trade-off nobody mentions.
1. Some operational tools require elevated privileges. 2. Removing privileged pods can break existing workflows. 3. Refactoring operational tooling takes time. 4. The benefit is preventing node-level compromise.
Follow-up 1. Senior level. Why are privileged pods worse than host path mounts?
Answer: because privileged pods disable multiple isolation layers at once, not just file system access. They effectively turn containers into host processes. In interviews, highlighting this distinction signals deep runtime security understanding.
Follow-up 2. Staff level. How do you eliminate privileged pods safely?
Answer: I replace them with narrowly scoped capabilities, sidecar patterns, or node-level agents where absolutely necessary. Each privilege is justified individually. In interviews, explaining capability-based design is a strong signal.
Follow-up, curveball. What if privileged pods are required for debugging?
Answer: then they should be ephemeral, tightly scoped, and never part of steady-state production. Debugging access must not persist beyond the task. In interviews, the correct response is temporary elevation with controls.
8. Pro insider tip.
If a pod is privileged, assume it can become the node. In interviews, saying, "We treat privileged pods as production incidents waiting to happen," signals senior Kubernetes security maturity.
Real-world cybersecurity incident, number 116. Secrets mounted as plaintext files.
Sensitive credentials were exposed from inside a running container without exploiting Kubernetes, the node, or the control plane. The data was accessed simply by reading files that were legitimately mounted into the container at runtime.
1. The setup, everything looks secure.
The cluster used Kubernetes secrets, RBAC, and namespace isolation. Secrets were created through approved workflows and mounted only into workloads that required them.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that secrets were stored in Kubernetes secrets and not hard-coded into images. Access to secret creation was restricted and logged.
3. The breach, what failed anyway.
An attacker exploited a minor application vulnerability and gained shell access inside the container. From there, they simply read the mounted secret files and exfiltrated credentials.
4. Where controls broke, diagnosis.
Kubernetes protected secret storage, but not secret usage. Once mounted as files, secrets became plaintext accessible to any process in the container.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Secrets are protected only until they are used. 2. Mounted secrets become part of the file system. 3. Application compromise equals secret compromise. 4. Runtime secret exposure defines blast radius. 5. Secret handling must assume container breach. Here is Kubernetes pod specification showing how mounting secrets as volumes exposes them as plaintext files at runtime. Disclaimer: always test code in a non-production environment. Here is the code snippet showing secrets mounted directly into the container file system. This code block references a Kubernetes secret that becomes readable plaintext once mounted.
6. The trade-off nobody mentions.
1. Mounting secrets is simple and widely supported. 2. Alternative secret delivery mechanisms add complexity. 3. Runtime secret access is harder to audit. 4. The benefit of avoiding mounts is reduced credential exposure.
Follow-up 1. Senior level. How do you reduce secret exposure at runtime?
Answer: I minimize secret lifetime by injecting them just in time, scope them per workload, and use external secret managers where possible. Containers are assumed to be breachable. In interviews, emphasizing runtime threat models is a strong signal.
Follow-up 2. Staff level. Why isn't encrypting Kubernetes secrets enough?
Answer: encryption protects secrets at rest, not in use. Once mounted, they are decrypted for the application. In interviews, explaining this distinction shows practical Kubernetes security knowledge.
Follow-up, curveball. What if the application only supports file-based secrets?
Answer: then secrets must be scoped narrowly, rotated frequently, and isolated to dedicated workloads. File-based delivery is a constraint, not a justification for broad exposure. In interviews, the correct response is containment.
8. Pro insider tip.
If a container is compromised, assume its secrets are too. In interviews, saying, "We designed secret delivery assuming container breach," signals senior Kubernetes security maturity.
Real-world cybersecurity incident, number 117. Lateral movement via Kubernetes service accounts.
A single compromised workload was used to access multiple internal services across namespaces without exploiting the control plane or container runtime. The attacker moved laterally using legitimate Kubernetes service account credentials mounted into pods.
1. The setup, everything looks secure.
The cluster used service accounts for workload identity, RBAC for access control, and namespace isolation. Service accounts were automatically mounted into pods by default.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed RBAC was enabled. Service accounts were used instead of static credentials, and cross-namespace access was reviewed at a high level.
3. The breach, what failed anyway.
After compromising a single pod, the attacker used the mounted service account token to call the Kubernetes API and access resources in other namespaces. Because permissions were broadly scoped, lateral movement was trivial.
4. Where controls broke, diagnosis.
Service account identity was treated as safe by default. Automatic token mounting and overscoped RBAC bindings expanded blast radius far beyond the original workload.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Service accounts are credentials, not metadata. 2. Automatic token mounting increases blast radius. 3. Namespace isolation fails without scoped identities. 4. Lateral movement often uses valid tokens. 5. Workload identity must be least privileged. Here is Kubernetes service account and role binding YAML showing how broad permissions enable lateral movement across namespaces. Disclaimer: always test code in a non-production environment. Here is the code block binding a cluster-scoped role, extending access beyond the intended namespace. This code snippet grants read access to resources across the cluster, enabling reconnaissance and lateral movement.
6. The trade-off nobody mentions.
1. Disabling automatic token mounting breaks some workloads. 2. Fine-grained RBAC increases configuration overhead. 3. Identity design requires coordination across teams. 4. The benefit is containing compromise to a single workload.
Follow-up 1. Senior level. How do you prevent service account lateral movement?
Answer: I disable automatic service account token mounting by default, scope RBAC tightly, and use separate identities per workload. In interviews, emphasizing token minimization signals deep Kubernetes security experience.
Follow-up 2. Staff level. Why is lateral movement so common in Kubernetes?
Answer: because service accounts are easy to overlook and permissions accumulate quietly. Valid tokens are more reliable than exploits. In interviews, explaining this reality shows practical threat awareness.
Follow-up curveball. What if workloads require API access?
Answer: then access must be explicitly scoped to required resources and verbs only. Broad access is never justified by convenience. In interviews, the correct response is precise authorization.
8. Pro insider tip.
If a pod has an API token, assume it will be used. In interviews, saying, "We disable automatic service account tokens unless explicitly required," signals senior Kubernetes security maturity.
Real-world cybersecurity incident. Number 118. Flat Kubernetes cluster with no network policies.
A Kubernetes cluster allowed unrestricted east-west traffic between workloads across namespaces. An attacker moved freely between services without exploiting Kubernetes itself. The breach occurred because network isolation was never enforced.
1. The setup. Everything looks secure.
The cluster used namespaces, RBAC, and authenticated service accounts. Ingress traffic was restricted at the edge, and external exposure was tightly controlled.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed namespace separation, RBAC enforcement, and secure ingress configuration. Internal pod-to-pod traffic was assumed to be trusted and was not reviewed.
3. The breach. What failed anyway?
After compromising one service, the attacker scanned the cluster network and accessed internal services across namespaces. Because there were no network policies, all traffic was implicitly allowed.
4. Where controls broke. Diagnosis.
Namespace boundaries were treated as security boundaries, but networking was flat. Without network policies, namespaces provided no runtime isolation.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Namespaces do not isolate network traffic by default. 2. Kubernetes networking is allow-all unless restricted. 3. East-west traffic is the primary attack path. 4. Network policies define blast radius. 5. Zero trust applies inside the cluster. Here is Kubernetes network policy, YAML showing how absence of ingress rules results in unrestricted pod-to-pod communication. Disclaimer: always test code in a non-production environment. Here is the code snippet selecting all pods in the namespace, forming the basis for default deny behavior. This code block defines ingress policy enforcement, without which all traffic is allowed by default.
6. The trade-off nobody mentions.
1. Network policies require deep understanding of service communication. 2. Misconfiguration can cause outages. 3. Policy maintenance adds operational overhead. 4. The benefit is containing lateral movement.
Follow-up 1. Senior level. Why are network policies critical in Kubernetes security?
Answer: because they are the only native mechanism to restrict east-west traffic. Without them, every compromised pod can reach every service. In interviews, explicitly calling out default allow networking is a strong Kubernetes signal.
Follow-up 2. Staff level. Why do teams avoid network policies?
Answer: because they are hard to design without breaking services. Flat networks feel easier until an incident occurs. In interviews, Explaining this trade-off shows operational realism.
Follow-up, curveball. What if the CNI does not support network policies?
Answer, then the cluster is not production grade from a security standpoint. Alternative enforcement must be introduced. In interviews, the correct response is acknowledging platform limits.
8. Pro insider tip.
If your cluster has no network policies, assume lateral movement is trivial. In interviews, saying, "We default deny east-west traffic," signals senior Kubernetes security expertise.
Real-world cybersecurity incident, number 119. Image pulls from untrusted container registries.
A production Kubernetes workload was compromised before it ever started serving traffic. No runtime exploit was required. The attack succeeded because the cluster pulled and executed a container image from an untrusted registry.
1. The setup, everything looks secure.
The cluster enforced RBAC, network isolation, and runtime hardening. Images were referenced by name and tag, and deployment pipelines completed successfully without errors.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that images were scanned for known vulnerabilities and that deployment pipelines were approved. Registry trust and image provenance were not explicitly validated.
3. The breach, what failed anyway.
An attacker published a malicious image with a trusted name in a public registry. The cluster pulled the image automatically and executed attacker-controlled code as part of normal workload startup.
4. Where controls broke, diagnosis.
Security controls focused on image contents but ignored image origin. Without registry allow listing and signature verification, image names were treated as trustworthy.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Image scanning does not prove image identity. 2. Registry trust is a security boundary. 3. Unsigned images are untrusted code. 4. Supply chain risk starts at image pull. 5. Execution begins at container startup. Here is Kubernetes pod specification, showing how pulling images from public registries allows untrusted code execution. Disclaimer, always test code in a non-production environment. Here is the code snippet referencing an image from a public registry, without any trust or signature enforcement. This code block shows the workload executing whatever image is pulled, regardless of provenance.
6. The trade-off nobody mentions.
1. Restricting registries reduces flexibility. 2. Developers must publish images to approved locations. 3. Signature verification adds pipeline complexity. 4. The benefit is preventing execution of untrusted code.
Follow-up 1. Senior level. Why isn't vulnerability scanning enough?
Answer, because scanning only checks known flaws, not who built the image. A clean image can still be malicious. In interviews, distinguishing identity from content signals supply chain maturity.
Follow-up 2. Staff level. How do you enforce trusted registries?
Answer, I use admission policies to allow only approved registries and require image signatures. Registry trust is enforced at deploy time, not by convention. In interviews, mentioning admission enforcement is a strong signal.
Follow-up curveball. What if teams need public images?
Answer, then those images must be mirrored into a trusted internal registry and signed. Public does not mean trusted. In interviews, the correct response is controlled ingestion.
8. Pro insider tip.
If you didn't build it or sign it, don't run it. In interviews, saying, "We only run signed images from approved registries," signals senior Kubernetes supply chain expertise.
Real-world cybersecurity incident, number 120. Compromised init containers.
A Kubernetes workload was compromised before the main application container even started. No runtime exploit was required, and no RBAC rules were violated. The attack succeeded because a compromised init container executed attacker-controlled logic during pod startup.
1. The setup, everything looks secure.
The cluster enforced RBAC, network policies, and runtime hardening. Application containers were minimal and well-scanned. Init containers were used for setup tasks such as migrations, configuration generation, and dependency checks.
2. What passed audits? Security incidents that passed every audit.
Audits verified application images, RBAC enforcement, and namespace isolation. Init containers were treated as auxiliary logic, and were not reviewed with the same rigor as primary workloads.
3. The breach, what failed anyway.
An attacker modified the init container image used by the deployment. When pods started, the init container executed malicious logic, altered configuration, and planted persistence before the main application launched.
4. Where controls broke, diagnosis.
Security controls focused on long-running containers and ignored startup execution paths. Init containers ran with full trust and equivalent privileges, making them an ideal supply chain insertion point.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Init containers execute before security assumptions apply. 2. Startup code has the same impact as runtime code. 3. Supply chain trust must include init containers. 4. Early execution paths are high-value targets. 5. Pod security begins before the app starts. Here is Kubernetes pod specification, showing how compromised init containers execute untrusted logic before application startup. Disclaimer: always test code in a non-production environment. Here is the code block defining init containers, which run before any application container starts. This code snippet shows an init container image pulled without provenance guarantees, executing attacker-controlled logic first.
6. The trade-off nobody mentions.
1. Securing init containers adds review overhead. 2. Startup pipelines become more complex. 3. Failures block pod startup entirely. 4. The benefit is eliminating pre-runtime compromise paths.
Follow-up 1. Senior level. Why are init containers such an attractive attack vector?
Answer: because they run first and are implicitly trusted. Anything they change affects the entire pod lifecycle. In interviews, calling out startup execution as a blind spot signals deep Kubernetes threat awareness.
Follow-up 2. Staff level. How do you secure init containers properly?
Answer: I apply the same supply chain controls, image signing, and runtime restrictions as application containers. Init containers are not exempt. In interviews, emphasizing equal treatment is a strong signal.
Follow-up curveball. What if teams treat init containers as harmless setup code?
Answer: then they misunderstand Kubernetes execution order. Setup code runs with full effect on the pod. In interviews, the correct response is reclassifying init containers as privileged execution paths.
8. Pro insider tip.
If you trust init containers blindly, you trust attackers early. In interviews, saying, "We secure init containers like production code," signals senior Kubernetes security mastery.
Category 12 wrap-up. Kubernetes is the new operating system.
Every incident in this category shares the same root cause. Kubernetes was treated as an orchestration tool instead of an operating system. Security controls existed, audits passed, and best practices were documented. Yet runtime behavior, mounts, tokens, privileges, startup execution quietly undermined every assumption about isolation.
What senior engineers miss?
Most cloud breaches blamed on AWS or GCP are actually Kubernetes failures. Secure accounts still fall when runtime defaults are trusted blindly. In real incidents, attackers do not break Kubernetes. They use it exactly as configured.
The interview level takeaway.
Kubernetes security is not about knowing YAML. It is about understanding execution order, identity propagation, and isolation boundaries at runtime. Senior engineers are expected to reason about blast radius inside the cluster, not just at the cloud perimeter.
Transition from runtime exploits to voluntary data loss.
So far, every incident involved systems behaving exactly as configured, but still being abused. The next category takes this even further. There is no exploit, no misconfiguration, and no attacker breaking in. The data leaves because employees send it out themselves.
Why the next category is different.
Traditional security tooling stops at infrastructure and applications. It does not see browsers, prompts, SaaS AI tools, or personal workflows. The next failures do not violate policies, they bypass them entirely.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving. Interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 13. Shadow AI and Data Sovereignty Incidents.
These incidents are not traditional AI attacks. There is no malware, no exploit chain, and no adversary breaking controls. Instead, sensitive data leaves the organization through well-intentioned employee behavior using AI tools that sit completely outside existing security boundaries.
Why this category matters in 2026 and beyond.
Shadow AI incidents bypass firewalls, IAM policies, and endpoint protection entirely. They occur in browsers, SaaS tools, and personal workflows that are usually compliant, until sensitive data crosses an irreversible boundary. Most organizations discover these incidents only after data has already propagated into external AI systems.
The core misconception.
Most security programs assume data loss requires malicious intent. Shadow AI breaks this assumption. Employees are not attacking the organization, they are optimizing productivity. The security failure is architectural, not behavioral.
Shadow AI and Data Sovereignty Incidents we are covering.
121. Employees pasting sensitive data into ChatGPT. 122. Code snippets containing secrets used in LLM prompts. 123. Proprietary documents uploaded to SaaS AI tools. 124. Unapproved browser extensions with AI access. 125. Auto-syncing meeting transcripts into AI assistants. 126. So-called private AI tools retaining context unexpectedly. 127. Cross-border data leakage via AI inference. 128. Prompt history visible across teams or tenants. 129. No audit trail for AI-assisted decisions. 130. Shadow AI bypassing data classification rules. CISO reality. We didn't get breached. We voluntarily exported our data.
Real-world cybersecurity incident number 121. Employees pasting sensitive data into ChatGPT.
Sensitive internal data left the organization without any breach, exploit, or malicious insider. Employees voluntarily pasted proprietary information into a public AI assistant to speed up analysis, documentation, or troubleshooting. No security controls were triggered because no system was technically compromised.
1. The setup. Everything looks secure.
The organization enforced IAM, endpoint protection, DLP on email, and strict network egress controls. Employees were trained on data handling policies, and no unauthorized file transfers were detected.
2. What passed audits. Security incidents that passed every audit.
Audits verified encryption at rest and in transit, access controls on internal systems, and proper data classification. There were no indicators of compromise, no malware, and no policy violations within monitored systems.
3. The breach. What failed anyway.
Employees copied sensitive customer data, internal documents, or proprietary logic into ChatGPT prompts. Once submitted, the data left organizational control and entered an external AI system with unknown retention, training, and access characteristics.
4. Where controls broke, diagnosis.
Security controls assumed data loss required malicious intent or system compromise. Browser-based AI usage sat outside traditional monitoring and DLP enforcement. The organization had no visibility into prompt content or data flow beyond the endpoint.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. This is not an AI breach. It is voluntary data exfiltration. 2. Employees optimize productivity, not security boundaries. 3. Browsers bypass most traditional security controls. 4. Data classification fails when enforcement is missing. 5. Shadow AI must be treated as an insider risk.
6. The trade-off nobody mentions.
1. Blocking AI tools outright reduces productivity. 2. Strict controls frustrate high-performing engineers. 3. Monitoring prompts raises privacy concerns. 4. The alternative is irreversible data loss outside the perimeter.
Follow-up 1. Senior level. Why didn't DLP prevent this?
Answer: because most DLP systems focus on files, email, and network transfers, not interactive browser prompts. Copy-paste into a web form often bypasses enforcement entirely. In interviews, explaining this gap shows real-world security tooling experience.
Follow-up 2. Staff level. Isn't this just a training problem?
Answer: training helps, but it does not scale against convenience. Engineers will always choose speed under pressure. In interviews, the correct framing is architectural guardrails, not perfect user behavior.
Follow-up, curveball. What if leadership encourages AI usage?
Answer: then governance must evolve alongside adoption. Approved AI tools, usage policies, and monitoring must be introduced explicitly. In interviews, acknowledging business pressure while controlling blast radius is the senior answer.
8. Pro insider tip.
If employees can paste it into a browser, you've already lost perimeter control. In interviews, saying, "We treat browser-based AI as an unmanaged data egress channel," signals 2026 ready security thinking.
Real-world cybersecurity incident. Number 122. Code snippets containing secrets used in LLM prompts.
Sensitive credentials were exposed without any breach, malware, or repository compromise. Engineers pasted code snippets into an AI assistant for debugging and refactoring, unaware that the snippets contained live secrets. The data left organizational control instantly and irreversibly.
1. The setup. Everything looks secure.
Secrets were managed through vaults and environment variables. Source repositories were scanned for credentials, access was tightly controlled, and CI/CD pipelines enforced secret detection. Developers followed documented secure coding practices.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed that no secrets were committed to repositories, vault policies were enforced, and rotation procedures existed. Endpoint and network monitoring showed no anomalous outbound connections.
3. The breach. What failed anyway?
Developers copied runtime code into LLM prompts to diagnose errors. The snippets included API keys, tokens, and database credentials that were valid in production. Once submitted, those secrets were transmitted to an external AI system outside governance controls.
4. Where controls broke, diagnosis.
Security controls focused on repositories and pipelines, not interactive workflows. Secret scanning did not apply to clipboard usage or browser prompts. The organization had no visibility into what developers shared with AI tools.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Secrets are most vulnerable during debugging. 2. Clipboard workflows bypass every pipeline control. 3. AI prompts are an unmanaged egress channel. 4. Developers optimize speed under pressure. 5. Secret hygiene must include human workflows.
6. The trade-off nobody mentions.
1. Blocking copy-paste into browsers hurts productivity. 2. Automated redaction can remove useful context. 3. Monitoring prompts raises trust concerns. 4. The alternative is leaking live production credentials.
Follow-up 1. Senior level. Why didn't secret scanning catch this?
Answer: because scanning tools protect code at rest, not code in motion. Clipboard and prompt-based workflows sit completely outside CI/CD boundaries. In interviews, explaining this distinction shows real operational awareness.
Follow-up 2, staff level. Can't we just rotate the leaked secrets?
Answer: rotation limits impact, but it does not undo exposure. Once secrets leave the organization, you lose control over retention and reuse. In interviews, acknowledging irreversibility is a senior signal.
Follow-up, curveball. What if developers insist AI is essential for debugging?
Answer: then approved tooling and guardrails must be provided. Security should enable safe usage, not force shadow behavior. In interviews, framing this as governance evolution is the correct answer.
8, pro insider tip.
If secrets appear in logs or stack traces, assume they will appear in AI prompts too. In interviews, saying, "We treat debugging as a high-risk data exposure moment," signals modern security maturity.
Real-world cybersecurity incident, number 123. Proprietary documents uploaded to SaaS AI tools.
Highly sensitive internal documents were uploaded into third-party AI tools to summarize, rewrite, or analyze content. No security control was bypassed and no alert was triggered. The data left organizational custody because the workflow itself was never governed.
1. The setup. Everything looks secure.
The organization enforced strict access controls on internal document repositories, used encryption at rest and in transit, and applied data classification labels. File sharing outside approved systems was restricted and logged.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed document access controls, retention policies, and secure internal collaboration platforms. There was no evidence of unauthorized downloads, email leaks, or external file transfers within monitored systems.
3. The breach. What failed anyway?
Employees downloaded proprietary documents and uploaded them directly into SaaS AI tools for summarization and analysis. Once uploaded, the documents were processed and retained according to the AI provider's policies, outside organizational governance.
4. Where controls broke. Diagnosis.
Security controls focused on storage and sharing systems, not user-driven browser uploads. Data classification labels had no enforcement mechanism once files left approved platforms.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Data controls ended at approved repositories. 2. Browsers act as uncontrolled data brokers. 3. AI tools are treated as productivity software, not vendors. 4. Document uploads bypass retention and deletion policies. 5. Governance must follow data, not platforms.
6. The trade-off nobody mentions.
1. Restricting uploads slows legitimate work. 2. Approved AI tooling requires procurement and review. 3. Content filtering may reduce AI usefulness. 4. The alternative is uncontrolled proprietary data exposure.
Follow-up 1. Senior level. Why wasn't this detected as data exfiltration?
Answer: because the traffic looked like normal HTTPS uploads from a browser. There was no malware, no unusual destination, and no policy violation at the network layer. In interviews, explaining this normalcy gap shows real-world experience.
Follow-up 2. Staff level. Can data classification labels prevent this?
Answer: labels inform users, but they do not enforce behavior outside managed systems. Once a file is downloaded, labels lose authority. In interviews, recognizing this limitation signals maturity.
Follow-up, curveball. What if teams argue this improves quality and speed?
Answer: then leadership must explicitly balance productivity gains against data sovereignty risk. Security should enable approved paths, not pretend the behavior doesn't exist. In interviews, acknowledging this trade-off is the correct answer.
8. Pro insider tip.
If employees can download it, they can upload it somewhere else. In interviews, saying, "We govern document flows beyond our repositories," signals modern data sovereignty thinking.
Real-world cybersecurity incident, number 124. Unapproved browser extensions with AI access.
Sensitive enterprise data was exposed through browser extensions that integrated AI capabilities into everyday workflows. No malware was installed, no system was compromised, and no alert fired. The data was accessed and transmitted by extensions operating with user-granted permissions.
1. The setup. Everything looks secure.
Corporate endpoints were managed, disk encryption was enabled, and endpoint protection agents were running. Users authenticated through SSO, and access to internal applications was tightly controlled.
2. What passed audits? Security incidents that passed every audit.
Audits verified endpoint compliance, patching levels, and approved software inventories. Browser extensions were considered user-level productivity tools and were not part of formal security reviews.
3. The breach. What failed anyway?
Employees installed AI-powered browser extensions that could read page content, form inputs, and clipboard data. The extensions transmitted sensitive information to external AI services as part of normal operation, outside enterprise monitoring.
4. Where controls broke. Diagnosis.
Security controls assumed browsers were passive clients. Extension permission models allowed broad access once users clicked approve. The organization had no visibility into extension behavior or data flows.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Browser extensions execute with user authority. 2. Permissions are granted once and rarely revisited. 3. AI extensions act as covert data brokers. 4. Endpoint security does not inspect extension logic. 5. Shadow AI often hides in productivity tooling.
6. The trade-off nobody mentions.
1. Restricting extensions frustrates users. 2. Allow listing requires continuous maintenance. 3. AI features embedded in browsers are hard to detect. 4. The alternative is uncontrolled data leakage.
Follow-up 1. Senior level. Why aren't browser extensions treated as third-party vendors?
Answer: because they are installed by users, not procured by IT. This bypasses vendor risk management entirely. In interviews, explaining this procurement blind spot signals senior governance awareness.
Follow-up 2. Staff level. Can endpoint protection stop malicious extensions?
Answer: only partially. Most extensions operate within browser sandboxes and use legitimate APIs. In interviews, recognizing that EDR visibility stops at the browser boundary shows realism.
Follow-up curveball. What if teams rely on these extensions daily?
Answer: then the organization must formally approve, review, and monitor them. Shadow usage should be converted into governed usage. In interviews, the correct answer is controlled enablement, not blanket bans.
8. Pro insider tip.
If you don't control browser extensions, you don't control data flow. In interviews, saying, "We treat extensions as unvetted SaaS endpoints," signals 2026 ready security thinking.
Real-world cybersecurity incident. Number 125. Auto-syncing meeting transcripts into AI tools.
Confidential business discussions were exposed without any breach, malware, or malicious insider. Meeting transcripts were automatically synchronized into AI tools for summarization and note generation. Sensitive content left organizational control as part of a default productivity workflow.
1. The setup. Everything looks secure.
The organization used approved video conferencing platforms with access controls, encrypted meetings, and authenticated participants. Recording permissions were restricted, and meeting access logs were reviewed regularly.
2. What passed audits? Security incidents that passed every audit.
Audits verified meeting security settings, participant authentication, and encryption. There were no unauthorized recordings, downloads, or external meeting links detected within the conferencing platform.
3. The breach. What failed anyway?
Meeting transcripts were automatically exported to AI tools connected through calendar integrations or built-in assistants. Once synced, the transcripts were processed and retained outside the organization's governance and retention policies.
4. Where controls broke. Diagnosis.
Security controls focused on meeting access, not downstream data flows. Automatic integrations were trusted implicitly, and transcript data was treated as low risk once meetings ended.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Meetings are data sources, not ephemeral events. 2. Transcripts contain strategic and personal data. 3. Auto-sync turns conversations into external assets. 4. Integrations bypass traditional approval workflows. 5. Governance must include collaboration metadata.
6. The trade-off nobody mentions.
1. Disabling auto-sync reduces meeting efficiency. 2. Manual controls increase cognitive load on users. 3. Reviewing integration slows adoption. 4. The alternative is silent leakage of sensitive discussions.
Follow-up 1. Senior level. Why wasn't this treated as data exfiltration?
Answer: because the data moved through approved integrations using normal APIs. There was no anomaly, no suspicious destination, and no explicit policy violation. In interviews, explaining this implicit trust gap shows real-world experience.
Follow-up 2. Staff level. Are meeting transcripts really sensitive?
Answer: yes. They often contain strategic plans, customer information, and internal debates. In interviews, recognizing meetings as high-value data sources signals mature threat modeling.
Follow-up, curveball. What if leadership mandates AI-generated meeting summaries?
Answer: then approved tools, scoped retention, and clear ownership must be defined upfront. Security should guide safe enablement, not block adoption. In interviews, balancing governance with business needs is the correct answer.
8. Pro insider tip.
If conversations are transcribed, they become data assets. In interviews, saying, "We govern meeting metadata like documents," signals modern data sovereignty thinking.
Real-world cybersecurity incident, number 126. Private AI tools retaining context accidentally.
Sensitive internal data was exposed even though employees believed they were using a private or enterprise-scoped AI tool. No public AI platform was involved, and no explicit sharing occurred. The data persisted because context retention behavior was misunderstood.
1. The setup. Everything looks secure.
The organization adopted an enterprise AI assistant marketed as private and compliant. Access was authenticated through SSO, data residency claims were documented, and internal approvals were completed.
2. What passed audits? Security incidents that passed every audit.
Audits verified vendor contracts, privacy statements, and authentication controls. There was no evidence of data being sent to public models or external consumers.
3. The breach. What failed anyway?
Prompts containing sensitive data were retained across sessions and surfaced later in unrelated interactions. Other users with access to the same AI workspace encountered prior context without realizing its origin.
4. Where controls broke. Diagnosis.
Security assumed privacy meant statelessness. Context retention, embeddings, and conversation memory were enabled by default. Data persisted beyond user intent and visibility.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Private does not mean stateless. 2. Context retention is a form of data storage. 3. Memory defaults matter more than access controls. 4. AI systems leak through reuse, not theft. 5. Retention must be explicit, not assumed.
6. The trade-off nobody mentions.
1. Disabling memory reduces AI usefulness. 2. Session isolation limits long-term assistance. 3. Explicit deletion adds operational overhead. 4. The alternative is silent cross-user data exposure.
Follow-up 1. Senior level. Why is context retention so dangerous?
Answer: because it turns transient prompts into durable data. Users do not reason about prompts as stored assets. In interviews, calling memory a storage layer signals deep AI risk understanding.
Follow-up 2. Staff level. Didn't vendor privacy guarantees prevent this?
Answer: they often cover external sharing, not internal reuse. Context persistence is usually allowed by design. In interviews, distinguishing privacy from retention is a strong signal.
Follow-up, curveball. What if teams rely on long-term AI memory?
Answer: then memory scope, retention limits, and visibility must be explicitly designed. Persistent context must be treated like a database. In interviews, the correct answer is governance, not blind trust.
8. Pro insider tip.
If an AI remembers, it stores. In interviews, saying, "We treat AI memory as regulated data storage," signals 2026 ready security maturity.
Real-world cybersecurity incident, number 127. Cross-border data leakage via AI inference.
Sensitive data subject to regional residency requirements was exposed without any file transfer, upload, or explicit sharing. The leakage occurred through AI inference and processing paths that routed data across geographic boundaries outside approved regions.
1. The setup. Everything looks secure.
The organization enforced data residency controls, region-specific storage, and geo-restricted SaaS platforms. Vendors provided assurances that customer data would remain within approved geographic boundaries.
2. What passed audits. Security incidents that passed every audit.
Audits verified regional storage locations, contractual data residency clauses, and compliance certifications. There were no cross-border file transfers detected and no violations within traditional data pipelines.
3. The breach. What failed anyway.
Sensitive inputs were processed by AI services that performed inference or embedding generation in global compute regions. Although data was not permanently stored, it was transmitted and processed outside approved jurisdictions during model execution.
4. Where controls broke. Diagnosis.
Security controls focused on data storage and retention, not transient processing paths. AI inference pipelines were treated as stateless and therefore excluded from residency enforcement.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Data residency applies to processing, not just storage. 2. Inference routes can cross borders invisibly. 3. Transient data movement still triggers compliance risk. 4. AI workloads abstract away geography by default. 5. Sovereignty requires end-to-end data flow control.
6. The trade-off nobody mentions.
1. Restricting inference regions reduces model availability. 2. Regional AI capacity may lag global offerings. 3. Latency increases when compute is constrained. 4. The alternative is silent regulatory violation.
Follow-up 1. Senior level. Why doesn't encryption solve cross-border inference risk?
Answer: because encryption protects confidentiality, not location. Data must still be decrypted to run inference. In interviews, explaining that processing location matters even for encrypted data signals deep compliance understanding.
Follow-up 2. Staff level. How do you enforce regional inference boundaries?
Answer: I require region-pinned inference endpoints, vendor transparency on execution paths, and explicit guarantees on processing geography. In interviews, calling out inference locality is a strong signal.
Follow-up curveball. What if the AI provider cannot guarantee regional processing?
Answer: then the data cannot be sent to that service. Compliance is binary. In interviews, the correct answer is refusing the integration or limiting data scope.
8. Pro insider tip.
If AI processes your data, geography matters even when nothing is stored. In interviews, saying, "We treat inference as data transfer," signals senior data sovereignty expertise.
Real-world cybersecurity incident. Number 128. Prompt history visible across teams.
Sensitive internal prompts became visible to users outside their original team without any breach, exploit, or access control failure. The exposure occurred because AI prompt history was shared at the workspace or tenant level by default.
1. The setup. Everything looks secure.
The organization deployed an enterprise AI tool with SSO, role-based access, and team workspaces. Users assumed their prompts were private to their sessions or immediate teams.
2. What passed audits. Security incidents that passed every audit.
Audits verified authentication, workspace access controls, and vendor security certifications. There were no indicators of unauthorized logins or privilege escalation.
3. The breach. What failed anyway.
Prompts containing sensitive context, customer data, and internal reasoning were accessible through shared prompt history views. Other teams encountered this information during normal AI usage without realizing its origin.
4. Where controls broke. Diagnosis.
The system assumed prompts were harmless artifacts. Prompt history was treated as collaboration data rather than regulated information, and default visibility settings were overly broad.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Prompts often contain raw sensitive data. 2. Shared history creates unintended data exposure. 3. Visibility defaults define real security posture. 4. AI collaboration features blur data boundaries. 5. Prompt governance must match data sensitivity.
6. The trade-off nobody mentions.
1. Isolating prompt history reduces collaboration benefits. 2. Per team isolation increases administrative overhead. 3. Users lose shared learning from past prompts. 4. The alternative is silent cross-team data leakage.
Follow-up 1. Senior level. Why weren't access controls sufficient here?
Answer: because access controls governed users, not data artifacts. Prompt history lived outside traditional document models. In interviews, recognizing that artifacts need their own access model signals senior thinking.
Follow-up 2. Staff level. Should prompts be treated like documents?
Answer: yes, when they contain regulated or sensitive information. Prompts are unstructured but high risk. In interviews, stating that prompts are data assets shows modern governance awareness.
Follow-up curveball. What if teams want shared prompt libraries?
Answer: then prompts must be curated, sanitized, and explicitly published. Default sharing is the problem. In interviews, emphasizing intentional sharing over implicit visibility is the correct answer.
8. Pro insider tip.
If prompts are shared, data is shared. In interviews, saying, "We default prompts to private and publish intentionally," signals 2026 ready AI governance maturity.
Real-world cybersecurity incident. Number 129. No audit trail for AI-assisted decisions.
Critical business and technical decisions were influenced by AI-generated recommendations, yet no record existed of how those decisions were made. When outcomes were challenged, the organization could not reconstruct inputs, prompts, or model outputs.
1. The setup. Everything looks secure.
The organization adopted AI tools to assist with design reviews, incident triage, and operational decisions. Access was authenticated through SSO, usage was approved by leadership, and outputs were treated as advisory.
2. What passed audits? Security incidents that passed every audit.
Audits verified access controls, vendor contracts, and privacy statements. There were no missing logs in core systems, and no unauthorized access was detected.
3. The breach. What failed anyway?
When a decision led to financial and regulatory impact, investigators discovered there was no record of the AI interaction that influenced it. Prompts, context, and outputs were ephemeral and unrecoverable.
4. Where controls broke. Diagnosis.
Security and compliance assumed AI assistance did not constitute a decision system. There was no requirement to log AI inputs or outputs, and no linkage between AI usage and downstream actions.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. AI assistance still influences outcomes. 2. Unlogged decisions are unaccountable decisions. 3. Auditability must extend to AI interactions. 4. Ephemeral prompts create permanent risk. 5. Governance requires traceability.
6. The trade-off nobody mentions.
1. Logging AI interactions raises privacy concerns. 2. Retention policies increase storage costs. 3. Developers fear reduced experimentation. 4. The alternative is unexplainable outcomes.
Follow-up 1. Senior level. Why is AI auditability a security concern?
Answer: because lack of traceability prevents incident reconstruction and accountability. Decisions without provenance cannot be defended or corrected. In interviews, framing auditability as a security control signals senior thinking.
Follow-up 2. Staff level. What should be logged for AI usage?
Answer: at minimum, prompts, context scope, outputs, and decision linkage should be recorded with retention controls. In interviews, describing selective logging shows practical governance awareness.
Follow-up curveball. What if teams resist logging due to fear of surveillance?
Answer: then governance must balance transparency with privacy through scoped retention and access controls. Avoiding logs entirely is not acceptable. In interviews, acknowledging this tension is the correct response.
8. Pro insider tip.
If you can't explain how a decision was made, you can't defend it. In interviews, saying, "We treat AI interactions as auditable decision inputs," signals 2026 ready governance maturity.
Real-world cybersecurity incident. Number 130. Shadow AI bypassing data classification rules.
Sensitive data governed by strict classification policies was processed by AI tools without triggering any controls. No policy was technically violated, yet regulated data crossed boundaries because classification enforcement stopped at internal systems.
1. The setup. Everything looks secure.
The organization used formal data classification schemes, enforced access controls, and trained employees on handling sensitive information. Classified data was restricted within internal repositories and systems.
2. What passed audits. Security incidents that passed every audit.
Audits verified classification labels, access policies, and compliance training. There were no unauthorized downloads, sharing events, or policy violations detected in monitored platforms.
3. The breach. What failed anyway.
Employees manually copied classified data into AI tools to assist with analysis and drafting. Because the AI tools were outside classification enforcement, the data was processed without restriction or visibility.
4. Where controls broke. Diagnosis.
Data classification informed users but did not enforce behavior beyond internal systems. Shadow AI usage bypassed classification boundaries entirely, rendering labels ineffective once data left controlled platforms.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Classification without enforcement is advisory. 2. AI tools ignore internal data labels. 3. Manual workflows defeat automated controls. 4. Data sovereignty ends at system boundaries. 5. Governance must follow data everywhere.
6. The trade-off nobody mentions.
1. Extending enforcement beyond systems is complex. 2. Users resist controls that slow workflows. 3. AI enablement requires cultural change. 4. The alternative is classification theater.
Follow-up 1. Senior level. Why didn't classification prevent this?
Answer: because labels inform but do not enforce outside managed systems. Once data enters a browser or clipboard, classification loses authority. In interviews, explaining this limitation signals real-world governance experience.
Follow-up 2. Staff level. How do you enforce classification with AI tools?
Answer: I restrict which data classes may be used with approved AI tools, enforce context filtering, and block high-risk categories entirely. In interviews, describing policy-to-tool mapping shows maturity.
Follow-up. Curveball. What if the business ignores classification rules for speed?
Answer: then leadership must explicitly accept the risk. Silent bypass is worse than documented exceptions. In interviews, the correct answer is forcing visibility, not pretending controls work.
8. Pro insider tip.
If classification stops at the system boundary, it will be bypassed. In interviews, saying, "We enforce data classes at entry points," signals senior-level data sovereignty expertise.
Category 13. Outro. When security fails without any attacker.
Every incident in this category occurred without exploits, malware, or malicious insiders. Data left the organization because modern workflows moved faster than governance. Shadow AI did not break security controls. It simply operated beyond where those controls existed.
The senior level takeaway.
In 2026 and beyond, the biggest data losses are voluntary. Security programs that focus only on adversaries miss the reality that productivity tools can export sensitive data more efficiently than any attacker.
Transition. From data leaving the system to systems lying.
So far, the failures involved data escaping organizational boundaries. The next category is more dangerous. The data stays inside the system, but its meaning, accuracy, and trustworthiness are silently corrupted.
Please check description or comments section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs. cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 14. Integrity and Logic Corruption Incidents.
These incidents do not steal data and rarely trigger alerts. Systems continue operating normally, audits pass, and metrics look healthy. Yet business outcomes, financial results, and decision-making are quietly altered through valid inputs and approved workflows.
Why integrity failures are the most dangerous.
Confidentiality breaches are visible. Availability failures cause outages. Integrity failures make systems lie. Senior engineers are expected to reason about correctness under adversarial use, not just system uptime.
Integrity and Logic Corruption Incidents we are covering.
131. Business rule manipulation via edge cases. 132. Silent data tampering through valid inputs. 133. Financial rounding exploitation. 134. Race conditions altering transaction outcomes. 135. Replay attacks changing business results. 136. Configuration drift corrupting calculations. 137. Model bias drifting over time. 138. Feature flags altering authorization behavior. 139. Retroactive data edits rewriting history. 140. Workflow abuse without policy violations.
Real-world cybersecurity incident number 131. Business rule manipulation via edge cases.
A production system processed all transactions successfully, passed reconciliation, and triggered no alerts. Months later, financial discrepancies emerged. No data was stolen and no records were altered directly. The system followed its rules, just not in the way anyone intended.
1. The setup. Everything looks secure.
Business rules were implemented in application logic, covered by unit tests, and reviewed during code changes. Inputs were validated, authorization was enforced, and financial operations were audited regularly.
2. What passed audits? Security incidents that passed every audit.
Audits verified access controls, data immutability, and transaction logging. No unauthorized changes were detected, and all calculations followed documented business logic.
3. The breach. What failed anyway?
Attackers repeatedly submitted transactions engineered to fall into rounding and threshold edge cases. Over time, these valid transactions accumulated financial advantage without ever violating a single rule.
4. Where controls broke. Diagnosis.
Security focused on access and data integrity, not outcome integrity. Business rules assumed honest usage patterns and did not model adversarial optimization of edge conditions.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Valid inputs can still produce invalid outcomes. 2. Integrity failures exploit assumptions, not vulnerabilities. 3. Business rules must be adversarially tested. 4. Correctness includes cumulative effects over time. 5. Security must reason about outcomes, not just enforcement. Here is Java business rule logic showing how edge case rounding silently alters financial outcomes. Disclaimer: always test code in a non-production environment. This code snippet enforces rounding down on every transaction. Individually harmless, it becomes exploitable when transactions are adversarially optimized. This block shows the percentage-based calculation that attackers manipulated. by submitting carefully sized inputs.
6. The trade-off nobody mentions.
1. Adversarial testing increases design complexity. 2. Edge case protection may reduce performance. 3. Rules become harder to reason about. 4. The payoff is preserving trust in system outcomes.
Follow-up 1. Senior level. Why wasn't this fraud detection?
Answer: because each transaction was individually valid. Fraud systems look for anomalies, not optimized compliance. In interviews, distinguishing rule abuse from fraud is a strong senior signal.
Follow-up 2. Staff level. How do you prevent this class of issue?
Answer: by modeling adversarial behavior during design and testing cumulative effects. Integrity is about long-term correctness, not single executions. In interviews, outcome modeling signals maturity.
Follow-up curveball. What if the business insists on keeping the rule?
Answer: then monitoring must shift to outcome-based detection. If rules remain exploitable, impact must be bounded. In interviews, acknowledging business constraints is the correct answer.
8. Pro insider tip.
Integrity failures rarely break rules, they optimize them. In interviews, saying, "We test business logic adversarially, not just functionally," signals true senior-level engineering judgment.
Real-world cybersecurity incident number 132. Silent data tampering through valid inputs.
Core business data was altered without exploiting databases, bypassing authorization, or modifying records directly. Every update was valid, authenticated, and logged. The corruption occurred because the system trusted input transformations that subtly changed meaning over time.
1. The setup. Everything looks secure.
The application enforced authentication, role-based authorization, and schema validation. All updates passed through service layer logic, and database constraints ensured structural integrity.
2. What passed audits? Security incidents that passed every audit.
Audits verified access logs, change histories, and database integrity checks. No unauthorized updates or direct data manipulation were detected.
3. The breach. What failed anyway?
Attackers repeatedly submitted valid updates that triggered normalization logic. Each update slightly altered stored values while remaining within accepted bounds. Over time, accumulated changes materially corrupted critical data.
4. Where controls broke. Diagnosis.
Security controls focused on who could change data, not how transformations affected meaning. The system assumed normalization was idempotent and safe under repeated application.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Valid updates can still corrupt meaning. 2. Normalization is a mutation, not a no-op. 3. Integrity failures accumulate quietly. 4. Audits miss semantic drift. 5. Correctness requires transformation awareness. Here is Java input normalization logic, showing how repeated valid updates silently corrupt stored data. Disclaimer: always test code in a non-production environment. This code snippet rounds values on every update. While valid individually, repeated application causes cumulative drift. This block shows normalization applied on each write, not just at ingestion, amplifying the effect over time.
6. The trade-off nobody mentions.
1. Avoiding repeated normalization complicates code paths. 2. Strict immutability increases storage requirements. 3. Semantic checks add processing overhead. 4. The benefit is preserving long-term data correctness.
Follow-up 1. Senior level. Why didn't database constraints prevent this?
Answer: because constraints enforce structure, not meaning. Values stayed within allowed ranges. In interviews, separating structural integrity from semantic integrity signals senior-level thinking.
Follow-up 2. Staff level. How do you detect this kind of corruption?
Answer: by tracking original inputs, monitoring drift over time, and validating idempotence of transformations. In interviews, mentioning drift detection shows real-world experience.
Follow-up curveball. What if normalization is required by compliance?
Answer: then it must be applied once and enforced immutably. Reapplying transformations is the risk. In interviews, proposing one-time normalization is the correct response.
8. Pro insider tip.
If a transformation is not idempotent, it is a potential integrity attack surface. In interviews, saying, "We test transformations for cumulative effects," signals deep systems thinking.
Real-world cybersecurity incident, number 133, financial rounding exploitation.
A financial platform suffered measurable revenue loss without any fraud alerts, unauthorized access, or data tampering. Transactions were processed correctly, balances reconciled, and audits passed. The loss occurred because attackers exploited deterministic rounding behavior at scale.
1. The setup, everything looks secure.
Financial calculations were implemented using standard libraries, reviewed by engineers, and validated by finance teams. Rounding rules were documented, consistent, and compliant with accounting standards.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed correct use of decimal arithmetic, approved rounding modes, and accurate reconciliation reports. No discrepancies appeared at the individual transaction level.
3. The breach, what failed anyway.
Attackers submitted large volumes of transactions engineered to consistently round in their favor. Each transaction complied with business rules, but the cumulative effect produced material financial loss.
4. Where controls broke, diagnosis.
The system assumed rounding effects were negligible per transaction. No controls existed to detect or limit adversarial optimization of rounding behavior over time.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Rounding rules are deterministic attack surfaces. 2. Per-transaction correctness does not guarantee aggregate correctness. 3. Attackers optimize math, not exploits. 4. Integrity failures emerge through repetition. 5. Financial logic must be adversarially modeled. Here is Java financial calculation logic showing how deterministic rounding enables cumulative exploitation. Disclaimer: always test code in a non-production environment. This code snippet enforces downward rounding on every calculation, which attackers exploited by shaping transaction sizes. This block shows the interest computation attackers optimized to maximize rounding bias.
6. The trade-off nobody mentions.
1. Changing rounding rules affects accounting consistency. 2. Randomized or deferred rounding complicates audits. 3. Additional aggregation checks add processing cost. 4. The benefit is preventing systematic financial leakage.
Follow-up 1. Senior level. Why didn't reconciliation catch this?
Answer: because reconciliation validated totals against the same flawed logic. When both sides share the same bias, discrepancies disappear. In interviews, calling this out signals deep financial systems understanding.
Follow-up 2. Staff level. How do you defend against rounding exploitation?
Answer: by validating aggregate outcomes, introducing randomization or balancing adjustments, and monitoring for adversarial input patterns. In interviews, discussing aggregate correctness is a strong signal.
Follow-up, curveball. What if regulations mandate this rounding mode?
Answer: then detection and caps must be introduced. Compliance does not eliminate exploitation risk. In interviews, acknowledging regulatory constraints while mitigating impact is the correct response.
8. Pro insider tip.
If math is deterministic, it can be optimized adversarially. In interviews, saying, "We monitor cumulative effects, not just per transaction correctness," signals senior-level integrity engineering.
Real-world cybersecurity incident, number 134. Race conditions altering transaction outcomes.
A high-throughput transaction system produced inconsistent balances without any failed writes, exceptions, or unauthorized access. All operations were valid, authenticated, and logged. The corruption occurred because concurrent requests exploited timing windows the business logic assumed would never overlap.
1. The setup, everything looks secure.
The application used a CID-compliant databases, transactional boundaries, and optimistic locking at the persistence layer. Business logic was stateless and horizontally scalable, designed for performance under load.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed database transaction isolation, correct use of repositories, and absence of deadlocks or failed commits. Load tests validated throughput, but did not model adversarial concurrency.
3. The breach, what failed anyway.
Attackers issued concurrent requests that raced between read and write phases of business logic. Each request was valid on its own, but interleaving execution paths produced outcomes that violated business invariants.
4. Where controls broke, diagnosis.
Security controls assumed database-level transactions, guaranteed business correctness. The application logic performed multi-step operations without enforcing atomicity across those steps.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Race conditions are integrity failures, not performance bugs. 2. Database transactions do not protect business invariants. 3. Concurrency is an attack surface. 4. Valid requests can still produce invalid outcomes. 5. Correctness must be enforced across execution paths. Here is Java transaction logic showing how non-atomic read-modify write enables race condition exploitation. Disclaimer: always test code in a non-production environment. This code snippet reads the balance outside an atomic operation. Concurrent requests can observe the same initial value. This block performs a write based on stale state, allowing multiple transfers to succeed when only one should.
6. The trade-off nobody mentions.
1. Enforcing atomicity reduces throughput. 2. Stronger locking increases contention. 3. Distributed transactions complicate architecture. 4. The benefit is preserving outcome correctness.
Follow-up 1. Senior level. Why didn't database isolation prevent this?
Answer: because isolation protects rows, not multi-entity business rules. The logic spanned multiple objects and steps. In interviews, distinguishing transactional safety from invariant safety is a senior signal.
Follow-up 2. Staff level. How do you eliminate this class of bug?
Answer: by enforcing atomic operations at the business level, using locking, version checks, or serialized workflows. In interviews, mentioning invariant-based design shows maturity.
Follow-up curveball. What if performance requirements forbid locking?
Answer: then correctness must be enforced through idempotency, reservation models, or eventual reconciliation. Performance cannot justify incorrect outcomes. In interviews, acknowledging trade-offs without compromising integrity is the correct response.
8. Pro insider tip.
If concurrent requests can change outcomes, integrity is already broken. In interviews, saying, "We design business logic to be concurrency safe, not just database safe," signals senior-level systems thinking.
Real-world cybersecurity incident, number 135. Replay attacks altering business outcomes.
A business workflow produced incorrect outcomes without any unauthorized access, data modification, or failed validations. Requests were authenticated, authorized, and syntactically valid. The corruption occurred because previously valid requests were replayed to change outcomes over time.
1. The setup. Everything looks secure.
The application exposed idempotent-looking APIs protected by authentication and authorization. Requests were logged, validated, and processed through standard service layer logic.
2. What passed audits? Security incidents that passed every audit.
Audits verified access controls, API authentication, and correct request handling. No duplicate records were detected, and all requests appeared legitimate in logs.
3. The breach. What failed anyway?
Attackers replayed previously successful requests with the same parameters and identifiers. Because the system lacked replay detection and outcome guards, each replay altered business state cumulatively.
4. Where controls broke, diagnosis.
The system assumed authenticated requests were unique in intent. There was no binding between a request and a single allowed outcome, and no mechanism to detect or reject replays.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Authentication does not guarantee uniqueness. 2. Replays are valid inputs with invalid intent. 3. Idempotency must be enforced explicitly. 4. Business outcomes need one-time guarantees. 5. Replay protection is an integrity control. Here is Java request handling logic showing how missing idempotency allows replayed requests to alter outcomes. Disclaimer: always test code in a non-production environment. This code snippet retrieves the same order state on every replay, assuming the request is unique. This block mutates business state without checking whether the action has already been applied.
6. The trade-off nobody mentions.
1. Idempotency tracking requires additional state. 2. Storage and lookup overhead increase. 3. Strict one-time semantics complicate retries. 4. The benefit is outcome correctness under abuse.
Follow-up 1, senior level. Why wasn't this caught as duplicate processing?
Answer: because the system did not define what duplication meant at the business level. Replays were indistinguishable from legitimate retries. In interviews, highlighting business-level idempotency is a strong senior signal.
Follow-up 2, staff level. How do you prevent replay-based outcome changes?
Answer: by introducing idempotency keys, one-time tokens, or state transitions that are enforced atomically. In interviews, mentioning one-time semantics shows practical experience.
Follow-up curveball. What if clients legitimately retry requests?
Answer: then retries must be explicitly modeled and bounded. Legitimate retries should not alter outcomes. In interviews, distinguishing retries from replays is the correct framing.
8, pro insider tip.
If a request can be replayed to change results, integrity is already broken. In interviews, saying, "We design APIs with one-time outcome guarantees," signals senior-level integrity engineering.
Real-world cybersecurity incident, number 136. Configuration drift, corrupting business calculations.
Business outcomes diverged across environments without any code changes, data tampering, or access violations. Calculations were correct in isolation, yet results differed depending on where the workload executed. The root cause was configuration drift, altering logic assumptions silently.
1. The setup, everything looks secure.
Infrastructure was managed through infrastructure as code, reviewed via pull requests, and deployed through automated pipelines. Application binaries were identical across environments, and configuration values were documented.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed version-controlled IAC, change approvals, and environment parity at a high level. No unauthorized infrastructure changes were detected.
3. The breach, what failed anyway.
Over time, manual hotfixes and emergency overrides caused runtime configuration to drift from declared state. Business calculations relied on configuration-driven thresholds that no longer matched documented intent.
4. Where controls broke, diagnosis.
Security controls focused on code integrity, not configuration integrity. Drift detection was disabled to avoid noise, allowing logic-altering configuration changes to persist undetected.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Configuration is executable logic. 2. Drift changes behavior without code changes. 3. Audits miss runtime divergence. 4. IAC only protects declared state. 5. Integrity requires enforcing convergence. Here is Terraform configuration showing how threshold drift silently alters calculation logic. Disclaimer: always test code in a non-production environment. This code snippet defines the threshold assumed by business logic. When runtime values drift, outcomes diverge silently. This block shows how calculations depend directly on configuration, making drift an integrity risk.
6. The trade-off nobody mentions.
1. Strict drift enforcement increases operational friction. 2. Emergency overrides become harder to apply. 3. False positives can slow incident response. 4. The benefit is deterministic system behavior.
Follow-up 1, senior level. Why is configuration drift a security issue?
Answer: because it changes system behavior without visibility or intent review. Logic moves, but code does not. In interviews, framing drift as an integrity failure signals senior-level understanding.
Follow-up 2, staff level. How do you detect harmful drift?
Answer: by continuously reconciling declared and runtime state, alerting on semantic changes, and enforcing reversion. In interviews, mentioning semantic drift detection is a strong signal.
Follow-up curveball. What if drift is required for emergencies?
Answer: then it must be time-bound, logged, and automatically reverted. Permanent drift is never acceptable. In interviews, acknowledging emergency paths while preserving integrity is the correct answer.
8. Pro insider tip.
If configuration can change logic, it must be protected like code. In interviews, saying, "We treat drift as an integrity incident," signals senior-level architectural maturity.
Real-world cybersecurity incident, Number 137. Feature flags altering authorization behavior.
User permissions changed in production without any role updates, policy changes, or access violations. All requests were authenticated, authorization checks executed successfully, and logs showed no anomalies. The integrity failure occurred because feature flags modified authorization paths at runtime.
1. The setup. Everything looks secure.
The application used role-based access control enforced at the service layer. Feature flags were introduced to enable gradual rollout of new functionality and were managed through a centralized configuration service.
2. What passed audits? Security incidents that passed every audit.
Audits verified RBAC rules, authorization middleware, and access logs. Feature flag systems were reviewed as operational tooling, not as security-relevant components.
3. The breach. What failed anyway?
A feature flag enabled an alternate execution path that bypassed secondary authorization checks. Users gained capabilities that were not intended for their roles, without any explicit permission change.
4. Where controls broke. Diagnosis.
Authorization logic was coupled to feature state. Security assumed feature flags only affected functionality, not access control. Runtime configuration became an implicit policy engine.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Feature flags are executable logic. 2. Authorization paths must be invariant. 3. Runtime toggles can bypass security assumptions. 4. Access control must not depend on rollout state. 5. Flags require security review when touching auth. Here is Java authorization logic showing how feature flag can bypass access control checks. Disclaimer: always test code in a non-production environment. This code snippet enables an execution path based solely on feature state, bypassing role validation. This block shows the intended authorization check, which is skipped when the flag is enabled.
6. The trade-off nobody mentions.
1. Decoupling flags from auth increases implementation effort. 2. Security reviews slow feature rollout. 3. More explicit policy code is required. 4. The benefit is preserving authorization integrity.
Follow-up 1. Senior level. Why wasn't this caught by authorization tests?
Answer: because tests validated roles, not runtime execution paths. Feature state altered behavior outside tested scenarios. In interviews, highlighting path explosion due to flags signals senior awareness.
Follow-up 2. Staff level. How do you prevent flags from affecting security?
Answer: by enforcing authorization checks independent of feature state and reviewing any flag that touches protected paths. In interviews, stating that auth must be invariant is a strong signal.
Follow-up curveball. What if product insists on flagging auth changes?
Answer: then the flag itself must be treated as a privileged security control with restricted access and auditing. In interviews, elevating flags to policy artifacts is the correct response.
8. Pro insider tip.
If a feature flag can change who is authorized, it is a security control. In interviews, saying, "We treat flags as policy when they affect access," signals senior-level judgment.
Real-world cybersecurity incident. Number 138. Model bias drift altering business decisions.
Business decisions slowly shifted in ways that disadvantaged certain users and regions without any explicit rule change, deployment, or access violation. Dashboards looked healthy, models performed within accuracy thresholds, and no alerts fired. The system became unfair and incorrect while appearing stable.
1. The setup. Everything looks secure.
The organization relied on machine learning models to support pricing, prioritization, and risk scoring. Models were trained on historical data, evaluated using standard metrics, and retrained periodically using automated pipelines.
2. What passed audits? Security incidents that passed every audit.
Audits verified training pipelines, access controls, and model performance metrics such as accuracy and precision. No anomalies were detected within defined evaluation windows.
3. The breach. What failed anyway?
Over time, shifts in user behavior and data distribution caused the model to reinforce subtle biases. Decisions increasingly diverged from business intent, yet remained statistically valid within monitored thresholds.
4. Where controls broke. Diagnosis.
Controls focused on aggregate accuracy, not outcome fairness or directional drift. The system assumed retraining preserved intent, even as the data-generating process evolved.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Accuracy does not equal correctness. 2. Bias can drift without performance loss. 3. Models optimize data, not intent. 4. Integrity includes decision impact over time. 5. Monitoring must include fairness signals.
6. The trade-off nobody mentions.
1. Fairness monitoring adds complexity and cost. 2. Business metrics may conflict with equity goals. 3. Bias remediation can reduce short-term performance. 4. The alternative is systemic decision corruption.
Follow-up 1. Senior level. Why is bias drift a security concern?
Answer: because it silently changes system behavior and outcomes without triggering controls. Integrity is compromised when decisions no longer reflect intent. In interviews, framing bias as integrity risk signals senior judgment.
Follow-up 2. Staff level. How do you detect bias drift in practice?
Answer: by monitoring outcome distributions, segment-level impacts, and directional changes over time. Accuracy alone is insufficient. In interviews, mentioning longitudinal fairness monitoring shows real-world experience.
Follow-up, curveball. What if the business prefers higher accuracy over fairness?
Answer: then the trade-off must be explicit and governed. Silent bias is unacceptable. In interviews, insisting on transparency over optimization is the correct stance.
8. Pro insider tip.
If a model's decisions change meaning over time, integrity is already broken. In interviews, saying, "We monitor decision drift, not just model accuracy," signals senior-level AI governance maturity.
Real-world cybersecurity incident. Number 139. Retroactive data edits rewriting history.
Historical records were altered without deleting data, bypassing permissions, or triggering alerts. Reports regenerated cleanly, audits passed, and timelines appeared consistent. The system allowed the past to be changed using valid workflows.
1. The setup. Everything looks secure.
The platform supported data corrections through controlled administrative workflows. Changes were authenticated, logged, and required elevated roles. Historical accuracy was assumed because all edits were traceable.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed role restrictions, change logs, and approval workflows. There were no unauthorized edits and no evidence of data deletion or tampering outside approved paths.
3. The breach. What failed anyway?
Authorized users repeatedly modified historical records to reflect new interpretations rather than corrections. Over time, the meaning of past events changed while remaining internally consistent.
4. Where controls broke. Diagnosis.
Security focused on who could edit records, not when edits should be allowed. The system treated history as mutable truth rather than immutable fact with append-only correction semantics.
5. The interview-winning explanation, solution.
Here's how a senior engineer explains this under interview pressure. 1. Auditability does not equal immutability. 2. History must be append-only. 3. Corrections should not overwrite facts. 4. Time is a security boundary. 5. Integrity requires temporal guarantees. Here is SQL update logic showing how mutable history allows retroactive integrity corruption. Disclaimer: always test code in a non-production environment. This code block shows a direct mutation of historical data, treating past records as editable state. This snippet demonstrates how a single identifier allows rewriting past events without temporal safeguards.
6. The trade-off nobody mentions.
1. Append-only models increase data volume. 2. Correction workflows become more complex. 3. Reporting logic must handle versions. 4. The benefit is preserving historical truth.
Follow-up 1. Senior level. Why aren't audit logs enough?
Answer: because logs record change, not intent or correctness. If history can be rewritten, truth is subjective. In interviews, emphasizing immutability over traceability is a senior signal.
Follow-up 2. Staff level. How do you design immutable history?
Answer: by storing corrections as new records linked to originals and preventing in-place updates. In interviews, describing event sourcing or append-only design shows maturity.
Follow-up, curveball. What if regulations require correcting past data?
Answer: then corrections must be additive and transparent. Overriding history is never acceptable. In interviews, distinguishing correction from erasure is the correct response.
8. Pro insider tip.
If the past can be edited, integrity is optional. In interviews, saying, "We treat time as a security boundary," signals senior-level system design judgment.
Real-world cybersecurity incident, number 140. Workflow abuse without policy violations.
A complex business workflow was abused to produce unauthorized outcomes without breaking any rules, bypassing any controls, or triggering any alerts. Every step was valid, approved, and logged. The system behaved correctly, just not truthfully.
1. The setup. Everything looks secure.
The platform implemented multi-step approval workflows with role checks, validations, and audit logging. Each action required explicit authorization, and no single step granted excessive power.
2. What passed audits? Security incidents that passed every audit.
Audits confirmed correct role enforcement, approval sequencing, and complete audit trails. No step violated policy, and no unauthorized actions were detected.
3. The breach. What failed anyway?
Attackers executed workflow steps in an unexpected but allowed order, chaining approvals and reversals to reach outcomes never intended by the design. The system permitted the sequence, even though the result violated business intent.
4. Where controls broke. Diagnosis.
Security controls validated individual steps, but never validated the end state. The workflow engine assumed that valid steps always lead to valid outcomes.
5. The interview-winning explanation. Solution.
Here's how a senior engineer explains this under interview pressure. 1. Workflows can be adversarially composed. 2. Valid steps do not guarantee valid outcomes. 3. Authorization must reason about state transitions. 4. End-state validation is mandatory. 5. Integrity lives at the workflow level. Here is Java workflow logic showing how valid step execution can still produce invalid end states. Disclaimer: always test code in a non-production environment. This code snippet validates each step in isolation, assuming step-level authorization is sufficient. This block advances workflow state without validating whether the resulting end state is allowed.
6. The trade-off nobody mentions.
1. State validation increases workflow complexity. 2. Designing invariant rules requires upfront effort. 3. More test cases are needed to model abuse paths. 4. The payoff is preserving outcome integrity.
Follow-up 1. Senior level. Why didn't approval controls prevent this?
Answer: because approvals validated permissions, not intent. The system never reasoned about whether the final state should be reachable. In interviews, distinguishing approval from outcome authorization is a senior-level signal.
Follow-up 2. Staff level. How do you defend against workflow abuse?
Answer: by defining allowed state transitions, enforcing invariants, and validating end states explicitly. In interviews, mentioning state machines and invariants shows strong system design maturity.
Follow-up curveball. What if business workflows must remain flexible?
Answer: flexibility cannot come at the cost of correctness. Guardrails must define what outcomes are impossible. In interviews, acknowledging flexibility while enforcing invariants is the correct answer.
8. Pro insider tip.
If workflows can be abused without breaking rules, integrity is already lost. In interviews, saying, "We validate end states, not just steps," signals true senior-level architectural thinking.
Here is the final incident that blows your minds. The system that passed every check and failed anyway.
This incident does not involve a breach, exploit, misconfiguration, or malicious actor. It arises from emergent behavior between correctness guarantees that were individually valid but collectively incompatible. There is no attacker narrative, no CVE, and no log anomaly. Organizations quietly absorb the damage and move on.
The invisible setup.
A large-scale enterprise system enforced strict correctness across multiple dimensions. Data was immutable. Events were append-only. APIs were idempotent. Caches were eventually consistent. Models were retrained continuously. Feature flags were used safely. Every architectural choice followed best practices, and each team was objectively correct.
The assumption nobody documented.
Each subsystem assumed it was the source of truth within its boundary. No subsystem assumed it could be wrong. No mechanism existed to reconcile disagreements between truths that were all locally correct.
The failure that had no moment.
There was no breach date, no outage, no alert. Over several months, different parts of the system began to disagree subtly about the same business reality, customer status, entitlement eligibility, financial exposure. Each view was internally consistent and audit compliant. The system did not fail. It diverged.
Why security tools saw nothing.
Security tooling is designed to detect violations, not contradictions between correct systems. 1. Every action was authorized. 2. Every event was logged. 3. Every right was valid. 4. No invariant was violated inside any single service.
The trust collapse.
Executives received two conflicting but equally defensible reports generated from the same system. Both were correct. Both could not be true at the same time. Trust in the system collapsed overnight, not because it was hacked, but because it could no longer answer a simple question consistently.
The real root cause.
Truth consistency was never treated as a security property. Engineers protected access, integrity, availability, and auditability, but not semantic convergence. No one owned agreement between systems as a first-class requirement.
Why this is worse than a breach.
Breaches end. This does not. Once trust collapses, every decision requires manual verification. Velocity dies. Compliance risk increases. Teams stop believing dashboards. The system is still running, but it is no longer usable.
The senior engineer's epiphany.
A senior engineer eventually said, "We secured every component, but we never secured agreement between them."
The only real fix.
1. Designate a single source of semantic truth. 2. Define reconciliation authority. 3. Treat divergence as a security incident. 4. This is not a data bug, not an ops issue. It is a security failure.
Why you will never read this online.
There is no villain, no exploit, and no lesson that fits a blog headline. Publishing it would mean admitting the architecture itself, not a bug, caused business harm. Most organizations quietly rewrite systems instead.
Pro-level insight.
In 2026 plus, the most dangerous systems are not the ones attackers break. They are the ones that cannot agree with themselves. If a system cannot answer the same question consistently, it is already insecure.
Category 14 wrap-up. When systems lie without breaking.
Every incident in this category shared a dangerous property. Nothing failed loudly. No alerts fired. No access was violated. No data was stolen. The systems behaved exactly as designed, yet outcomes drifted away from truth. Integrity was not broken at the control level. It was broken at the meaning level.
The senior engineer reality.
At senior levels, security is no longer about blocking attackers. It is about ensuring systems cannot be coerced into producing false outcomes through valid behavior. Integrity failures are the hardest to detect because they look like success.
Why integrity is the final boss.
Confidentiality breaches leak data. Availability failures cause outages. Integrity failures destroy trust. Once stakeholders stop believing system outputs, every decision becomes manual, slow, and politically charged.
Finally, the pattern behind every modern incident.
Across all 14 categories, one pattern repeated relentlessly. Systems were not breached, they were misused. Controls worked, audits passed, and architectures followed best practices. Yet incidents still happen because security focused on enforcement instead of intent.
What senior interviews are really testing.
Senior and staff interviews are not testing whether you know tools, frameworks, or controls. They are testing whether you understand where systems fail after everything works. Can you reason about misuse, drift, and unintended outcomes, not just attacks?
The shift that separates levels.
Junior engineers secure components. Mid-level engineers secure systems. Senior engineers secure outcomes. The difference is not knowledge. It is responsibility for what happens when assumptions break.
The final takeaway.
Modern cybersecurity is not about building stronger walls. It is about designing systems that remain truthful under pressure, misuse, and scale. If a system can behave correctly and still betray intent, it is not secure. If this series changed how you think about security, architecture, or interviews, then it did its job. Real-world security is not about stopping attackers. It is about preventing systems from quietly failing the business they exist to protect.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your cybersecurity jobs interviews like junior cybersecurity analyst jobs, cybersecurity analyst jobs, cybersecurity SOC analyst jobs, cybersecurity GRC jobs, cybersecurity CISO jobs, cybersecurity incident responder jobs, cybersecurity vulnerability analyst jobs, cybersecurity malware analyst jobs, cybersecurity engineer jobs, cybersecurity architect jobs, cybersecurity manager jobs, cybersecurity consultant jobs, cybersecurity specialist jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.